found in DNA only, because in RNA we have uracil and not thymine. Okay, so those are our answers for this one.
Okay, problem 40. What are functional groups? Okay, so functional groups are little compounds or molecules that are connected to a larger molecule. Okay, so it could be just one atom. Okay, or it could be a compound. Okay, and it is connected to a larger molecule. Now, why are they important though? So they are important because these functional groups exhibit their own chemical properties. Okay, they have their own chemical properties. Properties, and those properties affect the larger molecule. Okay, so their chemical properties affect the chemistry of the larger molecule that they are connected to. Okay, so hopefully that that gave an emphasis on why we care about functional groups.
Alright, so problem 41 is asking for us to describe the structure of the given functional groups. So starting here with part A. Okay, so starting with part A, we have alkene. And an alkene is characteristic of a double bond between two carbons. So we got a double bond between two carbons, and since each carbon could handle 4 bonds, we can have 2 more other things connected to each of our carbon. So that would be the structure for an alkene. Okay. Part B. Part B, we got alcohol. Okay. So part B, alcohol is characteristic of having an OH connected to a carbon. So we're going to have this carbon, and it will be connected to an O and H. Okay. So we're going to have OH connected to carbon, and as usual, that carbon could handle more bonds to other atoms. Okay. Next, part C. Part C, we have an ester. And an ester is very similar to carboxylic acid, right? Where we have a carbon double bonded to O, and then we have another oxygen right here. And as usual, it would be connected to a carbon. Okay, so what makes ester different is that instead of having hydrogen, you know how carboxylic acid would normally have H bonded to oxygen right there. So instead of having a hydrogen, we're going to have another carbon. Alright, so, and as usual, these carbons can be connected to other atoms as well. So this would be an ester. And finally, we have part D, which is amine. Okay, so amine is, as you probably remember, would have a nitrogen in it. So we have a carbon, and it will be connected to NH2. Okay, or if you want to write that out, we're going to have 2 hydrogen atoms with nitrogen. Okay, and as usual, that carbon have space for 3 other bonds. Okay, so that would be our structure for amine.
Let's propose a structure for the following conditions. For A, we need a ketone, which will have the formula C5H10O. So one possibility here is going to be CH3, CH2, C double bond O, which is our ketone, CH2CH3. So there's one possibility for that molecule. For B, we want an ester with the chemical formula C6H12O2. So this could be one possibility, CH3, CH2, CH2, C double bond O, OCH2CH3. So there's our ester with the formula C6H12O2. And for C, we want an amine and a carboxylic acid, which has the chemical formula C2H5NO2. So this molecule could look something like H2N, CH2, C double bond OOH for the carboxylic acid. Let's draw structures for the following molecular formulas. For A, we have C2H7N, and a possible formula can be CH3CH2NH2, and that could be a structure that can exist. For B, the formula is C4H8, and a possible structure could be CH3CH. We'll include a double bond here, CH3. For C, we have C2H4O, and a possible structure here is CH3CHO as an aldehyde. And for D, we have CH2O2, and a possible structure here can be HCOOH as a carboxylic acid. Let's draw the isomers of C3H8O. We can have CH3, CH2, CH2OH. We can have CH3, CH, CH3OH, and we could also have CH3, CH2, OCH3. So there would be the three isomers of C3H8O.
Problem 45, we are identifying function groups. Okay, so we have here the structure of cocaine, right? Structure of cocaine. And we are given both the line bond structure and the molecular model. Okay, so whatever is helpful or easier for you to use, just go for it, right? And I'm just going to use the line bond structure right here. So I'm using line bond, okay? So the way I want to do these types of problems is just to go on every carbon in the molecule, okay? So this first carbon right here is ACH3, so I'm not as interested, but it is connected to an oxygen, so maybe watch out a little bit, right? But once we get to this second carbon right here, we see that it is a carbonyl carbon, and it's actually a part of this larger function group, including the first CH3, right? So that makes it our ester. Okay, that makes it our ester. And after this carbon, we have this cyclic alkane, right? Got this ring right here. And in that ring, we see a nitrogen, okay? We see this nitrogen right here. But it's not next to any carbonyl carbon, so that makes it our amine, right? So it's not an amide. It's not an amide. Okay? And then once we get to this carbon right here, right, we see that it is connected to an oxygen, and then right next to that is another carbonyl carbon. Okay, so this group together would make another ester. Okay, and finally we see this aromatic ring right here. We got a benzene included in this molecule, so that would be our aromatic ring. Okay, so at this point we've gone over every single carbon in this molecule, and that's all our function groups.
Okay, so problem 46. We're asked to differentiate straight chain versus branched chain alkane. Okay, so straight chain alkane is pretty straightforward. You just need to have all your carbon atoms in one straight chain, hence the name straight chain, right? So what I mean by that is if you have any molecule at all, you'll just have all your carbons in one chain like that. Okay, now you could have other atoms that kind of sort of work as branches, like maybe you can have a nitrogen here, an oxygen here. It doesn't really matter as long as all those carbons are in one chain. Okay, meaning you don't have any carbons sticking out of the main chain. Okay, so moving on with branched chain alkane. Well, branched chain, as the name suggests, has carbons branching out from the main chain. Okay, so if you have a bunch of carbons in your molecule, okay, say this would be your main chain, there would be a carbon somewhere sticking out. Okay, so maybe you got one, maybe you got two, like that, and this would be a CH2, CH3. As long as there's carbon that is outside this main chain, right? So here we see a carbon and another carbon right here. That would be a branched chain alkane. Okay, but what I want to point out here, excuse me, is say we got something like this, right? Got that, and we got maybe we got a carbon, and then maybe you'll have an O, right? OH. Okay, so that would be just an example I came up with. Okay, so now is this a branch chain alkane? Okay, so is this gonna be your main chain, and then is that gonna be your branching group? And the answer is no. Okay, remember the main chain is the longest chain you could find. So if you find the longest chain here, it's actually the carbon. Okay, so that OH is going to be outside your main chain. So actually this molecule right here is a straight chain molecule. Okay, so try not to be confused. And I know it's not exactly a straight line, but they're all in one main chain. So hopefully that explanation was helpful.
Problem 47 is asking for us to differentiate alkane and an alkyl group. Okay, so an alkane is a molecule that contains only CH bonds. Okay, it contains only CH bonds, and all are single bonds. Okay, all are single bonds. Okay, an alkyl group is a substituent, right? It's a substituent that is derived from an alkane. Okay, derived from an alkane. Okay, so if we have, for example, an ethane, right? So an ethane would be 2 carbons, right, and 3 hydrogens each, right? That would be an ethane, right? If this ethane would be connected to a larger molecule, say we have this very large molecule right here, and here we connect our ethane, right? Okay, so once that ethane is connected to a larger molecule, we don't call it ethane anymore. We call it an ethyl group. Okay, so it is derived from the ethane, but since it's now connected to a larger group, we call it an ethyl group. Okay, so that's the same for every single alkane and its corresponding alkyl group. Okay, also one thing to notice is that the alkyl group is missing one of the hydrogens. Okay, so it's missing one of the hydrogens because it's now connected to the larger molecule. Okay, so hopefully that helped clarify the difference between the two terms.
Okay, so for problem 48, we have a molecule here that is proposed with a chemical formula of C3H9. So we're asked, why would scientists be skeptical about this molecule? Okay, so obviously this molecule is supposed to be an alkane, right? And it only has carbons and hydrogens. And the formula that we use for alkanes would be CnH2n plus 2. Okay, so what I mean by that is if carbon has a subscript of 3, or meaning you have 3 carbons in your molecule, right? So you got C3. So N equals 3 right here, okay? So that means your hydrogen is going to have to be 2N plus 2. So 2 times 3, which is N, plus 2 would have to be 8, okay? So this is supposed to be your alkane if you have 3 carbons. And that's precisely why scientists would be skeptical about this molecule, is because it has 9 hydrogens, meaning it has 1 extra than what the carbons could handle. For problem 49, we have a set of molecules given in condensed structures, and we're asked to find what's wrong with it. So there's one thing that is wrong in each of these, and we have to find that. Alright, so starting with part A, we have a carbon double bonded to another carbon here, and we see that this first carbon has 3 hydrogens. Alright, so it has 3 hydrogens, but at the same time, it's also double bonded to carbon number 2, right? So if we rewrite this, we're supposed to have carbon double bonded to another carbon with 3 hydrogens in it. Okay, and that doesn't make sense because here carbon has 5 bonds around it, and that just violates our octet rule here. And so this part right here is what's wrong with molecule A. Okay, so this part, okay, carbon 1 has more hydrogens than it can have. So part B, okay, carbon 1 is CH3 single bonded to carbon 2, nothing suspicious. Alright, and then we got carbon 2 being CH2, okay, and then bonded to carbon 1 and carbon 3. Again, nothing suspicious. So let's move to our double bonds here, okay? So what I want to do is redraw this part, okay? So we have a carbon double bonded to another carbon, and then double bonded to an oxygen, okay? And then this carbon is bonded to, let me number our carbons so we don't confuse ourselves here. 1, 2, 3, 4, 5, okay? So I'm drawing carbon 3 here. So this is carbon 3, and it is bonded to carbon 2. Okay, and then we have a hydrogen with it. And then carbon 4 here is bonded to CH3. Okay, so now that we drew everything, we could clearly see what is wrong here. We see a carbon, and it has 5 bonds with it, right? It is double bonded with oxygen, it's double bonded with a carbon, and then it still has this bond with CH3 right here. So that's what's wrong here. This carbon number 4 has more bonds than it's supposed to have. Okay, so part C. Let's I'm actually gonna go and start counting our carbons here, so we could talk about it easy. So 1, 2, 3, 4, 5. Okay, so carbon 1 here, right? Carbon 1 is CH3 bonded to a carbon. Nothing suspicious about that, right? Carbon 2 seems to be the same. Okay, so again, we come across our triple bond here, and I want to redraw that and see if there's anything wrong with it. Okay, so we got carbon 3, triple bond, C, and then this carbon 4 has 2 hydrogens in it, right? And then it is bonded to ACH3. And then on the left, we got CH2 bonded to carbon 3. So CH2. Okay, so is there anything wrong here? Well, yes, and it's pretty intense compared to part A and part B here. Here we got a carbon having 6 bonds, right? Got 6 bonds. It has a triple bond with carbon 3, and at the same time it still has 3 single bonds with it. So that's just whack. Okay, so that's what's wrong with this molecule. Okay, carbon 4 has just way too many bonds than it's supposed to. Okay. Alright, so we have the structure of vitamin C here on our screen, and we're asked to figure out all the functional groups that are in this structure. So again, the way I want to go about doing these kind of problems is to just go on every single carbon in the molecule and see if they have functional groups connected to them. Okay. So starting with this carbon right here, looking at everything that's connected to it, we see an OH group right here. So we got an alcohol group, right? So that's pretty much it for this carbon. Moving on to the next carbon right here, we'll look at everything attached to it. We got carbons, hydrogens, and this another OH group right here. So another alcohol group. Okay, so moving on, I'll start using a different color here. Moving on to our next carbon. There's really no immediate functional group that comes out of this carbon. So I'll go and proceed to this next carbon right here, which is a part of an alkene, right? So this would be an alkene. All right, so, and then in this alkene, we see two alcohol groups connected to it right here, okay? So this is an alcohol group. This is also an alcohol group, okay? And then moving on to our last last carbon right here, we see that this is actually part of an ester right here, right? With these kinds of functional groups, we have to be a little bit careful because um, sometimes it just looks like a carbonyl group, but we see that it's actually an ester, right? So this is an ester, a cyclic ester to be exact, because it is part of a ring. Okay. So at this point, we've gone over every single carbon in our molecule, and I think we've got all our functional groups. All right, so problem 50, we're naming some alkanes, right? Okay, so let's go for it, starting with part A here. So again, first step is to find the longest chain we could find, okay? So looking at the structure, this seems to be the longest chain, right? And next is we number according to where we have the first branch point. Okay, so I think it's pretty clear that the first branch point is closer if you count from the right instead of from the left. Okay, because if you count from the left, this would be your first branch point. But if you count from the right, this is your first branch point, and this is just closer to the end. So, hopefully I explained that well, but anyways, let's go ahead and count. Got 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so we got 8 carbons, meaning we have an octane, right? We got an octane for 8. Next is let's go and find our alkyl groups, okay? So here on carbon 3, we have a methyl group. So we have 3 methyl, okay? And on carbon 4, we have an ethyl group, okay? So we have CH2, CH3, which is ethyl. Okay, so we got 4 ethyl. Okay, so now that we have that, we can go ahead and combine every information that we have. Okay, so we go by alphabetical, and since E goes before M, we start with 4 ethyl. So we got 4 ethyl, 3 methyl octane. Okay, so 4 ethyl, 3 methyl octane. Next, part B. Again, find the longest chain, and I think this would still be our longest chain. Alright, and as usual, it looks like the first branch point is closer to the right side. Okay, so it's closer if we count from the right side. So let's go ahead and count. Got 1, 2, 3, 4, 5, 6, 7. Okay, we have 7, meaning we have a heptane. Okay, we got a heptane. let me box this answer from part A so we know it's separate. Okay, so we have a heptane. Next is we look at our branch points. Okay, so we see that on carbon 2 we have a methyl group. So we have 2-methyl. And next on carbon 4 we have this 3-carbon chain, which is an isopropyl group. So we got 4 isopropyl. Okay. Alright, so hopefully you remembered what isopropyl looked like. So finally, we've gone over all the branch points and we could combine all the information we have. Okay, so I goes before M in the alphabet, so we get 4 isopropyl. Oops. Isopropyl 2-methyl heptane. Okay. Alright, so that's for part B. Going for part C, I want to do this on the left side since we're kind of running out of space here. Okay. It looks like this would be our longest chain, right? And this time, I think the branch point is closer from the left side. We can't really confirm that. I think we just have to count from both sides and see. Okay, so we got 1, 2, 3, 4, 5, 6, 7, and if we count from the left side, 1, 2, 3, 4, 5, 6, 7. Okay, so the first branch point is always, looks like either way, you're going to have it on carbon 2 first. But what makes it different is that this carbon has 2 methyl groups in it, right? So it has 2 methyl groups. Let me remove that. And if we count from the left, or sorry, if we count from the right, if we follow the green counting system, we're going to end up having 2 methyl groups on carbon 6, right? But if we count from the left, if we follow our orange counting here, we're going to have our 2 methyl groups on carbon 2. Okay, so remember we still want the least kind of numbers as possible in our naming. So if we follow green, we're going to end up with let me get our highlight here, 2 and then 6, right? But if we do the orange counting, we're going to have 2, 2, and then 6. So having 2, 2, 6 would be better. In fact, that would be the only correct way. Okay, so let's start counting from the left then. Got 1, 2, 3, 4, 5, 6, 7, right? Since we have 7, that means we have a heptane. Okay, and now on carbon 2, as we mentioned, we got 2 methyl groups. Okay, so we got 2 methyl, and I'm just gonna separate them for now. Well, we're gonna combine this later. And we also have that methyl group on carbon 6, so we got 6 methyl. So this is what I'm talking about earlier. If we counted from the right going to the left, we're gonna end up having 2 methyl, 6 methyl, and then another 6 methyl. So if you add these, that's pretty much how I remember it. If you add these, this would be a larger number. It's going to be 14. If we add this is only 10. So we want this. Okay. we want the lower number. All right, so at this point, I think we have everything that we need, so we could combine our information. Okay, so we have all methyls, so this is gonna make a trimethyl, right? So we got 2, 2, 6, trimethyl heptane. Okay, there we go. All right, on to our last problem here. Okay, let's find the longest chain. This looks like it's gonna be our longest chain, right? Okay, so again, we count from left and then count from the right and compare. 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. Okay, so our first branch point, if we count using blue, the first branch point would be on carbon 5. Okay, be on carbon 5. If we count following green, the first branch point would be on carbon 4. So we're following the green counting here. So I'll erase everything and leave the green counting system, I would call it. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, meaning we have octane, right? For 8 octane. Okay, so our first branch point here, in fact, our only branch point, we got two things attached to it. One is a methyl group, so we got 4-methyl. And the other one is an ethyl group, okay? So we got 4-ethyl. Okay, so at this point, we could combine all the information we have. Okay, so we got ethyl and we got methyl, and E comes before M in the alphabet. So we got 4-ethyl, 4-methyl octane. Okay, so alright, so finally we have named all the molecules we have for problem number 50. Alright, moving on to problem 51. Okay, we're still on IUPAC naming, and this time we are naming isooctane. Okay, so we are getting the IUPAC naming for isooctane. This is the common name for it. Okay, so first step is find the longest chain, and I think it's easier with the condensed structure right here to see that this is the longest chain that we have. Okay, so I'm going to number from the left and then from the right, and let's see where we hit our first branch point. We got 1, 2, 3, 3, 4, 5, and then from the right we got 1, 2, 3, 4, and 5. Okay, so it looks like either way we're gonna hit our first branch point on carbon number 2. Okay, but as you see, if we follow the green numbering, if we count from the left, once we hit carbon 2, we have 2 groups attached to it, okay, as compared to when we count from the right side. When we hit our first branch point, we only have 1 group attached to it. So this counting from the left side would be our priority, okay? And I'll explain a little bit more of that as we go. Alright, so we're counting from the right, as I mentioned, and I want to deal with this using our molecular model since it has more space. and it's easier to just write. Okay, so we got 5 carbons in our main chain, which means we have a pentane. Okay, we have a pentane. So on carbon 2 right here, we have 2 CH3 groups. Alright, so that's a methyl group. So we have 2 methyl and another 2 methyl. I'm just going to separate them for now, and we'll combine them later. Okay, and then we have carbon 4 here with another methyl group. So we have 4 methyl. Alright, so at this point, we've gone over all our branch points, and we could combine the information we have. So we have 3 methyls, which gives us trimethyl, okay? And then we're just listing the numbers in order. So we have 2, 2, 4, trimethyl pentane. Okay? If we have counted from the right side and following this orange numbering right here, we're gonna have 2, 4, 4 trimethyl pentane, and as you could see, this would give us a lower total number, so that's why we counted it that way. Okay, but anywho, this is our IUPAC name for isooctane.
Alright, so problem 52, we are writing condensed structures. Okay, so let's just go for it. Part A. Okay, part A says we have 3 ethyl hexane. So hexane means we have 6 carbons in our molecule, right? So 1, 2, 3, 4, 5, 6. Okay, and then 3 ethyl here means we got an ethyl group on our 3rd carbon. So this would be my 3rd carbon, and I'll go ahead and add CH2, CH3. So that's your ethyl group, okay? And all that's left to do here is to add those hydrogens, okay? So our first carbon here on the left could handle 3 more hydrogens, okay? And then the second one could handle CH2. And this 3rd carbon currently has 3 carbons bonded to it, so it can only make 1 more bond with hydrogen, okay? And then this 4th carbon could handle 2 more, as well as this carbon, and the last carbon only has one carbon connected to it, so it could make 3 more bonds with hydrogen atoms. Okay, so that should be part A. Part B. Okay, we got 2,2,3 trimethyl pentane. Okay, pentane. So pentane means we got 5 carbons. So I'll go ahead and write 5 carbons here for 5. Okay, 2,2,3 trimethyl means we got 3 methyl groups, and they're on carbons 2, 2, and 3. So carbon 2 has 2 methyl groups, and carbon 3 has 1. Okay, so I'll go ahead and fill those bonds with methyl groups. Okay, CH3, and another CH3. Okay, so now that we have all our groups connected, all we have to do is fill up the carbons with hydrogens. Okay, so this first carbon would be CH3, right? The second carbon already has 4 carbons connected to it, so it can't handle another bond, so we could leave it alone, right? This 3rd carbon right here has 3 carbons connected to it, so it could handle 1 more hydrogen. Okay, and this 4th carbon could connect or could bond with 2 hydrogens more, and our last carbon can be CH3. Okay, so that's it for our part B. Okay, so just as a reminder for everyone that these spaces are not supposed to be part of our condensed structures. that's just an extra space that was left after my work, but when you write your structures, please make sure you don't have those spaces, okay? So part C, we got 3-ethyl, 3,4-dimethyl heptane, okay? So whenever I try to read these structures, I kind of start ignoring the groups first, and then I focus on the first thing that I need to know, which is how many carbons are there, okay? So now I know there's 7, so I'll go ahead and write 7. 1, 2, 3, 4, 5, 6, 7, okay? Now I got 7. Now I worry about the groups, right? So I got 3-ethyl. So I'll go to the third carbon and add an ethyl group, okay? So I'll put it up here. Ethyl would be CH2, CH3, okay? 2 carbons. And then I have 3,4-dimethyl. So I got 2 methyl groups. One would be on carbon 3 and one would be on carbon 4. So CH3 here and CH3. So 3,4-dimethyl, okay? So now that we have all our alkyl groups connected, we fill those bonds with hydrogen atoms, okay? So what I mean by that is that carbon needs to have four bonds around it, and we fill those bonds with hydrogen if they're missing some, okay? For example, this first carbon here, has 1 carbon connected to it, so that means it needs 3 more bonds, and that's going to be filled up by hydrogen, okay? So the second carbon would be CH2. This third carbon already has 4 carbons connected to it, so it doesn't need any more bonds with hydrogen, okay? Fourth carbon here could handle 1 more hydrogen, okay? These next 2 carbons could handle 2 hydrogens each, and our last carbon here would have 3 hydrogens connected to it, okay? So that should be our structure for part C. And finally, we have structure part D, okay? We got 5-isopropyl 2-methyl octane. So again, as you notice, I just kind of ignored all the groups there and went to the part where it says octane. Okay, so that means I have 8 carbons. So let's go ahead and draw 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then I have an isopropyl group on carbon 5. Okay, so 1, 2, 3, 4, 5. This is carbon 5. And I have an isopropyl group. So hopefully you remember what isopropyl looks like. Okay, so this is what it looks like. It has a carbon that splits and connects to two more methyl groups. Okay, and finally I have the 2-methyl right here, so I'll go to carbon 2 and add a methyl group. Okay, all that's left for us here is to make sure that every carbon is connected to 4 things. If it's not, then fill it up with hydrogen. Okay, so first carbon here needs 3 more bonds, so we're filling that out with 3 hydrogens. Okay, second carbon could handle 1, then we have CH2 for the next 2 carbons. Okay, fifth carbon has 3 things connected to it, 1 on the left, 1 on the right, and 1 below. Okay, so that means it could handle 1 more hydrogen. Then we have CH2 for the next 2, and our last carbon here would have 3 hydrogens connected to it. So there you have it. That's all our structures for this problem. Alright, problem 53. We are drawing structures, and as you would probably notice by now, they're all cyclic structures, okay? And the reason that I have these cyclic structures pre-drawn below is because I'm not very good at drawing polygons, so hopefully you are, but there you have it. I have our cyclic structures pre-drawn, so let's just go for it, right? Starting with part A here. Part A says cyclooctane. Okay, so that just means cyclo meaning you have a ring, and octane that means you have 8 carbons. Okay, so 8 carbons in a ring would give you an octagon, right? So outside of chemical or chemistry context, that's called an octagon. So you're just gonna have to draw an octagon, okay? Which is what I have here in part A. So I have a cyclic structure with 1, 2, 3, 4, 5, 6, 7, 8 carbons in it. Okay, so that's pretty much it for part A. Part B is a little more complicated. We have function groups now attached to it, right? We got 1,1-dimethyl cyclopentane. Okay, so pentane means we have 5 carbons, and cyclo means they are in a ring. Hence this pentagon that I have right here on the right side. Okay, and then we have 1,1-dimethyl. Okay, 1,1-dimethyl means we have 2 methyl groups, and both of them are on carbon 1. Okay, so at this point you're assigning numbers to carbons, and it's arbitrary, right? So you could use any of these carbons as your carbon 1. So I'll just choose this carbon right here. Okay, so I'll choose that, and there are 2 methyl groups attached to this carbon. So I'll go ahead and add those methyl groups. So there you go. That's 1,1-dimethyl cyclopentane. So this is part B. Okay, so moving on to part C here. We got 1, 2, 3, 4 tetramethyl cyclobutane. Okay, cyclo meaning you have a ring, and butane means you have 4 carbons in your ring. So it's kind of like a square, right? So so first is you draw that square or diamond, whatever you want to call it, and which we have right here. And we have 1, 2, 3, 4 tetramethyl. Okay, so that means we have 4 methyl groups, tetramethyl, and they're on carbons 1, 2, 3, and 4. Okay, so each carbon here is gonna have a methyl group. So for this example, doesn't matter how you count it because they're all gonna have the same methyl group, right? So you can choose which of these carbons would be your carbon 1, which would be 2, 3, and 4. In this case, it doesn't matter. Okay, so there you go. We have 1, 2, 3, 4 tetramethyl cyclobutane. So that is part C. Finally, here we have part D, and we got 4-ethyl 1,1-dimethyl cyclohexane. Okay, so whenever we are drawing structures, I think it's very important to start with the base structure, which is cyclohexane here. So as you noticed, I kind of just skipped over all the groups, all the function groups, and I'll just pay attention to those later. So this is part D. So we have a cyclohexane, which is outside of chemistry concept, that would be called a hexagon. Okay, so you got six carbons in one ring, cyclohexane, and then we got 4-ethyl 1,1-dimethyl. So I want to go ahead and just number my carbons here, and again, doesn't matter which one is carbon 1, so I'll just choose that to be carbon 1, 4, 5, 6. Okay, so now that they're numbered, I can go ahead and put my groups. I have 4-ethyl, so I'll go to carbon 4 here and add an ethyl group. So I'll have CH2, CH3. Okay, so that's ethyl. And I have 1,1-dimethyl, meaning I have 2 methyl groups, and both of them are on carbon 1. So this is methyl group and another methyl group. So there you have it. Those are all our structures for problem 53. Alright, problem 54 is asking us about aromatic compounds, and why is it that when a compound is aromatic, why is it that it doesn't necessarily mean that it smells nice? Okay, so why is that the case? Well, that's because the term aromatic refers to a class of compounds that is made of a 6-membered ring that has 3 double bonds. Okay, so this is what the term aromatic means. It does not mean it has anything to do with the smell. Okay, so it is made for these types of compounds. Okay, so hopefully that clarified that term.
An addition reaction is an organic reaction in which the reagent adds to the multiple bond of the unsaturated reactant to yield a saturated product.
Okay, problem 56. We are writing structural formulas for these molecules that they described for us. Okay, so there's a lot of different answers for these kind of problems, so I'm going to come up with one, but if it's not the same as the one you came with 5 carbons. Okay, so that's exactly what I'm gonna do here for part A. I will write my 5 carbons. Okay, 1, 2, 3, 4, 5. Okay, and I want a double bond somewhere, and I don't know, I just want to put it here on the very first carbon. Okay, so now that we have that, I actually need to rewrite that. Now that we have this double bond on the first carbon, right, we could fill up the rest of the bonds with hydrogens. Okay, so this bond would have CH2, right, could handle 4 bonds, and the same, oh, not actually not the same, the second carbon could only handle 1 hydrogen because it has 3 bonds before that. Okay, so then we have CH2, CH2, and CH3. Okay, so that's the structure that I came up with for part B, and again, that double bond could be anywhere else in this structure, so that's just where I wanted to put it. Part B. Okay, part B. We got an alkyne with 4 carbons, so I want to start with having 4 carbons, right? 1, 2, 3, 4. Okay, so I have 4 carbons, and we have an alkyne. Meaning we have 3 bonds, or a triple bond. We have a triple bond somewhere, and I'm just deciding to put that again on the first carbon. Okay, so now that we have that triple bond, let's go ahead and fill it out with hydrogens, right? This first carbon can handle 1 more hydrogen, plus those 3 bonds gives it a total of 4 bonds. This second carbon is saturated with 4 bonds, so we could leave it alone. So I'll just write the next carbon right next to it, right? And then we have this carbon, which could handle 2 more hydrogens, and finally we have CH3 at the end. Okay, so that's what I came up with part B. Again, if yours is if yours doesn't look like this, it doesn't mean it's wrong. Okay, so there should be isomers that are possible for this molecule. Okay. Part C. Part C, we got a substituted aromatic compound with 8 carbons. Okay, so, well, I know one very, very common aromatic compound, right? I have benzene, right? So what I want to do here is just to draw that benzene. Okay, draw that benzene. Okay, so it says that we need 8 carbons total, and benzene has 6, right? Benzene has 6 carbons. So we need 8 total. So 8 minus 6, meaning we need 2 more. 2 more carbons in this molecule. And it also says substituted aromatic compound, meaning it does have alkyl or functional groups that come with it. So I need 2 more carbons, and well, I'll just add 1 ethyl group, right? Ethyl group has 2 carbons. So CH2, CH3. So there you go. Is my aromatic compound substituted? Yes, it does have this alkyl group. Okay, does it have 8 carbons total? Yes. I have 6 from the aromatic ring, and then I have 2 from the ethyl group. So it satisfies all the requirements for part C. Again, all of these structures are just what I came up with. They do have isomers that are also correct. Okay.
There are 3 dienes with the formula C3H8, and these are, so diene is a compound with 2 double bonds. CH3, so 1, CH3, CH, double bond CH, CH, double bond CH2. So there's, sorry, this is C5H8, not C3H8. Let's fix that. C5H8, dienes with C5H8. Second diene will be CH2, double bond CH, CH2, CH, double bond CH2. So there's the second diene. And the third diene is going to be CH2, double bond CH, C, double bond CH2, and a methyl substituent here. So those would be the 3 dienes that can be formed from C5H8.
Problem 58, we're still on IUPAC naming. Okay, so let's go and start with part A. As usual, let's go and find the longest chain we could find, and I think for this one it's pretty obvious. All right, and here we have a double bond, right? And the rule is whenever we have a double bond or a triple bond, we count from the side where we're closer to that bond. Okay, so what I mean by that is this double bond right here looks like it's closer to the right side. And I mean, you don't really have to estimate. You could check, but I think it's clear to see that there's only 2 carbons on the right side of the bond and there's 3 on the left. So it's closer to the right side. So we count starting on the right side. So let's go and count. We got 1, 2, 3, 4, 5 on our main chain, okay? So let me give a space for part A down here. Okay, so we got 5, meaning we have a pentene, right? So pent for 5 and pentene because we have a double bond, okay? And that double bond starts on carbon 2, right? Starts on carbon 2. So this would actually be 2-pentene, okay? Just kind of ran out of space there. But, okay, so we have 2-pentene. Next is we check our branch points. And we see here on carbon 4 that we have a methyl group branching out. So we have a 4-methyl, okay? So now that we have all the information we need, we could combine all of it and come up with our answer. Okay, so we have only one group that we need to take care of. So we got 4-methyl, 2-pentene. Okay, so that should be our answer for part A. Let's go to part B now. Okay, so part B. Alright, so again, as usual, let's find the longest chain, and this looks like our longest chain right here, right? We got 2 carbons up here compared to just 1 if we go along a straight line, okay? And again, we count from where our double bond is closer, and for this one, it's pretty obvious that it's on the right side. Okay, in fact, it's at the end of the right side here, okay? So we're counting from the right side here, 1, 2, 3, 4, 5, okay? So just like part A, we got pentene, but this time our double bond starts on carbon 1, right? So we have 1 pentene, because there's 5 carbons, and pentene, E because we have a double bond, okay? So next is we take care of our branch points, and for this one, we actually only have 1. We have a methyl group connected to carbon 3, okay? So we have, let me use a different color pen here, okay? We have 3-methyl, okay? So I think that's all the information we need, and we could proceed to combining all these information. Okay, so we have 3-methyl. We name our branching group first. So 3-methyl, 1-pentene. And that's our answer for part B. Okay, so part C now. We have a benzene ring, and connected to our benzene ring are 2 chlorine atoms. Okay, so we gotta count 1 on the carbon where our functional group is, or our atom is, so this would be 1, and we gotta count 2 on the closest branching group as well, so this has to be 2. Okay, because if we count 2 here, then this chlorine would be carbon 6, and we don't want that, so this chlorine would be on carbon 2. Okay, so we have dichloro, right? So we have 1, 2, 1, 2, since that's where we have our chlorine atoms, and we got dichloro for having 2 chlorine atoms, right? Dichlorobenzene. Okay, alternatively, the way that they are positioned, since they are next to each other, we could also name that ortho. Okay, so we write O for ortho. O dichlorobenzene. Okay, So there's two possible IUPAC names for part C. Alright, moving on to part D. Part D, as usual, let's find the longest chain. And I think for this one, it looks like it doesn't matter, right? So even if you get this methyl or this methyl, it's going to be the same length since it's just one methyl for both choices. Okay, so let's just take the straight chain. I think it's simpler. And let's count and see where we hit our double bond first. Okay, so if you count from the left, we got 1, 2, 3, 4. And if we count from the right, we have 1, 2, 3, 4. Okay, so either way, looks like either way, I know it's kind of getting messy here, but either way, our double bond is gonna hit carbon 2 first. Okay, but if we count from the right and follow the green numbering, once we hit carbon 2, not only do we hit our double bond, we also hit this branch point right here. Okay, so kind of shooting two birds in one stone right there. So we are gonna count from the right on this one. So let's count from the right. We got 1, 2, 3, 4, and since we have 4, that's a butene because of the double bond, and it starts on carbon 2, right? Double bond starts on carbon number 2, and that gives us 2 butene. Okay, and I didn't write that well, but you get what I mean. That's 2 butene, and we have this methyl group sticking out from carbon 2 as well, so we have a 2 methyl. So combining all those information, we have 2 methyl, 2 methyl, 2 butene. Okay, and that would be our answer for part D. Alright, finally we are on part E here. Okay, and again, find the longest chain, and it looks like it's pretty obvious. This whole thing here is our longest chain. So again, we are counting from where our triple bond is closest. Okay, so this applies to both double and triple bonds. So it's closer to the left, so we're counting from the left first. 1, 2, 3, 4, 5. Let me rewrite that. 5, 6, 7, and 8. So we get 8. And our triple bond starts on carbon 3. So we got 3 oct. Rewrite that. Got oct for 8 and YNE because of the triple bond. So we got a 3 octane. Okay? And last thing that we need to do here is to account for our methyl group sticking out from carbon 7. Okay? So we got a 7 methyl group. Okay? Alright, so time to combine all the information that we have. We got 7 methyl, 3 octane. Okay, so that's our answer for part E. And finally, we're done here. We have named all the molecules we have for problem 58. Okay, so we're drawing structures for problem 59. So let's just go for it, starting with part A. We got cis-2-hexene. So hexene meaning we have 6 carbons, and 2 and ENE means we have our double bond on carbon 2. Okay, so I actually want to start drawing this with 2 having the double bond with carbon 3, right? and it says cis, meaning our hydrogens would be on the same side, or our carbons connected to carbons 3 and 4, or 2 and 3, sorry. This would be carbon 2, and this would be carbon 3. Okay, so cis, meaning our carbons connected to it would be on the same side, as well as our hydrogens, right? So if this is carbon 2, meaning we're going to have carbon 1 connected to it, okay? So this is carbon 1. And then we're going to have that carbon 4 connected to it as well, okay? So that's what we mean by cis. They're going to be on the same side, and the same is true for the hydrogens, okay? So this carbon is going to have hydrogen, this is going to have a hydrogen, and they're going to be on the same side, okay? So carbon 1 would have 3 hydrogens connected to it, that because we've pretty much gone over the important part on this molecule. So everything that we're going to do here is just filling up those carbons and hydrogens that we have left, okay? Alright, so we got carbon 4, and this is most likely going to be CH2, right? And then we got carbon 5, and finally we have carbon 6, which will be a CH3, okay? So there we go, that's our cis-2-hexene. Moving on to part B. We got 2-methyl-3-hexene, okay? So as usual, we got a 6-carbon molecule with a double bond on the third carbon. So again, I want to draw that starting with carbon 3, right? Starting with carbon 3, then we have it double bonded to carbon 4. So this is carbon 3, this is carbon 4, and it doesn't tell us about it being cis or trans, so we don't really have to show it, just like how we showed part A. So as long as we know that carbon 3 would be a CH, right, and carbon 4 would also be a CH, okay, and that would be connected to CH2 being carbon 2 and a CH3 for carbon 1, okay? So this is carbon 1, carbon 2, 3, 4, and then actually we'll edit that a little bit later, but let's go forward with carbon 5 and 6 for now. So we'll have, don't need that bond, we'll have CH2 for carbon 5 and CH3 for carbon 6, okay? So we got 5, 6, and now we take care of that 2-methyl right there. So on carbon 2, we have a methyl group sticking out. So let me erase this number 2 right here. And we have a methyl group sticking out, which means we're going to have to reduce the number of hydrogens that we have, okay? So instead of CH2, we're only going to have CH, okay? So that should be our structure for part B. So next, and finally, we got part C, right? We got 2-methyl-1,3-butadiene, okay? So that's a pretty long name. This but tells us we have 4 carbons, right? So I want to go ahead and write 4 carbons here. We got 1, 2, 3, 4, okay? 1, 3 tells us we have the double bonds on carbon 1 and then another one on carbon 3, okay? So we have 2 double bonds on this molecule. That's also why we have this diene in our naming. So carbon 1 would have a double bond with carbon 2, and then carbon 3 is going to have a double bond with carbon 4, okay? Alright, now that we got that, all we have to do is take care of the 2-methyl group. Okay, so carbon 2 would have a methyl group with it. And after that, we could go ahead and fill out the missing hydrogens. Okay, so the first carbon would have 2 hydrogens. Okay, and carbon number 2 here already has 4 bonds, so it's good to go. Our carbon 3 is missing a hydrogen to make it 4 bonds, and this last carbon here needs 2 hydrogens. Okay, so that should be our answer for part C. All right, so finally we have the structures for all our molecules here. All right, so for problem 33, we have this molecular model, and we're asked to provide a condensed structure. Okay, so before we start, I want to remind everyone with what the specific spheres mean. So whenever we see a black sphere, that represents a carbon atom. Whenever we see a white sphere, that represents a hydrogen atom. And the red sphere represents oxygen. Okay. And also I want to go ahead and number our carbons. That makes it easier for us to talk about it, right? So let's go ahead and count carbons. 1, 2, 3, 4, 5, 6, and I'll call this carbon down here 7. Okay. So let's go for it and start. So carbon 1, we see that it has 2 hydrogens attached to it, right? There's 2 white spheres. So let's go ahead and write CH2. And we see that it is double bonded to carbon 2. So let's go represent that double bond. And then carbon 2 doesn't really have any hydrogens attached to it. So we're writing just C for now. Okay. So it is connected to carbon 3 with 2 hydrogen atoms right here. So let's write CH2. Right. I'll just go ahead and rewrite. I feel like I'm not writing it well. So CH2. Okay. And then we also see that carbon 2 is connected to carbon 7. Right? This is carbon 2. Oops. This is carbon 2 right here, and it is connected to carbon 7. And carbon 7 has 3 hydrogens in it. 1, 2, 3, right? So we'll have a bond here on carbon 2, and we'll have a CH3 attached to it. So this CH3 would be our carbon 7. Okay, excuse me. Proceeding to carbon 4. Carbon 4 also has 2 hydrogen atoms, so we're writing CH2. Carbon 5 has 1 hydrogen atom attached to it, right? So for now we're just writing CH, just 1 hydrogen atom. And then it has this functional group connected to it, and as mentioned, this red sphere is an O and this white sphere is an H. So we have an alcohol group coming out of it. So let's go ahead and add that to our structure. So I'll just put it down here, and it is connected to an OH, right? Doesn't really matter if you put it below the C or above. At least for condensed structures, it doesn't really matter. And finally, we have carbon number 6. Carbon number 6 here has 1, 2, 3 hydrogen atoms. So we have CH3 at the end of our structure. And we're pretty much done here. This is the condensed structure of the given molecular model. Okay, so problem 6. We have 3 molecules here, and we're asked which of these is capable of cis-trans isomerism. Okay, so we got 1 hexene, 2 hexene, and 3 hexene. and I do have those molecules pre-drawn in here just so we could talk about it easier, okay? So, starting with 1-hexene, we have this double bond between carbon 1 and 2, hence the name 1-hexene. And the way that this structure is drawn, it doesn't show you the hydrogens, right? So I want to go ahead and draw that just so it's easier for us to see. And before I draw the hydrogens, I want to remind that there's a carbon in here and a carbon right there. Okay, so go ahead and draw the hydrogens. Okay, so there's 2 hydrogens in there, and then that carbon is double bonded to carbon 2. Okay, so carbon 2 has 1 hydrogen, right? So it could only handle 1 more hydrogen. So now we can analyze this molecule if it's capable of cis-trans isomerism. And as you can see, carbon 1 is connected to 2 hydrogens. It's connected to 2 hydrogens, and carbon 2 is connected to 1 carbon. Okay, so 1-hexene is not capable of cis-trans isomerism because there is no carbon connected to carbon 1 here. Okay, so the answer for A is no, it's not capable of cis-trans isomerism. Okay, so proceeding to 2-hexene here. Okay, again, I want to go ahead and draw those hydrogens along the double bond. Right, so we got 1 hydrogen here on carbon 2, and we have 1 hydrogen here on carbon 3. Okay, and then as you can see, you have carbon 4 right here and carbon 1 right here, and they are on opposite sides of the double bond. Okay, right there on opposite side. This one's, if you could think about it, this carbon 4 is kind of going up the double bond, and carbon 1 is kind of going down. Now, is there another way to draw this? Well, I think there is, right? We could draw one of this carbon 1 right here going up like that, right? So, and this is what that is gonna look like. Okay, so if we draw carbon 1 going up, this is what it's gonna look like. Okay, so in this molecule, both the carbons connected to carbon 2 and 3, so we got 1 and 4. Carbons 1 and 4 are on the same side of the double bond, right? They're kind of on the same side. They're both going up. So this would be your cis for same side, okay? Cis isomer and trans isomer. Sorry about that. Okay. So, well then, yes, 2-hexene is capable of cis-trans isomerism. There's 2 ways to draw those bonds around the double bond, okay? Next is 3-hexene right here. So we have carbon 3 and 4, hence the name 3-hexene, okay? And as you can see, carbon 2 right here is kind of going up the double bond if you think about it, and carbon 5 is going down, okay? So since they're going on opposite directions, that can be our trans isomer. Now, this can only be trans isomer if we could prove that we can draw this any other way, okay? And the other way that we could try to draw is to draw these carbons going on the same direction, and this is what it's going to look like, okay? So here, we still have that carbon 3 and 4, and they're double bonded to each other. And then we have 2 and 5 right here, both going on the same direction, okay? So they're on the same direction, so that would be our cis isomer, okay? So, as you can see, we only have 2-hexene and 3-hexene that's capable of cis-trans isomerism. Therefore, our answer would be B, and C. Okay, so I need to box that, I think. So B and C are capable of cis-trans isomerism.
So we're asked which of the following can exist as cis-trans isomers. A can exist as cis-trans isomers. So the cis configuration for A will be with the two hydrogens on the same side, CH3, and this would be CH, CH3, and H3C. So there's the cis configuration for A. The trans configuration for A will be this configuration here where the hydrogens are opposite, and we will get this configuration here for the trans. So A can exist as cis-trans isomers. B cannot exhibit cis-trans isomerism. So there cannot be, so as the CH2 group on the right end has two hydrogens attached, so we can't have different groups there. C does exhibit cis-trans isomerism. So for C, the cis isomer will be this configuration here. There's chlorine there, and then the trans isomer we can draw as this isomer here. And so this one does exhibit cis-trans isomerism. So A and C are able to show cis-trans isomerism, while B for A, let's write the reaction of 2,3-dimethyl-2-butene. So 2,3-dimethyl-2-butene. And it's going to be reacted with H2 in the presence of a palladium catalyst, and this would yield CH3 CCCH3, and we would get CH3 CH3 H and H. For B, again 2,3-dimethyl-2-butene. And this would be reacting with bromine, Br2, and this would yield CH3CCCH3, and this would be H, oh no, not H and H, these would be Br, CH3, and CH3. And for C, 2,3-dimethyl-2-butene. And this is going to react with H2O with a H2SO4 catalyst, so the presence of acid, and this would yield CH3C CCH3. This would be CH3, CH3, OH, and H. So there are our completed reactions. Let's complete the following reactions of paradichlorobenzene. For A, we have a halogenation, so paradichlorobenzene is going to react with bromine in the presence of FeBr 3, and this will yield the bromine group being attached here. So there's the halogenation. For 2, we're going to show a reaction of paradichlorobenzene with HNO3. We're using H2SO4 as our catalyst, and this is a nitration, so this will yield this molecule here, Cl, Cl, and NO2. And for C, we have paradichlorobenzene, and it's going to react with Cl2 in the presence of FeCl3 as a catalyst. This is another halogenation, which will yield Cl, Cl, and Cl.
Okay, so problem 64, we are drawing structures. Okay, so let's go for it, starting with part A. Part A here we have 2,4-dimethyl-2-pentanol. Okay, so we have that pent right there, meaning we have 5 carbons. So I want to start with drawing 5 carbons here. 1, 2, 3, 4, 5. Okay, and then next we got this suffix "ol", meaning we have an alcohol, and that alcohol group is on carbon 2. Okay, hence 2-pentanol. So let's go ahead and put that alcohol group on carbon 2, right? So there you go. Next, we got 2,4-dimethyl. Okay, we got 2,4-dimethyl, meaning we have methyl groups on carbon 2 right here, and carbon 4. Okay, now this methyl group could be below carbon 4, but I just chose to put it above it. Okay, so now we have all our functional groups, and all that's left for us to do is fill it out with hydrogens. Okay, so carbon 1 here is only connected to carbon 2, so it can handle 3 more hydrogens, so it's going to be ACH3. Okay, carbon 2 already has 4 things connected to it. It has this carbon, and then carbon 3, and then 2 more groups right here. Okay, so it can't handle any more hydrogens. Carbon 3 right here has 2 other carbons connected to it, so it can handle 2 more hydrogens, right? And then carbon 4 has 3 things connected to it, so it can handle 1 more. Okay, it can handle 1 more hydrogen. And then finally our carbon number 5 here could handle 3 more. Okay, so really the key here is to make sure every carbon is connected to 4 things. If not, then fill it out with hydrogen. Okay, so moving on to part B. part B, we got 2,2-dimethyl cyclohexanol. Okay, so that cyclohexanol means we have this 6-membered ring right here, and we're gonna use that. Okay, so cyclohexanol meaning we have the cyclohexene, and then it has an alcohol group. Okay, so let's go ahead and add that alcohol group. Just want to add this here on top. Okay, so whenever you have a cyclohexanol or whatever functional group your ring has, that carbon would be your carbon number 1. Okay, that will always be your carbon number 1. So let's go ahead and count our carbons here. 1, 2, 3, 4, 5, 6. Okay, and then next we got 2,2-dimethyl. Okay, so meaning we have 2 methyl groups on carbon 2, right? So this would be our carbon 2, and we just have 2 CH3 groups in there. Okay, CH3, CH3. Okay, and that's pretty much it for part B. Okay, again, the key here is setting this carbon as carbon 1. Okay, next is part C. Okay, part C, we got 5,5-diethyl 1-heptanol. Okay, heptanol right here tells us that we have 7 carbons. So let's go ahead and start with 7 carbons. 1, 2, 3, 4, 5, 6, 7. Okay, and then we got 1 heptanol, meaning we got the alcohol group on carbon 1. So let's go ahead and add that. And finally we got 5,5-diethyl. So diethyl meaning we have 2 ethyl groups and they're both on carbon 5. So this is carbon 5 right here, and we are going to have 2 ethyl groups. So CH2, CH3. That's 1 ethyl group, and then another one up here. Okay, so now we have all the groups that we need. All that's left is to fill out with hydrogens. Okay, carbon 1 has 2 things connected to it right now. It has the alcohol group and this carbon, right? So let's go ahead and fill it out with 2 more hydrogens. Okay, carbon 2 can be CH2. Same is true for carbon 3. Carbon 4 as well. Okay, so for carbon 5, it doesn't really have any more spots. It's currently connected to 4 things already, so we'll leave it alone. We got CH2 for carbon 6, and finally carbon 7 could handle 3 more hydrogens. Okay, so obviously we have the space here. That's just extra space. If you rewrite your molecule, you're not supposed to have any space there, but that's what we have for part C. Finally, we got part D, right? We got 3-ethyl 3-hexanol. Okay, so we got 6 carbons from hex right here. So I'm gonna go and draw 6 carbons here. 1, 2, 3, 4, 5, 6, and it says 3-hexanol. So carbon 3 has an alcohol group, right? And we got 3-ethyl. Okay, let me change the color for that. Let's use pink. So 3-ethyl, meaning carbon 3 also has an ethyl group. So CH2, CH3. Okay, so that's pretty much it for part D. All that's left for us to do is fill out with hydrogens. Okay, so first carbon would have 3 hydrogens. Got CH2 in here. Carbon 3 has 4 things connected to it right now. Okay, got 1, 2, and then it's connected to this carbon and that carbon as well, so we can leave it alone. Okay, and then we got carbon 4, can handle 2 more hydrogens, carbon 5 as well, And finally, carbon 6 right here would have 3 hydrogens, okay? Then again, as I've mentioned, we don't really have this space right here. That's just extra space from that we have, okay? So when you rewrite this molecule, it's not supposed to have that space right there. But that's all our structures. Okay, so problem 65, we're still drawing structures here and we're dealing with amines, okay? So I'm starting with part A. We got propylamine, okay? Propylamine, and the way I want to start doing this is to start with the amine backbone, okay? So what I mean by that is we just have this basic structure of an amine. So we have a nitrogen with 3 bonds to it. And part A says we have a propyl group attached to this amine. So propyl meaning we just have 3 carbons, right? We got CH2, CH2, CH3, okay? So that's our propyl group. And of course, we got 2 more bonds here which would be connected to hydrogens, okay? So that should be propylamine for us. Moving on for part B here, we have diethylamine, okay? So I realize I have this cyclohexane in the wrong spot here. Okay, so part B, we got diethylamine. So again, I want to start with kind of the basic structure for an amine, right? So just a nitrogen connected to 3 things. So it says diethyl, meaning we have 2 ethyl groups attached to nitrogen, okay? So we have one ethyl group right here, CH2, CH3, and another one right here. So it doesn't really matter where you put it, right? And of course, that last bond would be connected to hydrogen, okay? So that should be our diethylamine. Part C is a cyclohexylamine, okay? Cyclohexylamine, okay? So that's why I have this cyclohexane right here, and it's going to be connected to one of the bonds with nitrogen, okay? So since I already have this cyclohexane right here, I just want to connect that to nitrogen, right? And of course, nitrogen is going to have 2 more bonds, and those bonds would be filled up with hydrogen, okay? So that should be cyclohexylamine for us, and I think we all have our structures here. Problem 66 is asking for us to compare aldehyde versus ketone. Okay, so before we start comparing, I want to go ahead and draw what we have. So an aldehyde would be a carbon connected to an oxygen via a double bond and a hydrogen, and it's going to be connected to another carbon right here. Okay, so this could be anything. So that would be aldehyde. Okay, ketone would have a carbon and then another carbon and another carbon, and this middle carbon would be double bonded to oxygen. Okay, and this carbons at the end could be connected to anything. Okay, so that should be our ketone. So I think the difference is pretty clear here. Okay, for it to be a ketone, it has to be somewhere in the middle of the molecule, right? So it has to be in the middle of 2 carbons, hence it will be somewhere in the middle of your molecule, okay? And for aldehyde, for it to be an aldehyde, it kind of has to be at the end, right? Because this is hydrogen right here, and it's not going to be connected to anything else. So for it to be an aldehyde, it has to be a terminal group, okay? So I guess the biggest difference between aldehyde and ketone is that aldehyde would be a terminal group, meaning it's always at the end, and ketone would always be in the middle, okay?
carboxylic acids, esters, and amides all undergo carbonyl group substitution reactions.
Problem 68, we are identifying the carbonyl groups on all of these structures that are given. Okay, so starting with part A, I think part A is pretty clear right here. Okay, so what we just have a ketone right here. All right, so part A would just be a ketone. Okay, part B right here may be a little bit tricky. First of all, it's terminal, meaning it's connected to the very end carbon. Okay, so we have two choices here. It could either be an alcohol, or an aldehyde. Okay, and so the safest way here is to just count how many things are attached to carbon. Okay, so we got one. This is attached to our carbon, and then we have one hydrogen, right? So it has two things attached to it. So that oxygen has to be double bonded to carbon in order to fill those four bonds to carbon, right? So that means since we have a double bond, that means we have an aldehyde. Okay, and another easier way or faster way to identify if it's an alcohol or an aldehyde is that an alcohol would always be written as OH, right? And aldehyde would always be HO, okay, or CHO. Okay, so if it's OH, it's definitely alcohol. If it's written as CHO, then it's aldehyde. Okay, part C. So here's our oxygen right here. And again, this question stem already tells us we have a carbonyl group, but if it doesn't tell you that, this oxygen could either be an ether, or because it's somewhere in the middle of the molecule, it could be a ketone. Okay. So as discussed in a previous problem, if a carbonyl group is somewhere in the middle of a molecule, then it is a ketone. So part C here would be a ketone, okay? Since we know it is a carbonyl group. If you want to make sure it's not an ether, then you can go ahead and count the bonds connected to carbon, and you'll see that it needs to be double bonded to oxygen. Okay. Part D. Part D is right here. And I think it's pretty clear. We know that this is a carbonyl group, right? So it's going to be a C double bonded to oxygen. And we have that nitrogen in there. So that makes this group our amide. Okay. Okay, on to our last part, part D. We got two oxygens, okay? So we really only know two functional groups with two oxygens in it. One would be a carboxylic acid. That's a hydrogen. We rewrite it. Carboxylic acid, or an ester, right? The only difference would be either you have a hydrogen connected to your oxygen or another carbon, okay? In this case, as we see, we have this carbon connected to our oxygen, right? Meaning our functional group here would be ester, okay?
For A, we are to draw 3 amides with the formula C5H10NO. So one amide could be CH3, CH2, CH2, CH2C double bond ONH2. So there's one possibility. Second amide is CH3, CH2, CH2C double bond O, NH, and the CH3 group here. And a third amide could be CH3, CH2C double bond O, and CH3, CH3. So there's 3 amides with the formula C5H10NO. And for B, we're going to draw 3 esters, and these esters are going to have the formula C6H12O2. So one ester is going to be CH3, CH2, 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 C double bond O, OCH3. So there's one possibility. A second ester can be CH3, CH2, CH2C double bond O, OCH2, CH3, and a third ester can be CH3, CH2C double bond O, OCH2, CH2, CH3. So there are 3 esters with the formula C6H12O2.
Alright, so problem number 34 is asking us to identify the functional groups that we have in the given molecular models. Okay, so let's start with part A here. And as usual, I just want to go and go over every single carbon in the molecule and see if they're connected to any functional groups. So starting with this carbon, this first carbon here, this is just CH3, so I'm not as interested, but we see that it's connected to an oxygen atom, right? So this whole part right here is our ether, right? And moving on with this carbon, sorry, let me box that again. Okay, so moving on with this carbon, it's only connected to the other carbons and hydrogen, so I'm not as interested. Moving on with this carbon, that should be the same thing. But this next carbon right here, you see that it is connected with an oxygen atom, right? So this red sphere is an oxygen. So that represents our ketone, right? That represents our ketone, okay? And then moving on to the next carbon, we see that it is double bonded to the carbon next to it. So that would be our alkene. Okay? And they're both just connected to hydrogen atoms, so no other functional groups there. And moving on to our last carbon here, this last carbon, we see that it's only connected to hydrogen atoms, so there's no functional groups there either. So that's it for part A. We got 3 functional groups. We have an ether, a ketone, and an alkene. So part B now, again, just going through the carbons one by one. So starting with this carbon, right, we see that it has 3 hydrogen atoms, so no functional groups there. Moving on to this next carbon right here, we see that it is double bonded to a carbon, so that would be our alkene. Okay, next, moving on to this carbon, only connected to hydrogen, so no functional groups. Next would be this carbon, and we see that it is connected to this structure right here, and this blue sphere represents a nitrogen. Okay, so now we got a nitrogen connected to two hydrogens, NH2, so this makes it our amine group. Amine. Okay, last carbon here. Okay, last carbon, we see that it's connected. It is connected to two oxygen atoms, right? So this whole part right here is our carboxylic acid. Okay, carboxylic acid. So those oxygens, those red spheres are oxygens, and there's this hydrogen atom right here. So that's a carboxylic acid. And at this point, we've gone over every single carbon in this molecular model for part B. So we ended up with three functional groups. We have an alkene, an amine, and a carboxylic acid. All right, problem 70. So we're still on drawing structures, and as you probably noticed, all our molecules here has a suffix of O8, or I guess not for part C, but O8 means we're dealing with esters, right? Okay, so let's go ahead and start. Part A, we got methyl pentanoate, so pent, meaning we have 5 carbons. So I'm going to go ahead and draw 5 carbons first. 1, 2, 3, 4, 5. And we have that O8, right? Got that O8, so meaning we have an ester going on here. So we're putting our ester here as carbon 1. Okay, so whenever you have an ester, the carbon connected to your oxygens would always be carbon number 1. So our countings would be like so. Okay, and we got methyl right here. So for esters, whenever we have a alkyl group connected, we always connect that to our terminal oxygen right here. So this is where our methyl would be. Okay, so all that's left for us to do here is to fill out those missing hydrogens, right? So carbon 5 is at the end, so it could handle 3 hydrogens. Okay, and carbon 4 would be CH2, same for carbon 3, and finally for carbon 2 as well. So we got all our hydrogens now, and you could go ahead and confirm by counting how many bonds you have on carbons, but I'll leave it right there. Okay, so part B, we got butanoate, meaning we have 4 carbons. So I'll go ahead and write 4, right? 1, 2, 3, 4. Okay, and O8, got this O8 again. So we have an ester. Okay, so we're gonna have something connected to that oxygen right there. Okay, so we have 2-methyl. Okay, 2-methyl. Let me use a different color. We got 2-methyl butanoate. So again, whenever you have an ester, the carbon connected to oxygens would be carbon number 1, and let's proceed counting to carbon 4. So we got 2-methyl, meaning we have a methyl group on carbon 2. Okay, so CH3 right there. Okay, and finally we have isopropyl. So meaning our oxygen right here is going to be connected to an isopropyl group. Okay. So isopropyl is just one of those structures that you need to memorize. So that is what an isopropyl group looks like. Alright, so all that's left for us to do is fill it out with hydrogens, okay? So this would be CH3, CH2, oops, CH2. Carbon 2 here has one alkyl group connected to it, so meaning it can only handle one more hydrogen, okay? And carbon 1 already has all those 4 bonds filled out, so that would be our part B, okay? So I'll go ahead and let me write those parts just to make it clearer, okay? Finally, we got part C, okay? We got cyclohexyl acetate. So let's start with the acetate, okay? So an acetate is pretty much a kind of a nickname, sort of, for your ester with one more carbon connected to it. So what I mean by that is we have CH3 and then we have our ester. So that's it. That's all we have for an acetate. So whenever you have an acetate on your molecule name, this would be the kind of the base structure for it, okay? So that's your acetate, and we're told that it has a cyclohexyl group connected to it, okay? So as usual, that alkyl group would be connected to our oxygen, and I do have our cyclohexyl group right here that is ready to be connected, just right there, okay? So that's it. That is cyclohexyl acetate. Problem 71, we are still drawing structures, and this time we have amides. Okay, we're dealing with amides. So part A, we got 3-methyl pentanamide. So I want to start by drawing just 5 carbons for pent, right? So we got 1, 2, 3, 4, 5, and we have that amide, and I want to put that amide right here. Okay, so it's always going to be terminal, but as usual, just like in esters, this would be your carbon 1. Okay, 2, 3, 4, and 5. All right, and we're told that we have a methyl group on carbon 3. So let's go ahead and add that methyl group on carbon 3. Okay, and at this point, we have all of our branch points or alkyl groups connected. All that's left for us to do is fill this out with the missing hydrogens. Okay, so carbon 5 would have 3 hydrogens. Then we have CH2. Carbon 3 has 1 group connected to it, right? We have this methyl group, meaning it can only handle 1 more hydrogen. And then we got CH2 for carbon 2. And carbon 1 is already saturated. And then we have NH2 for our amide, okay? So that's for part A. Part B, we got phenyl acetamide, okay? So I want to remind everyone about acetate, okay? So whenever you see that acet, kind of like aceta, which is from acetate, so we could go ahead and draw an acetate molecule. So we got CH3, right? And we have an ester, okay? But because we have acetamide right here, this oxygen is going to be changed to a nitrogen, okay? So that would be acetamide. And then we have a phenyl group, okay? So unlike unlike esters where alkyl groups are usually connected to the oxygen, here it's never connected to the nitrogen unless specified, okay? So the naming is going to be different if it is connected to nitrogen. So that phenyl group would be connected to this carbon 2 right here. So I'll go ahead and draw a 6-membered ring, okay? So there we go, that's our benzene ring right there. So we got phenylacetamide, and if you notice, since we added this bond right here, we have to reduce the number of hydrogens we have, okay? So this carbon now could only handle 2 hydrogens. And as usual, this N right here could handle 2 more hydrogens. So there you have it, that's our phenylacetamide.
Hi everyone. Functional groups present in Novocaine are okay, are first one is ester that is C double bond O O. Then second one is amine. Of course, amine again. One is NH2, that is primary amine. The next one is tertiary amine. Then next functional group is aromatic ring. So the structure of alcohol and carboxylic acid used for synthesis of this, that is, this is NH2 C double bond O O C2H5, that is ethyl 4-aminobenzoate. Ethyl 4-aminobenzoate obtained from 4-aminobenzoic acid, plus another one is HOCH2 N C2H5. This is diethyl aminoethanol. Diethyl aminoethanol. Whenever they are treated with sodium ethoxide, C2H5O minus Na plus, you can say. So they gives Novocaine. NH2, then C double bond OO, CH2 CH2, N, C2H5, C2H5 plus C2H5OH. So this is Novocaine. It is also called Procaine. So these are the two structures of one is alcohol diethylamine ethanol and second ethyl 4-amino benzoate obtained from 4-amino benzoic acid. Benzoic acid. Now 4-amino benzoic acid cannot be used directly for synthesis of this, but that can be used in the form of ester.
Let's draw the structure of soap molecules, and this is a saponification reaction. So we have our reactants CH2 OC double bond O, CH2 14 CH3 CHO C double bond O, CH2 7 CH double bond CH, CH2 7 CH3, and CH2O, C double bond O, CH2 16 CH3 plus 3KOH, and this is going to yield CH2OH, CHOH, CH2OH plus CH3, CH214, COO minus K plus, and CH3, CH2 7, CH double bond CH, CH2 7, COO minus K plus, and CH3, CH2 16, COO minus K plus. And that would be our saponification reaction between a fat, so this is our fat, potassium hydroxide, and we will produce an alcohol, which is glycerol, and a mixture of potassium salts. And these would be our 3 potassium salts breaking apart the fat.
Problem 74 is testing your memory of amino acid abbreviations, right? So I think this problem is pretty straightforward. It's just something that you have to memorize, right? So part A is SER. So there's really only one amino acid that starts with SER, which is serine, okay? So we have serine. Part B is THR or threonine. So threonine. PRO for proline. Part D is PHE for phenyl, right? Phenylalanine. And finally, we have CYS for cysteine. Okay? So hopefully that wasn't too hard for you and you've memorized your amino acids.
Problem 75, we are drawing amino acids. So for each of these parts, we have a requirement, and then we need to draw an amino acid that satisfies that requirement. Okay, so part A, we need an amino acid that contains an isopropyl group, right, which is underlined right here, isopropyl group. And before we start doing that, I want to go ahead and draw the base structure for an amino acid, right? We have this NH2 group right here, and it's connected to CH, and it's connected to carboxylic acid, okay? And below this middle carbon is where our R group is going to be, okay? Okay, so our R group has to have an isopropyl group, okay? So the easiest I could think of is valine, okay? So valine is exactly what that is. Valine is an isopropyl group, right, connected to this base structure for amino acid, okay? So that should be part A. That's not the only amino acid with an isopropyl group, but that's the easiest that came to my mind. Okay, next. Again, before we look at that, let's go and draw our base structure for amino acid. Okay, and then we're ready for our R group. So we need something that contains an alcohol group, okay? And the easiest I could think of is serine, because serine just has a CH2 group, and then it ends with an alcohol group, okay? So that's serine. Moving on to part C. Again, before we look at our requirement, I'll go ahead and draw our base structure. Okay, so now we're ready for that R group. We need one that contains a thiol group. So thiol is an SH group, and there's really only one, right? We only have cysteine. That's the only amino acid that has a thiol group. It's not the only amino acid that has a sulfur. Methionine has sulfur, but it's not a thiol group. It's not SH, right? Okay, finally we have part D. We want something that contains an aromatic ring. Okay, so let's go ahead and start with our base structure. And we want an aromatic ring, and the easiest I could think of is phenylalanine, right? So phenylalanine has this CH2, and then it has a benzene ring. Okay, and there you have it. Again, let's just go around and name these amino acids that we drew. So part A is valine, part B is serine, part C is cysteine, and part D is phenylalanine. Okay.
Problem 76, we are identifying amino acids, okay? So we are given this massive molecule right here, and we're asked to identify amino acids, okay? So what's nice about this molecule though, it's drawn in a way that we have our backbone in a straight line, right? And everything outside this box would be our R groups, okay? So those are R groups that's going to help us to identify our amino acids. And since we have 6 R groups, as you can count those blue circles, meaning we have 6 amino acids, okay? So I'll go and erase those blue circles to make it easier to see, and let's go for it. Okay, so our first group right here, okay, we have a CH, so we have a C connected to 2 more methyl groups, okay, and if you notice, it looks like a V, an upside down V, and that's how I remember the amino acid valine. Okay, it looks like a V. Okay, next group right here, we have a CH2OH. Okay, so I think this is just something you have to memorize. That would be serine. So you have one carbon and then it ends with a alcohol group. Okay, all right, then our third R group here is very unique. It has that phenyl group attached to it. So from phenyl, it has a phenyl group that tells us this is phenylalanine. And it gets that name because alanine only has CH3 as an R group, and then you connected a benzene ring to it, or you connected a phenyl group. So hence the name phenylalanine. Okay. Next, our fourth R group right here. As you can see, it has a sulfur, so meaning we could only have either cysteine or methionine. Okay, but since our S is in the middle of carbons, that means we have methionine. Okay, methionine. If it was cysteine, that S is gonna be the very end atom. Okay, so we're gonna have SH if it was cysteine. Next, we got this R group, and you see that it has alcohol in it. Okay, so if you have an alcohol in your R group, you could either have serine or threonine. Okay, so serine, as we already saw on this R group, it only has one carbon with it. Okay, so meaning this would be our threonine. Okay, and finally here we have a very simple R group. We just have a CH3, so that would be our alanine. Okay, so we have six amino acids on this molecule, and if it helps, let's go ahead and write it as one molecule. So we have valine, we got serine, we got phenylalanine, we got methionine, we got threonine, and finally we have alanine. Okay, so hopefully that was helpful. Problem 78. We're asked to name all the tripeptides possible given methionine, isoleucine, and lysine. Okay, and my technique whenever we have this kind of problem is to just pick one of the amino acids to be the first amino acid in the chain. So let's choose methionine first. So I'll go right met for methionine. Okay, we're also asked to use the 3-letter abbreviations. So I'll follow that with isoleucine, and we got lysine left. Okay, and for the second tripeptide, I want to keep methionine as the first amino acid, and we have to flip lysine and isoleucine. Okay, so we got lysine as the second amino acid this time, and then we have isoleucine last. Okay, so next I want to have isoleucine as the first amino acid. Okay, so I'll have isoleucine right here, and then I have methionine and lysine left. So I'll just write methionine as second and then lysine. And then next I want to keep isoleucine being the second or the first amino acid, sorry. And then I still have methionine and lysine left, so this time I have to flip it. I need to put lysine as the second amino acid and then methionine as the last. Okay, and finally I want to have lysine as the first amino acid, so I'll put lysine, and then I have methionine and isoleucine left, so I'll just put methionine first, and then isoleucine would be last. And then again, I want to keep lysine being the first amino acid. And this time, isoleucine has to go second, and then methionine would be last. Okay, so there you have it. We have 6 tripeptides possible total. So we have 6 different combinations possible. Okay, so that's pretty much it. Problem 79. We are given 4 amino acids here. We got alanine, serine, leucine, and glutamic acid. Now we are asked 2 things. One is how many tetrapeptides are possible. So how many different combinations can we have with these 4 amino acids? Of course, assuming you could only use each once, okay? And we are also asked to name 3 out of all those possibilities, okay? So we have this pretty neat formula for that. We got number of peptides, or a number of different possibilities, equals and factorial, okay? And n is the number of amino acids that you have. Number of amino acids, okay? So in case you don't remember what n factorial means, so let me explain that a little bit. So we got 4 factorial here, right? We got 4 factorial from having 4 amino acids, okay? So in math, that means we do 4 times 3 times 2 times 1, okay? So if you got 5 factorial, you're going to have to do 5 times 4 times 3 times 2 times 1, okay? So now that we have that, all that's left for us to do is solve that, which would equal to 24, okay? So there are 24 possibilities of combinations for these 4 amino acids, okay? So out of those 24, we're asked to name 3, okay? So I think it's pretty easy to come up with 3, right? So I'll just write what we have here in order. So we got alanine, right? And then serine, and then leucine, and glutamic acid. Okay? So that's for the first one. And then second, maybe I'll just rewrite the same thing and then flip the last 2, right? Glutamic acid and then leucine, right? And then I need one more. So maybe I'll flip the first 2, right? I'll get alanine. Oops. I just said I'll flip those first 2. So I'll have serine first, and then alanine second. And then I'll just go on with glutamine and then leucine. Or glutamic acid, sorry. Okay? So that's it. We got 3 out of 24 possibilities. And I hope that was helpful. Alright, problem 80. Okay, we are asked to define the structural difference between an aldose and a ketose. Okay, so right off the bat, we could see that these are sugars. Okay, because of the suffix ose. So that's a suffix we use for sugars. And then what I have down here are 2 different structures of sugars. And this is not included in the problem. This is actually from a previous problem in the same chapter, but I thought they would be good examples for this problem. Okay, so we got the OSE, which stands for sugar, and then we got ald for aldose, and then ket for ketose. Okay, so aldose, from the prefix ald, that means we got aldehyde. Okay, means we got aldehyde. And then ket for ketose means we have a ketone. So that gives our structural difference, right? An aldose would have an aldehyde, and a ketose will have a ketone. And so we look at our sugars here. We look at part A and we see that does it have a ketone? No. Our carbonyl group here is at the end and it's attached to a carbon and then attached to a hydrogen, which means we have an aldehyde, okay? So this would be an aldose. And then we look at part B. Does it look like it has a ketone or an aldehyde? And it looks like it has a ketone, right? We have a carbonyl group in the middle, and then this carbon is connected to two other carbons, so that would be our ketone, and that means the sugar would be a ketose. Okay, so that is the structural difference between an aldose and a ketose. Alright, so for problem 35, we are on systematic naming. So we're asked to name these molecule models according to IUPAC rules. Okay, so starting with part A, we want to start with numbering our structure. So first we got to find the longest chain we could find, and then so let's start and do that. And I think from looking at it, I see that this would be my longest chain, right? And then I'll have two groups attached to it. Okay, and then we start counting from the end where the first branch point would occur. What I mean by that is, if we start counting from the right, we got 1, 2, 3, right? So the first branch right here, the first branch point would occur at carbon 3. But if we start counting from the left, we start with 1, 2, we see that the first branch point would be on carbon 2. So we got to start counting from the left because we want the branch point to occur first. Okay, so we want it to occur number 2 and not 3. So let's start counting from the left here. I'll go and erase everything I've got so far. Okay, so let's count from the left. We got 1, 2, 3, 4, 5. Okay, so we have 5 carbon chains. We have 5 carbons in our chain. And they're all single bonds, right? We don't see any double bonds. So that would be our pentane, right? That would be our pentane. Okay. Next is we figure out the branch points and see what we have connected. So for carbon 2, we see that we have a CH3, which means we have a methyl group attached. So that's going to be our 2-methyl, right? 2-methyl. And then next is we have, for carbon 3, right here, we have another methyl group coming out. So that's going to be 3-methyl, right? So since we have both methyl groups, we have to combine those, right? We have to combine these two and call it dimethyl. Alright, so now we've gone over all the branch points, and I think it's time to combine everything we have in here, okay? So as far as numbering is concerned, we write 2 before 3, okay? So we got 2, 3, and then we have dimethyl, right? Dimethyl pentane. Okay, so this would be your final answer for part A. So moving on to part B. Again, let's find the longest chain we could find before everything else. So from looking at it, I think this should be the longest chain, right? Actually, it doesn't matter, even if I counted this, and this would be the attached group. It doesn't matter. It will be the same amount of carbons in the chain. So we got 1, 2, 3, 4, 5, 6 carbons in the chain. But as you could see, the first branch point would be here, and also this is where our alkene is. So it's closer to the right side, okay? So we need to start counting from this side, okay? So let's go and erase everything we have so far and count from the right, okay? So let's go for it. We got 1, 2, 3, 4, 5, and 6. Okay, so we have 6 carbons in our chain, and we have a double bond. So 6 would be hex, hex, and since we have a double bond, that would be a hexene. All right. So also the hexene, right? The hexene starts on carbon 2, right here. So we're gonna have 2 hexene. All right. And also on carbon 2, we have our only group attached, right? We don't have any other branch points. This would be the only one. And we have a CH3, which is a methyl group. So we're going to go ahead and write 2-methyl because it's found on carbon 2. Okay? So at this point, I think we're done, and all we have to do is combine the information that we have. So as usual, we start with the attached group. So we have 2-methyl, 2-methyl, and then we have 2-hexene. Okay, so this would be our final answer for part B. For problem 81, we are classifying carbohydrates. Okay, so whenever we're classifying carbohydrates, we have 2 criteria. Okay, so one is it an aldose? Is it an aldose? Or is it a ketose? Okay, that's question 1. And second is how many carbons? So number of carbons. Okay, so those 2 would be like our criteria for classifying carbohydrates. Okay, so let's start with part A here. So first question, does it look like it has a ketone or an aldehyde? Okay, so we have our carbonyl group right here, and we see that our carbon double bonded to O is connected to a hydrogen. So here we have an aldose. Okay, so that this is an aldehyde. So we have an aldose. And we name carbohydrates by starting with either aldo or keto. Okay, so this would be an aldo because it has an aldehyde. And next we count the number of carbons. Okay, we got 1, 2, 3, 4, and 5. Okay, so for 5 carbons we got the prefix pent, and we got that OSE, meaning we have a sugar. Okay, so that's just a suffix for sugars. So part A is an aldopentose. Moving on to part B. So again, we look at the carbonyl group. Does it look like it's an aldehyde or a ketone? Okay, so this is our carbonyl group, and I think it's pretty clear that it is an aldehyde. So that means we start it with the prefix aldo. Okay, and next is we count the number of carbons. Got 1, 2, 3, 4, 5, and 6. So for 6, we got the prefix hex, hex, and we got that suffix OSE suffix for carbohydrates. Okay, so we got aldohexose. Part C. Let's look at our carbonyl carbon. This is right here, and since it is at the middle, that means we have a ketone, right? So we start our naming with the prefix keto, okay? And then we count our number of carbons. 1, 2, 3, 4, 5, and 6, okay? So we have 6 carbons in this sugar, meaning we have hex. We use the prefix hex. And again, we've put OSE, meaning we have a carbohydrate. So part C is a ketohexose.
Problem 82 is asking for us to draw an open chain structure of a ketotetrose, okay? So tetrose, meaning we have a sugar with 4 carbons in it, right? And then keto meaning we have a ketone as opposed to an aldehyde, okay? So I want to start by drawing just the 4 carbons. So 1, 2, 3, 4. Alright, and I just chose this carbon to be my carbon number 1, okay? So that would be our carbon number 1. And whenever we have a keto sugar, the carbonyl group is going to be on carbon 2, right? So I'm going to put it on carbon number 2. And then all the other carbons are going to have an OH group, okay? So they're all going to have an OH group. So let me add this OH group on this carbon, and then another OH group. So basically just an OH group for each carbon, okay? So this OH group is for this carbon. I just left some space there that we're going to need for the hydrogens, okay? So now we have all the oxygens that we need for this molecule. We could proceed to filling out the rest of the bonds with hydrogens, okay? So starting with carbon number 1, it's connected to carbon 2 here, and then the OH group, so it could handle 2 more hydrogens, okay? So it's going to be CH2OH, okay? This carbon 2, let me number our carbon so I don't confuse anyone. It's going to be 1, 2, 3, 4, okay? So that's the numbering for our carbons. Carbon 2 already has 4 bonds, so it's not going to have any hydrogens in it. Carbon 3 currently has 3, so it can handle 1 more hydrogen. And finally, we have carbon number 4, which is currently connected to 1 carbon and 1 oxygen. Now, so it could handle 2 more hydrogens, okay? So obviously, this space right here is not supposed to be there, so when you rewrite your molecule, just make sure you don't have that space. But this should be our open chain structure for a ketotetrose. Problem 83 is asking for us to draw an open chain structure of a 4-carbon deoxy sugar, okay? So before I even deal with this new term deoxy right here, I just want to go ahead and just draw that 4-carbon sugar, okay? And let's just deal with the deoxy part later. So I want to start with having those 4 carbons, right? 3, 4. And this sugar, I just chose to make it an aldose, okay? So that was just my personal preference. So I'm gonna have this aldehyde right here, okay? So that would be my aldose. And then if you have a regular sugar, you're just gonna have alcohol groups on all of the other carbons, okay? So let's actually go ahead and just add those alcohol groups on every carbon right here, right? And then we fill it out with hydrogens, okay? So every other bonds that are left shall be filled out with hydrogen. So carbon 1 is already is an aldehyde, so it's saturated, okay? The next carbon currently has 3, so it could handle one more hydrogen, okay? Same thing for this carbon, okay? And this this very last carbon right here could handle 2 hydrogens, okay? So deoxy, right? Term deoxy means we remove 1 oxygen, so just minus 1 oxygen, okay? So we have this, and usually it's the oxygen on the second carbon. Okay, so we have to get rid of this oxygen. Okay, and that oxygen is gonna be replaced by a hydrogen. Okay, so that should be a 4-carbon deoxy sugar, and normally it would be expressed as just an H2 here. Okay, we don't have to see that hydrogen separately connected like that. Okay, so instead of a CHOH, this changed into CH2. Problem 84, what is a fatty acid? Okay, so very straightforward. Basically, a fatty acid is just a long chain of carboxylic acid. Okay, so if you have a carboxylic acid right here, okay, then you're just gonna have a very long chain of that. Okay, so we could have maybe this is still your carboxylic acid part. Okay, and then you're gonna have that long chain with it. You could probably have some double bonds in there, right? So doesn't matter, but that is basically what a fatty acid is. Problem 85 here is asking what does it mean when we say that fats and oils are triacylglycerols? Okay, so what does that mean? So triacylglycerol is just a description of the structure of fats and oils. Okay, so this glycerol right here, so glycerol is a molecule in itself, and it looks like this. Got a CH2, got a CH, another CH2, and we got alcohol groups on all of that. Okay, so this is a glycerol molecule. Now triacyl, okay, triacyl means you have 3 fatty acids. 3 fatty acids. Okay, and as mentioned before, a fatty acid is just a very long chain of carboxylic acid. Okay, so I'm trying to draw it fast there, but that's what it looks like. Okay, and so since we have 3 fatty acid molecules, all those fatty acids would be connected to this part of the glycerol. Okay, so 1 fatty acid on this alcohol, 1 on this alcohol, and 1 on this alcohol. Okay, and as we react, of course, as you've probably seen in other reactions, that hydrogen is going to go away, and it's going to be connected to this carboxylic acid. So let's see what that looks like. Okay, so now that we've reacted our glycerol, that hydrogen is gone, and it's going to be connected to a fatty acid. Okay, so we'll have this 1 fatty acid chain right here. Okay, and then we'll have another one right here. This one shorter and probably has a double bond. Okay, and then we have 1 more. Okay, so this one is a lot longer and has a lot more double bonds. Okay, so that's what it means when we say that fats and oils are triacylglycerols. It basically just describes this general structure right here. Okay, so problem 86, we are asked to draw glycerol myristate. Okay, and we are also given its components. We are told that it has a glycerol molecule and it has 3 myristic acid molecules. Okay, which I have in here. So this is the structure of myristic acid, which I got from a table in your book. Okay, so let's go ahead and try to draw this molecule. Okay, so we're starting with glycerol. Okay, so glycerol is just 3 carbons, right? Got 3 carbons right here, and they all have an alcohol group in there. Okay, So now that we have that, we have to react this myristic acid with glycerol. And if we react an alcohol with, let me change that. So if you react an alcohol with a carboxylic acid, you'll have an ester, right? So you'll have the C right here, and then you'll have your ester just like that, okay? So this would be the carbon where the alcohol is. Oops. This is the carbon where the alcohol is, and this is where the carboxylic acid is, okay? So we're going to do the same thing with glycerol and myristic acid. So let me erase these alcohol groups for now and replace them with oxygen only. Okay, and now we're connecting it to our myristic acid. So again, we're going to have that ester, right? We're going to have that ester right there. And then we're going to have that CH2, and we're going to have 12 of those, and a CH3. Okay, and since we have 3 myristic acid molecules, that means each oxygen right here is going to be connected to that myristic acid. Okay, so CH3, and one last connection here. CH2, 12, CH3. Okay, there we have it. That should be our molecule for glycerol myristate. Okay, problem 87. We are asked to draw the structure of spermaceti. Okay, and we're told that its structure is made out of cetyl palmitate, which is an ester of palmitic acid. Okay, and we'll explain a little bit more of that later. And so cetyl palmitate and cetyl alcohol, which is a 16 carbon alcohol. Okay, so what I have here in blue is cetyl palmitate. Okay, so it's an ester of two palmitic acid molecules. Okay, so palmitic acid, as you would see in your table, is a 16 carbon fatty acid. So as you could see, this is one of those palmitic acids, and this is the second one, right? This is the second one, and of course we're gonna lose some of those oxygens in the process. So this second palmitic acid right here doesn't have the oxygens connected to it originally. Okay, so that is our cetyl palmitate. Okay, this is the ester bond that the book is talking about. Okay, so let's clear that out a little bit. Okay, and next we have a cetyl alcohol, which is a 16 carbon alcohol. Okay, so it's just straight chain 16 carbons, right? So we have 15 CH2s and 1 CH3 at the end, and we'll have that alcohol group right there, just ready for our reaction. Okay, so if we react an ester with, this is an ester, with an alcohol, so what's going to happen is this oxygen is going to replace this oxygen, right? And this whole group right here is basically going to be kicked out. Okay, and this ester would be connected to this alcohol instead. Okay, so let's go ahead and draw it down here in our page. Okay, let me use green. So we'll have the CH3. So we'll have the first part of the ester, right? CH2, 14, and then we'll have this carbonyl group right here. Okay, so that is this part. Okay, and we'll connect it with this part. Okay, so we'll have the oxygen, and then we'll have the CH2, and we'll have 15 of those, and we'll have CH3. Okay, again, obviously this this OH is gonna have to go, okay? Or this oxygen, but one of those is gonna have to go. All right, so this is actually our final structure here. This is the structure of spermaceti. For problem 88, we are asked to draw the isomers of a fat molecule, and we are given its components. So we have a glycerol, right? We have a glycerol, and we have 1 palmitic acid and 2 stearic acids. Okay, so what I have on the right here are the fatty acids that we need. Okay, so palmitic acid is a 16 carbon fatty acid, right? So it's this green structure right here that has 16 carbons. Okay, and stearic acid has 18 carbons. It's an 18 carbon fatty acid. Okay, and we have 2 of those, but this is what the structure looks like. Okay, so let's just draw one for now, and let's figure out the isomer later. So starting with glycerol, okay, we got CH2, CH, and another CH2, and all of those have alcohol groups, but I'm not gonna draw the hydrogens anymore because we know that when we combine it with fatty acids, that hydrogen is gonna have to go anyway. Okay, so we have 1 palmitic acid, so I want to go and just connect that with our first oxygen here on glycerol. Okay, so we're gonna have that ester bond. We're gonna have those 14 CH2s, right? CH2, and we have 14 of those, and we have CH3. Okay, and we have 2 of the stearic acids. So same thing for that. We got the ester, and then we're gonna have 16 of those CH2s, right? 16 and CH3. Okay, and we have one more. We have one more of that ester bond, and 16 CH2s and a CH3. Okay, so this is one of those. This is one of those isomers, and we have to think of the other one. And the only thing that I see that I could change here is the arrangement of our fatty acids, right? So instead of having these stearic acids right next to each other, I can move one of the fatty acids and move it on this top oxygen here, or top part of the molecule, I would say, and this palmitic acid would be in the middle. Okay, so let's try that. So again, I'm just exchanging these two. Okay, so again, starting with our glycerol molecule. Okay, I'll give us a little bit more space this time. And we have those oxygens. Okay, and we have the stearic acid first, so let's have that ester bond, right? And we have CH2, and we got 16 of those, and a CH3. Okay, and then we have the palmitic acid as our second ester bond here. Okay, CH2, got 14 of those, CH3. And finally, we have our last fatty acid, again another stearic acid. Okay, CH2, 16, CH3. Okay, and there we go, that we have our 2 isomers of this fat molecule. So problem 89 here is giving us this massive fat molecule, and it's asking for us to react it with KOH and give the products. Okay, so what we have here is a triacylglycerol. Okay, and whenever we're reacting triacylglycerol with a base, it makes a split like so. Okay, so probably not trying that, but it makes a split in this molecule, and what it does is it gives us back our components for a triacylglycerol, which is one glycerol molecule and 3 fatty acids. Okay, so let's go ahead and split this molecule. So we're splitting it, right? So now we're gonna have hydrogens on these oxygens, right? So these oxygens are going to be grabbing hydrogens. Okay, so now we have our glycerol and 3 fatty acids. So let's go ahead and name our products here. So we have a glycerol molecule, okay? And here we have an 18 carbon fatty acid. Okay, we got 16 CH2s and we got 2 more carbons in here. So 18 carbon fatty acid with no double bonds is going to be stearic acid, right? So this is just information that you could find in your book. Okay, so that's a stearic acid. Next we have a fatty acid with 1 double bond. Okay, so that makes it our oleic acid. Oleic acid. Okay, and finally here we have this fatty acid with 3 double bonds. So it's got 3 double bonds, which makes it our linolenic acid. Linolenic acid. Okay, so there you go. That's all our products. Problem 90. What is a nucleotide? And we have to name its 3 components. Okay, so a nucleotide is basically the monomer for nucleic acids. Okay, so monomer for nucleic acids. So nucleic acids, namely DNA or RNA. Okay, so it has 3 components, and what I have right here is a portion of a nucleic acid. Okay, so let's look at this molecule and find the 3 components. Okay, so here's one of its components. So we have a phosphate group. Okay, so we got a phosphate, and then we also have an aldopentose. Okay, so 5 carbon sugar, aldopentose. Okay, so for DNA we have deoxyribose, and for RNA we have ribose. And as you could see with this sugar, we have this oxygen right here, which tells us this is an RNA molecule. Okay, and lastly we have this amine base. Okay, so we have adenine, guanine, cytosine, thymine, and uracil for RNA. Okay, this specific one is adenine. Okay, this one is adenine, but in general we have an amine base. Okay, so there's our 3 components. We have a phosphate, an aldopentose, and an amine base.
Okay, so for problem number 36, we're asked to identify the amino acid given the molecular model. Okay, so before we start, I want to remind everyone with the main chain for amino acids. We start with an amine group, and then we got a carbon, and then we have another carbon that is part of a carboxylic acid. Okay, so this is an amine group right here. And then this is where we would have our side chain, right? The other one would be a hydrogen. So the side chain is going to help us identify the amino acid. In fact, that's the only way we identify it when it comes to structures. Okay, so let's start with part A. Let's find that main chain, right? So here we have the blue sphere, which represents our amine group, and this would be our carboxylic acid. So that means this this whole part right here would be our main chain. So that leaves us with this part being our side chain. So let's see what we have in our side chain. Okay, so we have a carbon connected to two hydrogens. So we have a CH2, right? And it is connected to an oxygen atom, and which is connected to a hydrogen atom. So we have an alcohol group. Okay, so we have CH2OH, which you probably remember is the side chain for serine. Okay, serine. Moving on to part B. Again, let's look for our amine group, which we see right here, and this part is our carboxylic acid, which means that this part would be our main chain for amino acid, and everything that's left would be our side chain. Okay, and in case you didn't notice, I actually didn't point it out. Here's the hydrogen atom connected to our carbon right here, right? So this hydrogen I'm boxing on the left represents this hydrogen, and same thing for part B. Here's that hydrogen. Okay, so everything outside the blue box here would be our side chain. So let's see what we have, right? We have ACH2 right here, right? And then we have another CH2, right? And then we have this yellow sphere, which represents a sulfur atom, okay? And finally we have a CH3. Okay, so there's only two side chains with a sulfur. One would be a cysteine and one would be methionine. Okay, and as you probably remember, a cysteine would have an SH at the end, so the sulfur atom would be the very last atom. And we see here that we have a methionine because we have a methyl group after sulfur. Okay, so this amino acid would be methionine. Okay, so hopefully that was helpful.
Okay, so for problem 91, we are asked to name the sugars in DNA and RNA. Okay, so for DNA, we call the sugar deoxyribose. Okay, so deoxyribose, and I actually have the molecule right here to the right. So this right molecule is deoxyribose. Deoxyribose. Okay, so that's for DNA. And next is for RNA. We got the sugar ribose, which is actually this structure here to the left. So ribose. Okay, so what's the difference between the two? Well, there's only really one. Okay, an oxygen. That's it. Okay, so we have a ribose, right? You take away that oxygen, we call it deoxyribose. Okay, so that's the only difference. Nothing more, nothing less. Okay, and I hope that was clear. Problem 92 is asking for us to show the phosphate sugar bond in nucleic acids. Okay, so I just have the sugar here. This one is specifically ribose, and it already has the base attached to it. So now we just have to connect the phosphate group that we are missing. Okay, so there's going to be two phosphate groups attached to this molecule. Okay, so one would be here on the 5' carbon, right? So our phosphate is going to be connected to this oxygen, right? Let me actually just put it up. So this is where going to be our phosphate is. You're going to have that double bond and that single bond and so on and so forth, okay? So this top part is going to be connected to another sugar, okay? And then on the 3' end of this sugar, let me erase that part. Okay, so on the 3' end, which is this part, I'll go and erase our hydrogen, right? And we are going to be connecting this oxygen to another phosphate group that is going to be a part of the next nucleotide, okay? So here we're going to have our phosphate group, right? We're going to have this double bond right here. We're going to have this oxygen with a negative charge on it, and then there's going to be another oxygen, and this is where we're going to have our 5-membered ring or our sugar, okay, and so on and so forth. So this would be the second nucleotide at this point, okay? But there you go, there's how phosphate is connected to our sugar here. Problem 93 here is asking for us to show the sugar amine base bond, okay? So what I have right here is a phosphate group connected to our ribose here, and we have a uracil molecule here on the right, which needs to be connected to this sugar, okay? So this uracil or amine base molecule is going to have to connect to the sugar, and where this arrow is pointing at is actually where this base is going to attach, okay? So what I want to do here is to remove this OH group, right? So we're deleting that OH group, and we are connecting our base, okay? So and the part of the base that is going to connect with the sugar is the nitrogen, okay? So this carbon right here is going to be connecting to that nitrogen, okay? So I'm not drawing the length of the bond to scale here because of just the constraints of our drawing, but this is where that amine base is going to connect. So there you have it. So problem 94, we are given a DNA strand, and we're just asked to give the complementary strand of this DNA, okay? So just as a reminder, when it comes to DNA, G pairs with C and A pairs with T, okay? So our first base here is a thymine, so that's going to be pairing with A pairs with T, C pairs with G pairs with C, and A pairs with T, okay? So that should be our complementary strand. For problem 95, we are given the DNA strand, and we are asked to come up with the complementary RNA strand, okay? And so before we go ahead and answer that, let's just go over the pairings for DNA and RNA first, okay? So when it comes to RNA, it's just like DNA, G pairs with C and C pairs with G, right? And A, unlike DNA here, when it comes to RNA, A pairs with U, which is uracil, okay? But T still pairs with A, okay? So this would be if you have your DNA and this is the corresponding RNA bases, okay? So let's go for it. We have this first base here, which is thymine. So again, thymine still pairs with adenine, right? So A, however, pairs with U when it comes to RNA. C still pairs with G, just like DNA. G pairs with C, and A again pairs with uracil. Okay, so problem 96, we have polypeptide chains, right? One of them has 21 amino acids and one of them has 30 amino acids. So there we go, 21 and 30. And we are asked how many nucleotides would be needed to code for each of these polypeptide chains. Okay, so this question is actually pretty straightforward. It's pretty simple. Okay, as long as we know that one amino acid, I'm gonna abbreviate it with AA. Okay, so one amino acid is coded by 3 nucleotides. Okay, let me write that. So one amino acid is coded by 3 nucleotides. Okay, so that's just the crucial information that we have to know. But now that we know that, okay, we have 21 amino acids, and in order to calculate the number of nucleotides needed, we just multiply it by 3, right? And the same thing for 30 amino acids, we just multiply it by 3, because again, 3 nucleotides are needed for 1 amino acid. Okay, so polypeptide chain with 21 amino acids would need how many? 63, right? Needs 63 nucleotides. And following the same process, 30 amino acids would need 90 nucleotides. Okay, and that's it. That's our final answer for this problem. Problem 97, we have sea urchin DNA here, and we are given its composition. Okay, so we are told that adenine comprises 32% of its DNA, and guanine comprises 18% of its DNA, and we're asked to calculate the percentage of thymine and cytosine in the DNA. Okay, so before we go ahead and do that, just wanted to mention that this information is irrelevant, right? We didn't have to know that it's a sea urchin. We just had to know that we're dealing with DNA. Okay, so I think it's very important to be knowledgeable of what information you need or you don't. Okay, so anyways, so we have adenine here, and I just wanted to remind everyone that adenine pairs with thymine when it comes to DNA, and guanine pairs with cytosine. Okay, so it's safe to assume that since A pairs with D and G pairs with C, A here is always going to have the same amount as D, right? For every A that you have in your DNA, you have the same amount of thymine. Okay, so if A comprises of 32%, then it's only logical to think that thymine would also comprise of 32% of DNA, right? And following that same logic, because guanine occupies 18% of the DNA, then every guanine would have a cytosine associated with it, then cytosine should also occupy 18%. Okay, and if you want to verify that information and see if you got the right numbers, you could go ahead and add all the percentages that we have, and all of these should total to 100%. Okay.
Let's draw the following compounds. For A, we have 2-methylheptane. So this would be a heptane, CH3, and a methyl group at carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, 2, 3, 4, 5, 6, carbon 7 for the heptane parent, 2-methylheptane. For B, 4-ethyl, 2-methylhexane. This would be CH3, CH, carbon 2, there's a methyl group. CH2, CH, carbon 4, there's an ethyl group. Carbon 5, carbon 6. So there would be 4-ethyl 2-methylhexane. For C, we have 4-ethyl 3,4 dimethyl octane. So carbon 1, carbon 2, carbon 3 is a methyl group. Carbon 4 is a methyl group and an ethyl group. Carbon 5, carbon 6, carbon 7, carbon 8. For D, 2,2,4 trimethylheptane. CH3, carbon 2, there are 2 methyl groups. CH, 2,4,4. Let's go backwards. Not 2,2,4. 2,4,4 trimethylheptane. So CH3, CH, so 1 methyl group, CH2, carbon 4, there are 2 methyl groups, carbon 5, carbon 6, carbon 7. There's my heptane 7 carbon parent. For E, we have 1,1 dimethyl cyclopentane. So draw cyclopentane, 5 carbon ring, carbon 1, 2 methyl groups. So there's 1,1 dimethyl cyclopentane. And for F, we have 4 isopropyl 3-methylheptane, and this would be CH3, CH2, CH, carbon 3, we have a methyl group. Carbon 4, we have an isopropyl group. Carbon 5, carbon 6, carbon 7. And there would be 4 isopropyl 3-methylheptane. Let's provide a UPAC names for the following alkanes. For A, we have 2,3 dimethyl hexane. For B, we have 4 isopropyl octane. For C, 4 ethyl 2,4 dimethylhexane. For D, 3,3 diethyl pentane. And for No, there is no E. We'll end with D. So there are our UPAC names for the following alkanes.
Alright, so problem 100, we are asked to draw the structure of carnauba wax, okay? And we are told that its composition is made of a C32 straight chain alcohol and a C20 straight chain carboxylic acid, okay? So we're making an ester out of those components. And before we go do that, I just wanted to remind everyone of what the basic structure of this would look like, okay? So let's say we have this carboxylic acid, right? We got carboxylic acid and it's connected to an alkyl group, which I'm just going to label R1, okay? So we have this carboxylic acid right here, just like that. And then we have an alcohol right there with R2, okay? So if you combine these into an ester, we are gonna get a structure that looks like this. Okay, so this would be our ester, and this would be the R2, okay? So we see that we kind of combine these two alcohol groups into just one oxygen, okay? So following that pattern, let's go ahead and start drawing our C20 carboxylic acid. Okay, so I want to go ahead and start with this one, starting with the carboxylic acid, okay? So C20, so let's start with a CH3, right? And then we're gonna have 18 CH2s in between. We got 18, so that's a total of 19 right now, and we'll have that 20th carbon as a carboxylic acid, okay? So since we already know what base structure we're looking for, I'm gonna go ahead and start drawing the alcohol connected to it already, okay? So I'll be drawing this C32 straight chain alcohol, okay? So this would be the alcohol part. We got 32 carbons, so we're gonna have 31 CH2s, right? We're gonna have 31 of these, 31, and then the 32nd carbon would be a CH3. Okay, so as you see, this follows our pattern that we established earlier. Okay, so hopefully that was clear.
Let's draw the 3 resonance forms of naphthalene. So one resonance form would be placing the double bonds in this configuration here. Second resonance form would be placing the double bonds in this configuration here. And the third resonance form would be placing the double bonds in this configuration here. So these would be the 3 resonance forms of naphthalene. Let's solve for the minimum molar mass of this enzyme cytochrome C. So we're told that cytochrome C is 0.43% iron. So if we assume that we have 100 grams of cytochrome C, that would yield 0.43 grams of iron. So starting from 0.43 grams of iron, let's solve for the moles. So this would be molar mass, 55.85 grams of iron in 1 mole of iron, and this would yield 0.0077 moles of Fe. Now we're going to assume that this is the minimum molar mass, that each cytochrome C has at least one Fe atom present. So we'll assume a 1-to-1 mole ratio. Therefore, if we found that 0.0077 moles of iron, and if it's a 1-to-1 mole ratio, we'd have 0.0077 moles of the cytochrome C, and so the molar mass for cytochrome C would be equal to the 100 grams that we assumed divided by the 0.0077 moles, and therefore this would yield a molar mass of, now 2 sig figs, 1.3 times 10 to the 4th grams per mole. Let's write a full structure of the following peptides. So we have valine, phenylalanine, and cysteine, and then we'll also indicate the position of the amide bond. So we're going to have NH2, CH, CH3, CH3, C double bond O, and H, CH, CH2, and aromatic ring. C double bond O, and H, CH, CH2, SH, C double bond O, OH, and our amide bonds would be here and here. So these would be where the amide bond is formed. For B, we're going to have the polypeptide glue, pro, ILE, and U. So here's our peptide. So we've got NH2. I'm going to do this one fairly small to make it fit. CH, CH2, CH2, COOH, C double bond O, N, CH. This would be structure here. C double bond O, and H, CH, CH, CH2, CH3, CH3, C double bond O, and H, CH, CH2, CH, CH3, CH3, C double bond O, OH. So the amide bonds here, I am going to just outline them. We have an amide bond here, we have an amide bond here, and we have an amide bond here. There are 3 amide bonds joining the amino acids together. For A, let's write the representative structure for a fat. CH2, CH, CH2, O, C, double bond O, CH2, CH2N. Now we can have a long chain here of a long carbon chain, O, C double bond O, CH2, CH2N, CH3. So again, a long carbon chain there, O, C double bond O, CH2, CH2N, CH3. So there would be kind of a representative structure for a fat. For vegetable oil, gonna look very similar. CH2, CH, CH2, O, C double bond O. Now there's going to be some unsaturation here. So we could have a long chain, CH, CH double bond here, and this could yield another, so we can have different levels of unsaturation in a sample of vegetable oil. CH double bonds present. So we can have these double bonds in these long carbon chains, and that would be kind of a representative structure of vegetable oil. And for C, we're looking for a general structure for an aldotetrose, and an aldotetrose would have a structure C double bond O H, C O H H, C H H O, C O H H, and H. So there would be kind of a representative structure for an aldotetrose.
Problem 104, we are given a DNA strand and we are asked to come up with the complementary DNA strand. Okay, so just to refresh everyone's memory, when it comes to DNA, G pairs with C and vice versa. C also pairs with G, and A pairs with T and vice versa. Okay, so let's go for it. We got A, and that pairs with T. G pairs with C. D pairs with A. C pairs with G. A pairs with T. T pairs with A. C pairs with G, and finally we got G pairs with C. Alright, problem 105. We are asked to draw the structure of jojoba wax, right? And we are told that the structure of this wax is an ester. It's an ester of stearic acid, and a C22 straight chain alcohol. Okay, so if you look back to your table in your book, you'll see that stearic acid is a C18 straight chain carboxylic acid. Okay, so I want to go ahead and start by drawing that stearic acid. Okay, so C18, so we're starting with CH3, and we'll have 16 CH2s in between. Got CH2, we got 16 of those, and our final carbon is going to be that carboxylic acid. Okay, OH. Okay, so just as a reminder as well, whenever we have a carboxylic acid and an alcohol and we react them as an ester, we're gonna end up having a molecule that looks like this. Okay, so this would be the carboxylic acid, and this would be the alcohol. Okay, so following that pattern, I would go ahead and delete this hydrogen right here and draw that C22 straight chain alcohol. So this part, right? So we have 21 CH2s, right? We have 21, and that 22nd carbon, since we have C22, would be a CH3. Okay, so we could count the carbons just to confirm, but this should be the final structure for jojoba wax. Alright, problem 106. So we are given this molecule, methylphenidate, okay, and we are asked to do two things. One is to identify the function groups, and second is to predict the products after reacting it with an aqueous base. Okay, so let's start with the function groups. That should be pretty straightforward. Okay, right off the bat we see this huge aromatic ring right here. So we have this benzene ring, so that would be our aromatic function group, right? And we also see this nitrogen, right? See this nitrogen right here, so that makes it our amine, right? We don't see any carbonyl carbon next to it, so that should be our amine group. And finally we have this carbonyl group right here, and as you notice, it is not connected to hydrogen, but it is connected to a CH3 group, so that makes it our ester. Okay, so let me write our function groups over here to the left so I could erase what we have in there. So got aromatic, we got amine, and we have an ester. Okay, so we are going to react this molecule with an aqueous base, so I'm going to need all this space, and I need to clear all of that writing. Okay, so what we have here is an ester. Okay, we have an ester. So just like what we have when it comes to fatty acids or triacylglycerol, whenever we react an ester with an aqueous base, it makes a split down this oxygen, right? And it gives you a carboxylic acid on this side and an alcohol on this side, right? So what I'm going to do here now is to make that split, right? So let me erase. I'm going to erase this methyl group right here, right? And replace that with an oxygen, or I'm sorry, a hydrogen, okay? So that would be the carboxylic acid side of this molecule. And since we deleted that methyl group is going to have its own alcohol connected to it, okay? And there you go. So these are our products after reacting this molecule with an aqueous base. We have a carboxylic acid and we have an alcohol. Okay, so problem 107, we are asked to draw the line bond structure of these two molecules, oleic acid and allylic acid. Okay, so starting with oleic acid, a couple of things that we need to do or we need to know is that one is it has 18 carbons. Okay, it is a cis isomer, and the double bond is on carbon 9 and 10. Okay, and allylic acid is the trans isomer of oleic acid, so that double bond is also on C9 and C10, but it is in trans isomer, okay, or trans configuration. So let's start with drawing our oleic acid. So I always, whenever I draw fatty acids, I always want to start with the carboxylic acid. Okay, so that's our carbon 1, and this is our carbon 2, right? 2, 3, 4, 5, 6, 7, 8, 9. Since this is our 9th carbon, we want to go and do that cis configuration. So carbon 10, 11, 12, 13, 14, 15, 16, 17, and 18. And of course that double bond is going to have to be here. Okay, so this should be our oleic acid. And next, we are drawing the trans isomer of the exact same molecule. Okay, so again, we're starting with carboxylic acid. That's carbon 1, and this is carbon 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And I believe, actually, let me just go ahead and count. Got 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 10. Okay, so our double bond has to be between carbons 9 and 10. And there you have it. That should be our allylic acid.
Let's solve for the empirical formula of fumaric acid. We're going to assume 100 grams, which will yield 41.4 grams of carbon, 3.5 grams of hydrogen, and 55.1 grams of oxygen. Let's convert all of these to moles. 12.011 grams of carbon in 1 mole will yield 3.45 moles carbon, and 1.008 grams of hydrogen in 1 mole will yield 3.5 moles of hydrogen and 16.00 grams of oxygen in 1 mole will yield 3.44 moles of oxygen divided by the least, which is 3.44, and the nearest whole number ratio would be 1, 1, and 1. Therefore, our empirical formula for fumaric acid will be CHO. For B, we're asked to find the molecular mass. So for B, let's first solve for the molarity by rearranging the formula for osmotic pressure. We're given the osmotic pressure at 240.3 millimeters of mercury, but we have to convert this to atmospheres. And one atmosphere is equivalent to 760 millimeters of mercury. And in the denominator, ideal gas constant, liters, atmospheres per mole Kelvin, and told the temperature here is 298 Kelvin. Therefore, the molarity here will work out to 0.0129 moles per liter. And now we can find the moles of fumaric acid. The moles would be equal to C times V. Concentration we just got 0.0129 moles per liter times the volume. We're told that we have a volume of 100 milliliters, so this is 0.1 liters, so our moles will be 0.00129 moles. And now we can calculate our molar mass, which will be equal to, we have 0.1500 grams of the fumaric acid over the 0.00129 moles, and this will yield a molar mass that's equal to 116 grams per mole. So there's our molar mass for the fumaric acid. For C, we're asked to draw three possible structures. We first have to calculate the molecular formula before we draw the structures. So N, molar mass, divided by empirical mass. Molar mass, 116 grams per mole, we just calculated. The empirical mass, which is based on our empirical formula, CHO, which is 29 grams per mole. This will work out to 4. So that's our whole number ratio. So our molecular formula for fumaric acid is equal to 4 times CHO, which will be equal to C4H4O4. So our three structures that we can come up with here, structure number 1 would be structure here. So there's one structure, second structure, and our third structure is going to be OH, C, double bond O, C, C, O, OH, double bond CH2. So there's our three structures for fumaric acid. And for D, we're told that if it contains a trans double bond, so fumaric acid contains a trans double bond. Therefore, from part C above, structure 2 is correct. For A, we're asked which group is more acidic. So the pKa for the carboxylic acid group is equal to 2.34, and the pKa for the NH3 plus group is equal to 9.69. So the group with the lower pKa is more acidic. Therefore, the CO2H group is more acidic. For B, what percentage of each form is present at pH 4? So we've got H2A plus, and this would be represented by pKa1, which is equal to 2.34 to H2A, or sorry, that would just be HA, and this would be A minus pKa2, which would be pKa of 9.69. At a pH equal to 4, the predominant species are H2A plus and HA, as the pH is closest to pKa1. So we'll have to use the Henderson-Hasselbalch equation here, which is the pH is equal to the pKa plus the log of HA over H2A plus. The pH is 4, the pKa is 2.34, plus the log of HA H2A plus. So the log of HA over H2A plus is equal to 1.66. Solve this mathematically here. HA over H2A plus would be equal to 10 to the 1.66, which would be equal to 46. Let's write this as ratio. It would be 46 over 1. Therefore, the percent of HA would be equal to 46 over 46 plus 1 times 100%, and this would be equal to 98%, and the percent of concentration, and then the percent of the molarity of H2A plus would be equal to 1 plus 46 plus 1 times 100% according to the ratio, and this would be equal to 2.1%. So there would be the percentage of each at a pH of 4. For C, at a pH equal to 8.50, the predominant species are HA and A minus, as the pH is closest to pKa2. So let's apply the Henderson-Hasselbalch equation again. pH is equal to pKa plus the log of A minus over HA. The pH is going to be 8.50. pKa is 9.69 plus the log of concentration ratio, the log of A over HA minus over HA would be equal to minus 1.19, and so the ratio here, A minus over HA, is equal to 10 to the minus 1.19. Solving this, we will get this is equal to 0.065 over 1. Now, using this ratio here, the percent of A minus would be 0.065 over 0.065 plus 1 times 100%, and this would work out to 6.1%, and the percent of HA would be equal to 1 over 0.065 plus 1 times 100%, and this would be equal to 94%. For D, at what pH is the neutral form present in maximum amount? So the neutral form would be present when we average the pKa values. So the pH is equal to the pKa1 plus pKa2, and divided by 2 would give us the average there. So this would be 2.34 9.69 over 2, and solving this, we get a pH that's equal to 6.01. Therefore, the maximum amounts of the neutral form of the amino acid is at a pH equal to 6.01. For A, let's calculate the mass of the iodine. Starting from, we have 25 milliliters, which will be 0.0250 liters, times the molarity, which we're given as 0.2 moles per liter, times the molar mass. 1 mole of iodine has a molar mass of 253.8 grams, and this would yield the mass of I2, which would be 1.27 grams. For B, let's calculate the mass, or the mass of I2 reacted and how many grams are in excess. To do so, we'll need the balanced equation, and the balanced equation is 2Na2S2O3 plus I2 to produce 2NaI and Na2S4O6. And first, let's find the moles of the Na2S2O3, and we're starting with 81.99 milliliters, so 0.08199 liters, and the molarity is 0.1 moles per liter. This will yield 0.008199 moles of the Na2S2O3. Now using the balanced equation and the stoichiometry, 0.008199 moles of the Na2S2O3 times 2 moles of the Na2S2O3 to 1 mole of I2. And moles of I2 we can find are going to be equal to we'll carry some extra sig figs here. 0.0040995 moles of I2. And now let's find out the mass of I2, which will be reacted, will be equal to 0.0040995 moles of I2 times 1 mole of I2 has a mass of 253.8 grams of I2, and this will yield I2 reacted of 1.04 grams. So that's the first part of the question. And then the mass of I2 in excess will be the starting amount, which is 1.27 grams minus the 1.4 grams. So this will yield 0.23 grams of I2 that would be present in excess. For part C, the iodine number in human milk fat would be equal to the mass of I2 times the mass of the fat times 100%, or just times 100. So we found that we have the 0.23 grams of I2 present in excess, and we have 0.500 grams of the fat times 100. So the iodine number works out to 46. And lastly, assuming a molar mass of 800 AMU, how many double bonds does an average molecule of milk fat contain? So let's first, for D, using the molar mass, let's calculate the mole of fat. So we have 0.5 grams and the molar mass is 800 AMU, or 800 grams per mole. So we can find that this is equal to 0.000625 mole of the fat. And we can find the mole of iodine present in excess, which would be 0.23 grams over 253.8 grams per mole is its molar mass. So this would be equal to 0.00091 moles of I2. And so the mole ratio between I2 and the fat would be 0.00091 over 0.000625, and this would yield a ratio of 1.4. So the average molecule of milk fat contains 1.4 double bonds.
Okay, so for problem 38, we are asked to identify the dipeptide. Okay, so the only thing we want to do here is to find our R group or our side chain and identify the individual amino acids, okay? And the way we do that is to find the main chain first. So again, I just want to remind what the main chain for amino acid is. So we have an NH2, we have a carbon and another carbon that is part of a carboxylic acid, right? And then we'll have that R group sticking out of it, and this is what we're interested in, okay? Of course, there's that other hydrogen connected to that. All right, so our amine group is represented by a blue sphere, okay? So that represents the nitrogen. So we see our nitrogen atoms here, and we have to find that carboxylic acid, okay? So you see that there's this amine group right here, and this is the carbon that is double bonded to an oxygen, and we don't see the carboxylic acid part anymore because once you get a dipeptide, you will have this amine group from the other amino acid connected to it. So this is still our backbone for the first amino acid, right? So this part right here. And then we continue on with the second amino acid. This would be the amine group for it, right? And there's our carboxylic acid right there at the end, okay? So now everything I have outside the blue box would be our R group, okay? So this is our first R group. This is our second R group, okay? So our first R group has a CH2 connected to an OH, right? This is an oxygen atom. So that is the R group for serine, right? And the second R group right here, we see that we have a, let me try to highlight it. This part right here, we have a CH, okay? So we have a CH, and then it's connected to two methyl groups, okay? Oops. It's connected to two methyl groups, so CH3, CH3, and this R group is very characteristic of valine. Valine, okay? The way I want to remember that is that it looks like the letter V, right? So this R group kind of looks like a letter V, which stands for valine, okay? So let's rewrite that into our dipeptide. So I think we're asked to use the three-letter abbreviations as well. So we're going to have SER for serine and VAL for valine. So this would be our final answer. Okay, so problem 39 is asking for us to identify the amine base. So the molecular models given here are bases that can be found in nucleic acids. Okay, so starting with part A here, we see that we have two rings in our structure. So whenever you have two rings, you could only have A or G. Okay, and what's our telling feature here is this carbon double bonded to oxygen, okay, and also this amine group right here. But more so, at least for me, this is what I look for. Okay, so whenever I see two rings with a carbon double bonded to oxygen, that tells me that it is guanine. Okay, so that one is guanine. And of course, you have to make sure that you actually have a base that can be found in nucleic acid. Okay, so moving on to part B. Okay, part B, we have one ring only, right? So that tells us we could have C, T, or U. Okay, remember we have that uracil for RNA. Okay, so right off the bat, we got just one carbon double bonded to oxygen. Okay, so we only have one carbonyl group, and the other one is a amine group. Okay, so whenever you see this this combination of functional groups, then you know that you have cytosine. Okay, you have cytosine. And I say that because thymine and uracil both have two COO bonds. Okay, so you're gonna see two of these if you have thymine or uracil. Okay, so that would be our answer for 39.
In this problem, we are given with a galvanic cell, and we are given the shorthand notation for the galvanic cell, and we are asked to find out the balanced equation for the overall cell reaction, and we have to give a brief description of the galvanic cell, which is represented by that shorthand notation. So let's down the shorthand notation first, and it is like this. Lead metal is oxidized to lead 2 plus ion, and here bromine, liquid bromine is being reduced to bromide ion, and by this platinum we mean that this is the electrode for the cathode. To write down the overall cell reaction, first let's write down our half cell reaction for anode and cathode. So the anode half reaction will be for this one. So in this case, lead metal will be converted to lead 2 plus ion by releasing two of its outermost shell electrons, and this will be our, this is our anode half reaction. And the cathode half reaction will be the conversion of bromide ion from liquid bromine. So the reaction equation will be liquid bromine taking those two electrons from the anode half reaction, and it will be converted into two bromide ions. So this is our cathode half reaction. So now we know our anode half reaction and cathode half reaction, and for the overall cell reaction, all we have to do is to sum up these two equations. So if we sum up these two half equation, we'll get the full overall equation, and from here we can easily see that if we add them up, these two electrons and these two electrons will cut off, and the overall reaction will be so this is our overall cell reaction for this. And now we are asked to describe the galvanic cell, which is represented by this shorthand notation. So to represent or to describe the galvanic cell, we can draw the galvanic cell real quick. So if these two are our compartments, and if this is our anode compartment, this is our cathode compartment, we'll have two metal strip as anode and cathode. So in this case, our anode is a lead strip. So this is our lead anode, and the cathode is a platinum wire, which is mentioned by this PT here. So the cathode is platinum, and there will be a wire connection, two of them, and the electron will be produced here in the anode when these lead metals will produce lead ion and electron, and these three electrons will go this way, come here, and they will reduce the bromide to the liquid bromine to bromide ions, and here is the galvanic cell for this cell notation.
In case of lithium chloride, it ionizes, it forms lithium ion and chloride ion. 2 lithium chloride gave 2 lithium ion and 2 chloride ion. In case of inert electrode, the following reaction take place at anode. Oxidation take place, so the chloride ions form chlorine molecule and release 2 electron. On the other hand, at cathode, the lithium ion gain the electrons and form lithium. In case of copper sulfate solution, when it oxidizes, it forms copper ion and sulfate ion. The following reaction take place when the electrodes are inert electrodes at anode. Oxidation of the water molecule take place, where water molecule form oxygen, hydrogen ion and release 4 electrons. On the other hand, at cathode, 2 copper ions gain these 4 electrons, forming copper atoms. In case of potassium chloride sulfate, when it ionizes, it forms potassium ion and sulfate ion. At anode, using inert electrodes, at anode oxidation of the water molecule take place. Water form oxygen, 2 hydrogen ion and release 2 electrons. The potassium ions at cathode gain these 2 electrons, forming potassium atoms. The overall cell reaction in each case can be written by adding the anodic and cathodic half reaction. So we can, in case of lithium chloride, we can cross the electron on either side, so we can say that 2 chloride ions react with 2 lithium ions, forming chlorine gas and 2 lithium atoms. In case of copper, we can cross the electrons on either side, so we can write that two water molecule react with the two cupric ions, forming two copper atoms, an oxygen molecule and four hydrogen ions. In case of potassium sulfate, adding the two reactions, we can cross the electron on either side, so we can write that a water molecule react with the potassium ion, forming potassium atoms, oxygen gas and two hydrogen ions. And silver plating, silver is made the anode, and at anode the oxidation of the silver take place, where silver oxidizes to silver plus ion and electrons is released. On the other hand, at cathode, the same silver ion move from the anode toward the cathode, where it gain electron back and is reduced to silver metal. This is the electroplating cell for the silver. The anode is made up of silver, where oxidation takes place. Silver oxidizes and move toward the solution in the form of Ag+, while it moves toward the cathode. When the silver ion moves toward the cathode has negative charge, while anode has positive charge. So a non-spontaneous reaction takes place by the help of electric current or voltage supplied by the source. There is external source which supply the voltage. The silver spoon has negative charge over it. When the silver ion from the solution move toward the silver spoon, it reduces and a uniform coating of silver is formed over the silver spoon. AgNO3 silver nitrate is used as electrolyte in the electroplating cell of the silver. We can say a total n number of silver oxidizes, giving n number of electrons, where again the n number of silver reduces and form a uniform coat over the silver spoon.
So we're given a mixture of aluminum and cryolite. Okay. You have aluminum, then you have cryolite. Is a mixture. Then you're told that a current of 1 times 10 to the power 5 coulombs is passed for 8 hours. Okay. And remember, this time needs to be in seconds. Okay. So automatically, we need to can get the charge that was used. Okay, because charge is given as current multiplied by time. This time needs to be in seconds. Okay, so that means that this is going to be 1 times 10 to the power 5 multiplied by 8 hours multiplied by 60 to convert them into minutes, then again by 60 convert these into seconds. Okay, so this is going to be around 2.8 times 10 power 9 coulombs. This is a lot of charge for that particular electrolysis reaction. So from here you can get moles, because we know that from Faraday's constant, we know that 1 mole of electron equals 96,500 coulombs of charge. So we need to get how many moles of that were used for this particular reaction. Okay. So when you do the math, so we're going to equate about 2.8 times 10 power 9 coulombs of charge. So when you cross multiply, you're going to get that the most moles of electrons that were used here are 22.9844 times 10 to the power 4 moles. Okay, but when you look at half cell reaction for this aluminum, you know that 3 moles of electrons were needed to for this reaction. So aluminum is going to gain 3 electrons so that we deposit aluminum metal. So this is what we need to find out, how much of this was deposited. That means we're going to divide this number of moles for by 3 electrons each, so that we get how many is for this particular reaction. That means we're going to have moles of aluminum used. So are going to be 2.9844 multiplied by 10 to the power 4 multiplied by 1 mole of aluminum divided by 3 moles of electron. So this is going to give us around 9,948.18 moles. Okay, these are just moles that we used here. So we have moles and you have gram of aluminum. Remember, gram of aluminum is metal is 26.98 grams per mole. That means when you want to get mass that we are asking in kilograms, we're going to multiply gram, relative atomic mass, multiplied by the number of moles. So ram is going to be 26.98 grams per mole. Okay, multiplied by 948.218 moles. So per mole and moles are going to cancel out, so that you get mass in grams. And this is going to be 268,418.62 grams. This, when you divide by 1,000 for convert them into kilograms, we're going to get around 268.42 kilograms of aluminum that will be deposited here. So that's the procedure for this particular question. So in this video, we are given silver, element silver. Okay. Then we are told that this silver is electrolyzed with current of current is 0.1 amperes. Okay. This current is too small that it will take a lot of time for us to to deposit a mass of 3 grams. Okay, it will take a very long time for us to deposit a mass of 3 grams with this current. It's very small. 0.1 is very, very small. Okay, but then we also need to understand that silver has a ram of 108 grams per mole. Okay, So we need to find out how many moles mass of this particular mole. Okay, we need to find out how many moles of silver are we talking about. Okay, so we're going to use the moles to divide the mass that is deposited. Okay, by the relative atomic mass, grams per mole. Okay, so this is going to give us around 0.02778 moles. Okay, this is just the moles of that are deposited, but then we understand also that 1 mole of electron gives us the Faraday's constant, which is 96,485 charge coulombs of charge. Okay, so we need to find out how much charge these particular moles that are involved give us. Okay, so how about 0.02 778 moles? How much charge are these going to give us? So when we do cross multiplication, you're going to get that this is same as saying 96,485 coulombs or ampere seconds multiplied by 0.02778 moles. Okay, divided by 1 mole of electron. Okay, this is going to give us around 2000. Okay, 2680 coulombs. But then we understand that charge in coulombs is the product of a current and time. So if there's a case, we're going to substitute that. So current multiplied by time. In this time should be in seconds. Okay. So the current we're given here is 0.1 amperes, and time, we don't have time. So we need to find time. Yeah, we find this. So we equate this equation so that we have 2680 coulombs should be a product of 0.1 multiplied by a time in seconds. That means that our time is going to be 2680, all right, divided by 0.1, which equals to around 26,801 seconds. So when you divide this by 1 hour, okay, when you divide this by 1 hour, you know that 30,600 seconds, we're going to get around 7.5 hours. So you see, for this current of 0.1 amperes, we really need a lot of time to deposit 3 grams of silver. So the time that is required is around 7.5 hours.
While anodizing titanium at anode, the oxidation of titanium take place where it form TiO2 plus 4 hydrogen ion and 4 electrons are released, where the oxidation potential of the titanium is 1.066 volt. On the other hand, at cathode, the reduction of hydrogen take place. Your 4 hydrogen ion gain 4 electrons, forming 2 hydrogen molecule. As we know that the reduction potential of the hydrogen is 0. So in writing the overall equation, we can write that titanium react with through water molecule. Here we can cross the hydrogen ion and the electron on both sides of the reaction, so it forms titanium oxide and hydrogen gases form. Overall potential of the cell is the sum of the oxidation potential and reduction potential. So the sum of oxidation and reduction potential is 1.066 volt. As we know that the thickness of the layer of aluminum oxide is equal to 0.01 millimeter. To change it into centimeter, so we will divide it by 10, so it will be equal to 0.001 centimeter. The area, the length of each edge is equal to 10 centimeter, so the area is equal to L square, so it is equal to 10 centimeter square. So the area of the sheet is 100 centimeter square. To get the volume, so volume is equal to area multiplied by thickness. So the area of the sheet is 100 centimeter square, where the thickness is 0.001 centimeter, so we get the volume 0.1 centimeter cube. This is the volume of the thin coat of aluminum oxide deposited over the plate. So as we know that the density of Al2O3 is equal to 3.97 gram per cm cube. To measure the mass of aluminum oxide, so we will multiply density with the volume. So the density is 3.97 gram per cm cube, where the volume is 0.1 cm cube. We can cross the cm cube with cm cube and multiplying 3.97 with the 0.1, so we get 0.397 gram. This is the mass of a layer of Al2O3 deposited over the sheet. Now we know that by Faraday law, we know that mass is equal to Z into Q, where Q is equal to I, the current applied, multiplied by T for the time. So it is the product of current into time, where Z is equivalent mass or mass equivalent divided by Faraday constant. So we can write that M is equal to E, equivalent mass, divided by Faraday constant, multiply by ampere current, multiply by time t. We also know that mass equivalent E is equal to molecular weight of the substance divided by N. So we can write that, rearranging the equation for the T, we can write that T is equal to mass first of all putting for the equivalent mass, we can write that M is equal to molecular weight of the substance divided by N into F multiply by I into T. To determine the T, we will rearrange the equation, so we can write that T is equal to mass into N into F divided by molecular weight of the substance multiply by current in amperes. As we have given the sheet of aluminium, so Al2O3 has molecular weight 102 gram per mole, where in case of the reaction between aluminum and oxygen, so there is Al2 and aluminum has 3 plus charge, so it has lost 6 electron, therefore N is equal to 6. Faraday constant F is equal to 96,500 coulomb per mole of electrons, where the current I is given 600 ampere. Putting these values, so we can write that M is equal to 0.397 gram, where N is 6 mole of electrons. Faraday constant is equal to 96,500 coulomb per mole of electrons, where molecular weight is 102 gram per mole and the current is 600 ampere. So calculating the above equation, we get that the time is 3.75 minutes. For an electrochemical cell which consists of lead and zinc electrodes, so there is zinc and lead electrodes. And this cell, as we know, at anode oxidation take place and the oxidation potential of the zinc is greater than the lead, so the zinc will oxidize to Zn2 plus, will release 2 electrons, where the at cathode the lead ion Pb2 plus will gain the electron and will reduces to lead, because lead has greater reduction potential while zinc has greater oxidation. So we can write the overall reaction like that. zinc react with lead ion Pb2 plus forming Zn2 plus and lead. So the zinc oxidizes where the lead is reduces. So this is a galvanic cell showing the two half cells. One is oxidation half, the second is reduction half. In oxidation half there is zinc electrode dipped in the zinc solution, so zinc will oxidizes and form Zn2 plus. So this is anode. At oxidation take place over here, zinc will leave electron at the electrode, so here anode has negative charge on it because the cell is galvanic cell. On the other hand, there is reduction in the second half, so the reduction of the lead take place, so lead from the solution move toward the electrode. Pb2 plus gain electron and deposited in the form of Pb. So there is positive charge over the cathode. The electron will move from the anode toward the cathode. This is the flow of electron. There is a salt bridge made of sodium nitrate NaNO3, so the nitrate ions will move toward the oxidation half while the sodium ions will move toward the reduction half. So this is the diagram for the galvanic cell showing the oxidation of zinc and reduction of lead.
In this problem, we are given with a galvanic cell, and we can see the galvanic cell here in this image. And we have 4 parts of this question. In the first part of this, we are asked to complete the drawing by adding any components essential for a functioning cell. So here we can see that we have 2 compartments, and we can assume that one of them is anode and one of them is cathode, and the anode and cathode are not leveled here, and we have to level that, and that's another part of this problem. But let's first complete the drawing by adding the essential part, which is a salt bridge. So without a salt bridge, a galvanic cell is incomplete, because in that case there will be an imbalance of the ions in 2 of the compartments, and that will create a short circuit of the cell, and it will eventually end up producing any more electron or current. So for the salt bridge, we actually add a U-shape tube here, and in this U-shaped tube we have an inert electrolyte solution. In this case, since we already have nitrate ions in the cell, so we can use any nitrate solution, and in this case we will use sodium nitrate. So we can write down sodium ion and nitrate ion, that will this salt bridge. So that's the essential part we are missing in this galvanic cell. Now in the second part, we are asked to level our anode and cathode. So from here, so we have to identify the anode and cathode. We can identify that from the flow direction of the electron. So from here we can see that the electron is flowing in this direction, and we know that electrons always go from anode to cathode since electrons are being produced in anode. So we can say that our aluminum strip here is our anode, and our cobalt strip here is our cathode. So these are anode and cathode, and we are also missing the sign of the anode and cathode. And as we know that electrons are being produced in anode, that means the sign for the anode will be minus. And since the charge for the cathode is plus, we have to put a plus sign here. We are also asked to indicate the ion flow direction. So since our electron is moving in this direction, these electrons will go here to neutralize cobalt 2 plus ions. The cobalt ion will go in this direction, and at the same time producing electron here in this aluminum strip, and the aluminum Al3 plus ions are being released to the solution here. And the aluminum ions go through this solid bridge here, and they come in a direct contact with the cobalt ion. In that case, we will not have the electron flow in this direction. So we have to prevent this aluminum ion from going through this solid bridge, and for that our nitrate ions from the solid bridge will come down in this direction, and those nitrate ions will react with aluminum to neutralize them or to keep them in the solution. The direction for the nitrate ion will be in this direction, and for the aluminum ion it will be in this direction. In our part C of the question, we have to write down a balanced equation for the cell reaction. So first we have to write down the anode and cathode half reaction. So our anode half reaction with the oxidation of aluminum metal. So aluminum metal will become Al3 plus ion by giving up its 3 electrons, and our cathode half reaction will be cobalt 2 plus will take up 2 electrons to become neutral cobalt. So this is our anode and cathode half reaction, and but to write down the overall cell reaction, we have to have a balance in our number of electrons in cathode and anode half reactions node. And from here you can see that to make them a same number, we have to multiply the anode half reaction by 2, and we have to multiply the cathode half reaction by 3. 2L 2L3 plus 6 electron, have 3 CO2 plus 3 times 2 6 electron, and 3 cobalt. So now we have 6 electron in both cases, and add these two equations up, and when adding up we'll have these 6 electrons, and these 6 electrons will cut off, and the overall cell reaction will be 2 aluminum plus 3 CO2 plus equal to 2L3 plus 3 cobalt. So that's our overall cell reaction. And finally, if we have to write down the cell notation for this, so our anodic half reaction will be aluminum metal being converted into Al3 plus, and we have to give this vertical line in between these two to separate their phase. So this is our anode half cell, and then we will place the solid bridge notation in between anode and cathode, and then we'll start writing down the cathode half cell, and that will be our cobalt 2 plus in aqueous form, phase change to cobalt, solid cobalt. And this is our cell notation for this galvanic cell.
For a cell notation where copper oxidizes into Cu2 plus ion and it come towards the 1 molar solution. On the other hand, iron Fe2 plus in 1 molar solution Fe3 plus in 1 molar solution Fe3 plus in 1 molar solution reduces to Fe2 plus in 1 molar solution at platinum electrode. So in this, at anode, as we know, oxidation take place, so the copper oxidizes into Cu2 plus, releasing 2 electrons. On the other hand, at cathode, reduction take place, so 2 ferric ions Fe3 plus gain the 2 electrons released by the copper and it change into 2 ferrous ion Fe2 plus. As the E oxidation of the copper is minus 0.34 volt, as the reduction potential of the copper in the electrochemical series is given, that is 0.34 volts. So when we writing the oxidine, we will change the sign, so the E oxidation of the copper is minus 0.34 volt, while the E reduction of the ferric ion is plus 0.77 volt. To write the overall reaction, we will add the above two reactions. So overall reaction is like that copper react with 2 ferric ion. We can cross the electrons on both sides, so it form Cu2 plus and 2 ferrous ion Fe2 plus. E of the cell is equal to E cell is equal to E oxidation plus E reduction. So E oxidation is minus 0.34 volt, while E reduction is 0.77 volt. So we can subtract 0.34 from 0.77, so we get the potential, that is 0.43 volt. This is E naught, standard potential of the cell. So this is the solution to part A. Now in part B, we have given the concentration of the copper Cu2 plus, which is equal to 1 molar, while the concentration of the Fe3 plus ferric ion is also 1 molar, while the concentration of ferrous ion Fe2 plus is 5 molar. So initially there is 1 molar, and when 5 molar is added, so the total concentration of the ferrous ion become equal to 6 molar. Now we can calculate E cell is equal to E naught minus 0.0592 over n log of Q, as Q is equal to the concentration of the product over the concentration of reactants. So we can see that in the cell. On the product side, there is the concentration of the Cu2 plus ion raised to the power their number of mole, that is 1. There is Fe2 plus ion which has 2 moles, so raised to the power 2, divided by, on the reactant side we has ferric ion Fe3 plus raised to the power their number of mole, that is 2. So putting the values, E is equal to E naught is 0.43 volt minus 0.0592, where N is the number of electron lost and gain, so N is equal to 2. We can write 2 over here, and log up instead of Q, we can write the concentration of copper, iron and iron Fe2 plus divided by Fe3. So putting the values direct, we can write the concentration of copper is 1 molar, while the ferrous ion is 6 mole square, divided by the ferric ion is also 1 molar square. We can calculate E. E is equal to 0.43 volt minus 0.0592 divided by 2 multiply by log of 6. So when we divide 0.0592 by 2, it become equal to 0.0296, and log of 6 square is equal to 36. Log of 36 is equal to 1.5. Now multiplying 1.5 with 0.0296, so we will get that E is equal to 0.43 volt minus, multiplying these two, we get it is equal to 0.046. So E is equal to 0.476 volt. This is the cell potential for the concentration when the concentration of the ferrous ion is 6 volt. Now in the part C we have given the concentration of copper, that is 0.1 molar, also of the ferric ion 0.1 molar, and the ferrous ion is also 0.1 molar. So the concentration of each is 0.1 molar. Again, using the same equation, we will write that E is equal to E naught is 0.43 volt minus 0.0592, where N is equal to 2, and log of the concentration of copper ion is 0.1 molar, multiply by ferrous ion 0.1 square, divided by the ferric ion is 0.1 molar square. So we can cross 0.1 with 0.1. We will take only log of 0.1. So we will write that E is equal to 0.43 volt minus 0.0592 divided by 2 is equal to 0.0296, and log of 0.1. So E is equal to 0.43 volt minus 0.0296, where log of 0.1 is equal to minus 1. So E is equal to 0.43 volt minus multiply by minus plus 0.0296, adding both, so we get that E is equal to 0.4596 volt. This is the potential of the cell. So from the calculations we get that this concentration is greater, so cell cell C has greater potential. Then all, as cell A has potential 0.043 volt, while cell B has a potential of 0.389 volt. In an electrolytic cell where electrolysis of copper bromide take place, so the copper bromide ionizes, forming cupric ions and bromide ions. At anode, the oxidation of the bromide take place, so the bromide ion oxidizes, forming bromine liquid and releasing the electrons, while at cathode copper ion reduces, gain 2 electrons into copper metal. There is a positively charged electrode connected to a voltage source. So the positively charged electrode is called anode, because this is an electrolytic cell. Anode has positive charge on it, while the negatively charged electrode is called cathode. Cathode has negative charge over at an electrolytic cell. Oxidation take place at anode while reduction take place at cathode. So the copper ion from the solution move towards the cathode, where it gain electron and is reduces to copper, while the bromide ions from the electrode moves toward the anode, where it oxidizes and forming bromine molecule. Here the electron moves from the anode through the external circuit toward the voltage source, and the electron from the voltage source moves toward the cathode. The net reaction or overall reaction for the two is that copper ion react with two bromide ions, forming copper and bromine.
Okay, this is sort of an odd problem. I've never been asked to do definitions before, but I guess we can do definitions together. We have 4 substances to define, or 4 terms to define. First is enthalpy of solution. And this is going to be represented by delta H SOLN. And this is pretty easy. It is the heat that's either generated or absorbed, generated for exothermic or absorbed for endothermic, when a known quantity known quantity or known amount of a solute is dissolved in a known quantity of solvent. Pretty simple. Second term is heat of hydration. Heat of hydration. Which our reference material calls HYDR. And that's just exactly what it sounds like. It's the heat change associated with the hydration of a substance. And that is when water molecules are associated with a substance. Third term is lattice energy. Let's go with a light blue. Lattice energy. And lattice energy is the energy required to dissociate, vaporize, whatever you want to call it, 1 mole of solid ionic, a solid ionic compound completely, and it has to be into gaseous ions. Okay, one more. I'm going to check, make sure my camera's on, and it is. And last but not least, heat of dilution. Also, exactly what it sounds like. It is the heat change that occurs during the dilution process. Pretty simple. Thanks for listening.
So for this problem, we're given an equation and the heat of that reaction. So the equation is hydrogen gas yields 2 moles of atomic hydrogen gas. And the heat of this reaction, the delta H, is equal to positive 436.4 kilojoules per mole. And we're supposed to find the heat of formation for atomic hydrogen. So we know that the heat of formation, or that the delta H of this entire reaction can be expressed as, or expressed through the heats of formation for each of the reactants and the products. So the heat is equal to the heat of formation of H minus the heat of formation of H2. So for this case, the heat of formation of hydrogen gas, of diatomic hydrogen gas, is 0 because it's an element. So we know that the heat of this entire reaction is equal to twice the heat of formation of atomic hydrogen, because in this case there are 2 moles of H within the reaction. So all we have to do is divide the heat of the entire reaction by 2, and we get that our final answer is equal to 218.2 kilojoules per mole.
This is a pretty simple problem. We're going to be given 3 alcohols, methanol, ethanol, and N-propanol, and we are going to be given the heat of combustion for 1 gram of material. So let's do first methanol. For methanol, which has a chemical formula of CH3OH, we are given that 1 gram of ethanol will liberate, where's my number? Has negative 22.6 kilojoules. So that will translate into negative 22.6 kilojoules per gram. Okay, now we want to convert this to kilojoules per mole. And to do that, we're going to use the molar mass. So for molar mass, the molar mass for CH3OH is 32.04 grams per mole. I'm just going to add that right here, 32.04 grams, and that's methanol per mole. And the answer for this will be negative 724 kilojoules per mole. Okay, now let's switch to purple and look at ethanol. And ethanol's chemical formula is C2H5OH. You don't always see it written in that way, but that's okay. And I'm going to put its molar mass right here, 46.07 grams per mole, because we're going to do the same thing for each of these. And we are told that upon burning 1 gram of this, negative 29.7 kilojoules per that 1 gram are released. So we're going to set this problem up exactly like we set the other one up. Negative 29.7 kilojoules per gram and 46.07 grams per mole. Still dealing with 3 sig figs here. So when I do my math on this one, I get 1,370 kilojoules per mole. Okay, last but not least, let's go with the dark blue. We have M-propanol, which is C3H7OH, and this has a molar mass of 60.10 grams per mole. And we are given that it releases 33.4 kilojoules per gram. And as you probably guessed, this is going to be set up exactly like our other problems. Negative, oh, did I forget to put my negative on this last one? Negative, I hope you caught that, negative. There we go. Fixed. Negative, let's go back to black, 33.4 kilojoules per gram and 60.10 grams per mole equals negative 2,010 kilojoules per mole. And that's reported to 3 significant figures. Problem solved.
So this question asks us to calculate the heats of combustion for some reactions. And the first reaction is a combustion of ethylene. So as always, our strategy is going to be to find the sums of the heats of formations of the products, subtract the heats of formations of the reactants. We can eliminate oxygen from this problem because the heats of formations for all elements are 0. So, on the left, or on the right, with our products, we have 2 moles of CO2, and the heat of reaction of CO2 is negative 393.5 kilojoules per mole. We also have 2 moles of liquid water, and the heat of formation of that is negative 285.8 kilojoules per mole. And then we have the C2H4 as our only reactant. So we have to subtract that out, and the heat of formation of that is 52.53 kilojoules per mole. And when you plug all of that into your calculator, you will get that the delta H for this reaction is negative 1,411 kilojoules per mole of reaction. So that is the answer to part A. Now the reaction for part B is a combustion of H2S. So just like last time, we're going to find the sum of the heats of formations of the products and then subtract out the heats of formations of the reactants. And we can ignore oxygen as well. So just like last time, we have 2 moles of water. The heat of formation of that is negative 285.8 kilojoules per mole. We have 2 moles of SO2. The heat of formation of SO2 is negative 296.81. And then finally, we have to subtract out 2 moles of H2S. And the heat of formation of that is 20.1 kilojoules per mole. So that'll yield us the heat of this reaction. And when we plug all of that into our calculator, we will get that the final answer is negative 1,124 kilojoules per mole of reaction. And that is the final answer.
This problem is going to look at using standard enthalpies to calculate heats of combustion. And we have 2 equations. Our first equation is H2 plus O2 yields H2O. And then we'll balance this equation. This is liquid. States are important because it will depend on what we're going to look up here. Okay, now we're told in this problem to look up our standard enthalpies of formation in a table that's referenced as Appendix 3. And that one was pretty easy to find for this. I'm going to switch colors. And I'm going to tell you the standard heats of enthalpies of formation. 0 for hydrogen, 0 for oxygen, and for liquid water, it is negative 285.8. And these are units of kilojoules per mole. Okay, so here's the equation we're using right here. Delta H, and in this case it's combustion, is going to equal the sum of the products. Well, we only have one product, so it's going to be negative 285.8 times the 2. There's our products. And then looking at our reactants, it's just a 0, so I'm going to stick a 0 in there just to make it a little easier. And our answer is negative 571.6 kilojoules per mole. That's as simple as this is. The hardest thing is keeping track of signs. Okay, next let's do our second equation, which is 2C2H2, and that is a gas, plus O2. And our products, we have, I think I have 5 of these. Double check. I got 4 carbon dioxides. And the last thing I have is 2 liquid H2O. Okay. So again, I'm going to write down, I'm going to make a little squiggly line right here. I'm going to switch colors to Let's go with this blue. And I'm going to write down what I look up for each one of these standard enthalpies of formation. Starting here, I have positive, I'll put a plus there, 226.8. I have a 0 for O2. I have negative 393.5. And just like that water up there, I have negative 285.8. So those are my values. And although those are kilojoules per mole. Now remember, it's always products first minus reactants. That's probably the biggest problem I see. So for this, we're going to start with our products. And this time I'm going to put 4 times negative 393.5, and that's kilojoules per mole, but I'm going to leave it off because I'll run out of room. And then we're going to add to that 2 times our negative 285.8. There's our products. Now for our reactants, we're going to take 2 times, I'll go ahead and put my plus there, 226.8, and I'll go ahead and put the 0. Okay, and when you're done doing your math on this one, you will find that your answer is negative 2599.2 kilojoules per mole. It's on my calculator. Yep, 2599 kilojoules per mole. There's the answer.
So for this problem, we're given 2 parts, and for part A, we're supposed to calculate the heat of formation for negative chloride ions given the following chemical reaction. So we know that the delta H for this entire reaction is negative 74.9 kilojoules per mole. And we're going to take advantage of that to find the heat of formation for the negative chloride ion. So we know that we can express this delta H as the following. The heat of formation of the negative chloride ion plus the heat of formation of H plus minus the heat of formation of the reactants. The only reactant in this case is HCl. So we know from the problem that in aqueous solutions that the standard enthalpy or the heat of formation for H plus is going to be 0, so that takes that out. And we also know that the heat of formation for HCl is equal to negative 92 kilojoules per mole. And given that there's only 1 mole of HCl in this equation, we can re-express the heat of formation of the negative chloride ion as the following. When we plug the numbers into this equation, we get that the final answer, or that the heat of formation of negative chloride, is equal to negative 167 kilojoules per mole. So that is the answer to part A. Part B. Now we have the neutralization equation, and we know that the heat of formation for the OH, the negative, or the hydroxide ion, is equal to negative 299, or negative 229.6 kilojoules per mole. And we're supposed to find the enthalpy of neutralization. So in this case, the entropy of neutralization is just the heat of reaction of the neutralization reaction. And so we can just write that reaction as the following. because that is the neutralization reaction for hydrochloric acid. So the important thing to note here, however, is this isn't the final net equation, because there are some spectator ions. For example, both Cl- and K+ are spectator ions, so they can be eliminated. So the final, or the net equation, is just going to be H+ plus OH- yields H2O. So from there, we can just use this equation and find the heat of reaction, and that can help us find the heat of neutralization. So once again, we know that the heat of formation for H+ is 0, so that isn't going to be needed in this problem. So the heat of neutralization is going to be the heat of formation of H2O liquid minus the heat of formation of the OH- ion. And when we plug those numbers in, and there's only 1 mole of H2O and OH-, we know that the heat of formation for water is negative 285.8 kilojoules per mole. And we know that the heat of formation for the hydroxide ion is negative 229.6. So the two negatives cancel out, and we simply add 229.6 kilojoules per mole. When we add those two together, we get the heat of neutralization is negative 56.2 kilojoules per mole. And that is the final answer.
Okay, here's a super easy problem. It's a super easy Hess's law, and we're asked to calculate, let me get through here, make sure I'm saying this correctly. We are asked to calculate the heat of decomposition. So we're going to find our delta H for this. And there's a table in our reference material. You can look at these tables anywhere, and you might not get the exact same values, but you'll get close. We are going to take the sum of the delta H's for our products and subtract from that the sum of the delta H's for our reactants. So it's product minus reactants. Don't forget, because that's probably the biggest problem that people have. So our heat of the reaction will be, we're going to use these two first. And I'm going to bracket those. I don't really need to do that, but I'm going to. So I look up the calcium oxide on a table, and I get negative 635.6 kilojoules per mole. Were there coefficients, I'd have to multiply those by a coefficient. And I'm going to add to that the CO2, and make sure you check the sign. That is negative 393.5. Now I'm going to subtract from that, and I'll just put it like that so it looks pretty, the calcium carbonate, which is negative 1206.9. 1206.9 kilojoules per mole. And that's a negative right there. So I've got a negative, and when you add a negative and negative, when you have a negative to a negative, then you're going to add that. So plugging numbers into the calculator, I guess I should have done this already. I've got negative 635.6 plus negative 393.5. I'm going to add to that 1206.9, and I get 177.8. and that will be in units of kilojoule per mole. That is just about as easy as a Hess's Law problem can be.
So this question asks how we can measure the heat of formation for Ag2O and CaCl2 from their elements. So the first step is to write the composition reactions for both of these compounds. So for Ag2O, the composition reaction is 4Ag plus O2 yields 2Ag2O. And so to find the heat of formation for Ag2O, all you would have to do is find the delta H for this reaction and then divide it by 2, because 2 moles of Ag2O are produced. So that's how you would do Ag2O. For CaCl2, it's a little bit simpler. Once again, we write the composition reaction, and we get that Ca plus Cl2 yields CaCl2. And for this, because only 1 mole is produced, you would just find the delta H, and that would equal the heat of formation for CaCl2. And that is the final answer.
We're going to think about hydrogen peroxide. And one thing we know about hydrogen peroxide, it decomposes to form water and oxygen. This is the reaction that occurs. And we know that negative heats of formation tend to be more stable. They're more stable than positive. And H2O2 does have a negative. This does have a negative heat of formation. So why does it decompose? Well, let's think about that. All we have to do, if we look up the H2O liquid, that has a standard heat of formation of, let me check here, water is negative 285.8 kilojoules per mole. And that's a liquid. Hydrogen peroxide has the heat of formation of negative 187.6 kilojoules per mole. So H2O is more negative, therefore more stable. This is more negative, therefore more stable. So this reaction is one that will go spontaneously. And we'll learn later about particles, but right now we'll just know that that reaction wants to proceed.
So this problem asks us to predict the value of the heat of formation for certain elements. So part A is about bromine. So bromine gas. So for bromine gas, the heat of formation is going to be greater than 0 kilojoules per mole. And the reason is because some heat or energy is required to turn bromine from a liquid to a gas. So energy is required. Hence, heat of formation is greater than 0. But for bromine liquid, the heat of formation is just going to be 0 kilojoules per mole. And the reason why it's less than bromine gas is because bromine liquid is in its natural state, so no energy is required. Part B is about iodine. So once again, we have iodine gas and iodine in its solid state. And in its solid state, the heat of formation is also 0 kilojoules per mole. Because like bromine liquid, iodine in solid is its natural state. In contrast, when you have iodine gas, the heat of formation will be greater than 0 kilojoules per mole because energy is required to go from a solid to gas. And that is the final answer.
All right, so for this question, we're asked to compare the standard enthalpies of formation of liquid water and gaseous water, water vapor. And to do this, you can look up these values in an appendix or just a list of standard enthalpies of formation lists that you can find online. So under standard conditions, the changes in enthalpy of formation of these two, for liquid water, it's negative 285.8 kilojoules per mole. And for gaseous water, it's negative 241.8 kilojoules per mole. So liquid water will be the more negative change in enthalpy of formation.
So for this question, we're supposed to find the heat of this reaction, given that we have two other chemical equations, and we know they are heats of reactions. So the two chemical reactions that we know are the following. The heat of this reaction is negative 1,669.8 kilojoules per mole. And the second chemical reaction that we have is the following. And the heat of this reaction is negative 822.2 kilojoules per mole. So once again, when solving these kinds of problems, it's very important to write out all the equations so that you can identify mole ratios and see which chemicals and compounds need to be on the left side versus the right side. So the first thing that we want to find is this first reactant, which is 2 moles of aluminum metal. The only equation that has 2 moles of aluminum metal, or any moles of aluminum metal for that matter, is the very first one. And it's already on the left side, like we want the desired equation, and there's already 2 moles. So this equation remains unchanged, and that's the final equation that we're going to need for the first one. Now for the second one, we want to find Fe2O3, or iron oxide. And we see that the only iron oxide in both these equations is right here. Now, while there's 1 mole, which is what we want, the problem is that it's on the products, not the reactants. And so to correct for that, we want to multiply this by -1. Now, I know that even though I may not look at iron or the Al2O3 that's on the right side, that this must be the answer, and these must be the final equations, because those are the only 2 conditions that satisfy the reactants. But just to quickly verify, we can also see that this will work out. The 2Fe, when we multiply by -1, will show up on the right side, and the Al2O3 is already there. And in this case, these 2 oxygens will cancel out because this one move, the second one will move to the right side once it's multiplied by -1. So now all we need to do is add up the 2 delta H's that we saw. So we add a negative 1,669.8, and then we subtract that with negative 222.2, and that will yield a final answer of negative 847.6 kilojoules per mole, and that is the final answer. So we're given 2 allotropes of oxygen, O2 and O3, and we're supposed to find which is more stable at 25 degrees Celsius. So we know that the heat of formation for O2 is equal to 0 kilojoules per mole. While for O3, it's 142.2 kilojoules per mole. So immediately off the bat, we can tell that the reaction to form O3 is going to be endothermic, which means that it requires energy to get to O3. And when there is energy required to form something, it means that the bonds are at a higher energy level. And that means that O3 is more unstable because when you put energy into a system, higher energy levels result in instability. So because O2 has a lower enthalpy, we can see that O2 is more stable. And that is the final answer.
Super easy problem. We are given, I believe, 6 substances, and we have to identify which ones do not have a standard enthalpy of formation of 0 at 25 degrees. And here they are. NaS. That one is 0, so that's not one of them. Second, Neg. That one's also 0. Remember, the standard enthalpies of formation are 0 for any substance that's in its most common elemental state. Here's one. It's methane. That one is not equal to 0. That one's not 0. S8, unless you looked at your charts that you have, you would probably guess that's one of them, but that one is equal to 0. HgL, that is, look at the periodic table, that one's 0. Last but not least, we have H. And of course, that one is not equal to 0 because hydrogen is diatomic, so the H2 would be equal to 0. But that's not what we were given. So these are the two that would not be equal to 0.
All right, so for this question, we're discussing Hess's law and how heats of formation can be found by using the change in enthalpy of a reaction. So first of all, the change in enthalpy of a reaction by using Hess's law is basically equal to the sum of the changes in enthalpy of the the products, heats of formation of the products minus the sum of the heats of formation of the reactants. This makes sense because the heats of formation are their own reactions, and it's those reactions, the heats of formation, it makes sense that we're adding them because when we're forming something, the heat of formation is going to be a product of that specific product. And it makes sense that we're subtracting the heat formation of the reactants because say in this case, the heat of formation of C2H6 has a heat of formation of such and such. Well, in our case, for our reaction, C2H6 isn't in the product side. It's on the reactant side. So we can just give this a negative value to put this on the reactant side. So that's why it makes sense that we're adding the heats of formation of the products and subtracting the heats of formation of the reactants. And by doing such, we're basically adding and subtracting the reactions that form those products and reactants to get the overall change in enthalpy of the reaction. So in this case, this reaction, this combustion reaction, if we can measure the change in enthalpy of the reaction, and we know the heats of formation of 3 out of 4 of our reactants and products, then we can find the heat of formation of whichever one we don't know. In this case, it would be 3 times the heat of formation of water plus 2 times the heat of formation of CO2 minus our reactant, so minus 5/2 heat of formation O2 minus heat of formation C2H6. So if this is known, this is known, this is known, and this is known, then we can solve for this. And that goes for any of the products and reactants. All right, so for this question, we're talking about Hess's law. And Hess's law is, because enthalpy is a state function, the change in enthalpy that occurs when reactants are converted to products in a reaction is the same whether the reaction takes place in one step or in a series of steps. In other words, no matter what the path is, if you know the 2 points, the beginning and end, you know the change in enthalpy of the reaction. So an example of this would be, say we have reactant A, which can become product B. And let's say the enthalpy of this reaction is equal to 5 joules. Then we have another reaction where B is the reactant and it produces C. And say the enthalpy of this reaction is 10 joules. We can then say that A to C, the change in enthalpy of that reaction is equal to this reaction plus this reaction, 15 joules. So as long as we can add reactions together and the reactants and the products cancel out, so in this case, adding these reactions together would yield this, but the B's would cancel out, yielding just A converted to C. And because it's a state function, we can just add them together. Because no matter the path, whether it be this or simply this, the change in the enthalpy of the reaction is the same, 15 joules. Now, this would be useful in the case, say, for whatever reason, we couldn't do the reaction A to C. We couldn't, maybe it's dangerous, I don't know, maybe we don't have the reactants necessary, who knows. What we could do is we could just figure out the change in enthalpy of A to B and B to C, perhaps being more doable to figure out the change in enthalpy for A to C without ever doing that reaction.
So this question asks us to write the equation for calculating the enthalpy of reactions. So for all chemical reactions, you can find the delta H of that reaction using this equation. Delta H of products minus delta H of reactants. And so for defining each specific term, delta H of the reaction is the total enthalpy of the reaction or heat of reaction. The delta H of products is the enthalpy of formation for each individual product multiplied by the number of moles for each product. And then the delta H of the reactants is the enthalpy of formation for each reactants, and taking account for the fact that there may be multiple reactants and multiple moles for each reactants. So that is the equation you use for every single thermochemical equation.
All right, so for this question, we're discussing the standard enthalpy of reaction, which is represented by this here. This is the change in entropy, the change in enthalpy. This indicates standard state, and this, of course, represents the reaction. And basically what the standard enthalpy of a reaction is, it's the enthalpy of a reaction carried out under standard conditions, represented by little degree sign.
So this question asks us to find how standard enthalpies of elements and compounds are determined. So for elements, it's simple. The standard enthalpy is always 0. For compounds, it's a little bit different. So let's say we have a synthesis reaction of A plus B yields C. And C is a compound and A and B are elements. Obviously, trying to find the heats of formation of A and B and subtracting the heat of formation of the products minus the reactants isn't going to be useful because A and B, the standard enthalpies of those are 0 because they're elements. So the way that you would do this is you would have to determine the standard enthalpies of C experimentally by finding how much energy is either absorbed or released in this equation. And typically, given that it's a synthesis reaction, you typically see there would be exothermic and some heat is released. But this specific value would have to be determined experimentally and not theoretically. And that is how you would solve the standard enthalpies of a compound.
All right. For this question, we're defining what a standard state conditions are. So standard state conditions are just conditions that we create as a standard so that we can compare experimental conditions between experiments. So for the standard state conditions, the pressure is usually 1 atmosphere. Liquids and gases have to be pure. Solutions are at 1 molar concentration. Temperature is usually at 25 degrees Celsius. And if you have a solid, we assume that the most stable allotrope or form of that solid is being used. We also assume that gases behave ideally. And this is all represented in a little degree sign next to, say, change in enthalpy of the reaction. That means that this reaction happens at standard state conditions. But very important here is usually the pressure and the fact that the temperature is usually at 25 degrees Celsius.
Okay, we are given a quantity of 85 milliliters, 0.0 milliliters of 0.900 molar hydrochloric acid is mixed with 85 milliliters of 0.900 molar KOH. This is put in a constant pressure calorimeter and we have a heat capacity of 325 joules per degree C. The initial temperatures of both solution is equal to 18.24 degrees C. Find TF. The heat of neutralization is equal to negative 56.2 kilojoules per mole. And we're asked to assume that the density and specific heat are the same as water. which is 1.00 grams per milliliter and 4.184 gram J over G degrees C respectively. Okay, I think we can do this one without too much trouble. Let's take a look here. We've got we're going to have to figure out how many moles we have. So our Q for the reaction is going to equal our moles times our heat of neutralization. And that is going to equal 85.0 milliliters times 1,000 milliliters per liter times 0.900 moles per liter times 56.2 kilojoules per mole. So the heat will be 0.085 times 0.9 times 56.2 is 4.2, I'll round later. Okay. So we know that the Q of the reaction is going to equal my Q of my system plus Q of my calorimeter. So this will be a negative of a negative 4.2993. I should have started this way over here. Will equal my mass of water. I should have figured this out up here. I'm going to have to erase this and do a little bit more work first. My mass of my system, which is water, is going to be 85 milliliters plus 85 milliliters times 1 gram per milliliter equals 170 grams. Okay, and my delta T will equal TF minus 18.24 degrees C. Okay, now I can set this up. So I'm going to have negative 4.2993. I'm going to leave my units off because otherwise it's going to get too busy. Will equal 170 grams times 4.184 times TF minus 18.24 plus what was it, 325? 325 times TF minus 18.24. Okay. Let me do some math here. I'm going to also have to, this was kilojoules, so I'm going to have to there we go. So I'm going to have 4.2993. 4.2993 equals, and this will be 170 times 4.184 is 711.28x minus 12973.7 12973.7 plus 325x minus 5928. Okay, so let me combine my x terms here. 711.28 plus 325 will be 1036.28x equals, and here I have that'll be on that side. Then I'll have 4299.3 minus 5928 plus 12973.7. Holy cow, that's wrong. Oh, I took a times there, my bad. 4299.3 plus 12973.7 minus that should be plus again. Plus 5928 is 23,201. X equals 22.39 degrees C. And I think we're done. Okay, we're going to do an easy calorimetry problem. Let's write down what we're given. We have a sample of magnesium that's 0.1375 grams. And the magnesium is going to be burned in a constant volume bomb calorimeter. My heat capacity of the bomb calorimeter is 3,024 joules per Celsius degrees. And my delta T for the reaction, for the combustion, is 1.126 degrees C. And that's how much, that's my temperature increase, because this is going to be combustion, this is going to be exothermic. Heat's given off. Exothermic. Okay, they're actually a pretty simple problem. We are asked to find the heat given off as kilojoules per gram and as kilojoules per mole. So we'll solve this one and then just convert grams to moles. Simple. Very good. So you could start this problem however you want it. I'm going to go ahead and start it with I'm just going to write my heat given off, my energy given off is going to be equal to my temperature increase. Then I'm going to multiply that by my calorimeter constant, J per degrees C, cross off as I go. And then I know that I had 0.1375 grams of magnesium. Get done with this, and I believe I got, I erased it, but I'm going to have to change it, 24,760 joules per gram, which of course is equal to 24.76 kilojoules per gram. So there is the answer in kilojoules per gram. Very simple. Next, we're just going to take our 24.76 kilojoules per gram, and we're going to convert our kilojoules to grams using the molar mass. Magnesium of 24.31, multiply that by 24.31, grams go away, and I'll get like 602. Oh, I already did kilojoules on that one. I don't have to do that. Okay, so I got 602.0 kilojoules per mole of magnesium. And that's my second answer. Very good. We're going to be applying Hess's law. Let me make sure my screen's on. So here's what's going to happen, and I'll start this on the next page. We're going to be given 3 equations, and they're going to be thermochemical equations. They'll be, it's not very well written. They'll be thermochemical equations, so they will have a heat term. We'll be given a desired or our target equation, and then we're going to rearrange and combine three equations to get the target. So that's our goal. Let's begin. Okay, I took the liberty of writing these down. And I want to make sure, again, my camera is still on. Okay, so let's look at these equations quickly. I sort of hate doing this because I'd rather you were paying attention and writing them down. So we've got methanol, graphite, H2, and O2. Notice we have a couple fractions here that can happen. So in our first equation, methanol plus oxygen yields CO2 and H2O. And then graphite, that's what you're writing with if you're using a mechanical pencil or any kind of pencil, plus oxygen yields CO2. Hydrogen and oxygen yields water. And here's our heat terms. Notice that they're all negative for our 3 given equations. And here's what we want. This is important. We want graphite plus hydrogen plus oxygen yields methanol. And we need to find the heat term. Let's begin. So I'm going to write 1, 2, and 3. And we're going to put our equations in. Okay, I'm going to start with equation number 2 because graphite is on the reactant side for my target and it's on my reactant side here. So I'm going to start with my graphite plus my O2 yields CO2. And since I didn't do anything to this, I'm going to leave my delta H as exactly 393.5 kilojoules per mole. Okay, one equation done. Now I'm going to look at equation 2. I would like to get, and I think I'll switch colors for this. For equation 2, I want to get my methanol on the product side. So I'm going to flip, if you will, this equation. These 2 products are now going to be my reactants. Let's write them down. CO2G plus 2H2O. And on my product side, I'm going to have CH3OH plus 3 over 2 O2. And my delta H, I also have to flip my sign. So now this is going to be positive 726.4 kilojoules per mole. And last but not least, we have our water. And for this reaction, you'll notice I do not have water in this reaction. So the waters here have to cross out, which means I need to keep this water on this side. You could also look and see that I need hydrogens here. Doesn't really matter, as long as you get the right one. So my delta H for this will also be the same. It's negative 285.8, ran out of room there, kilojoules per mole. And I'm almost done, but I have one more thing I need to do here. Let's go to green. Now, I don't have a sufficient amount of water here. So I need to multiply this whole equation, including the heat term, by 2. So I need to multiply this by 2. 2 times negative 285.8. And I will end up with 2 hydrogens, 1 oxygen, and 2 waters. And now I can cross out those terms that appear exactly the same on both sides of the arrows. So 2 waters and 2 waters, goodbye. 1 carbon dioxide and 1 carbon dioxide, goodbye. Now the oxygens are a little trickier. Please note that I have 1 plus 1. I have 2 oxygens right here. And I have 1.5 oxygens right here. So I'm left with an excess of 1/2 O2 on this side of the equation. So I'm just going to put a single line through all these because I took care of that. Now, my final equation, I've got this term, C graphite, I have 2 hydrogens, and I have half of an oxygen, and that satisfies all 3 of these. And my only product is CH3OH. Now, for the mathematical part of this, we are going to take positive 726.4, these are all kilojoules, plus kilojoules per mole, negative 393.5, plus 2 times negative 285.8. Again, all kilojoules per mole. And when I'm done here, let me find my paper, I got negative, I'm going to switch colors, negative 238.7 kilojoules per mole. Let me write my answer right here. Negative 238.7 kilojoules per mole. These aren't hard, but just keep organized. I like to try to line my arrows up best I can.
So this question asks us to find the mass of water in a container when a piece of aluminum is added, and we're given some numbers about this entire situation. So the key fundamental thing in solving this problem is the idea that the energy is going to be, heat energy is going to be conserved. And the way we're going to go about solving this problem is through the fact that the amount of heat that is released by aluminum into the water is equal to the heat that is gained by the water, and as a result, the subsequent temperature change in water. So first, we want to find the heat change of aluminum. So we're going to use the equation that heat is equal to mass times specific heat capacity times the change in temperature. So we know that the mass of aluminum that was put into this water was 12.1 grams. We also know that the specific heat capacity of aluminum was 0.900 joules per gram centigrade. The final component, which is the change in temperature, can be calculated from the fact that initially the temperature of the aluminum was 81.7 degrees centigrade, and then the final temperature of the water, which includes the aluminum, was 24.9. So then we can multiply that by final minus initial temperature. Now, when you put all of that into your calculator, you'll get that the answer is negative 618.55 joules. So in other words, this number is the change in heat of aluminum And so we know that in order to conserve the heat in the system, or the energy in the system, that the heat gained by water must be the exact opposite of this. In other words, Q of H2O must have been a positive 618.55 joules. And now we're going to simply do the exact opposite of what we did with aluminum, because now we know that 618.55 joules, which is the heat that the water gained, is going to be equal to the mass of the water times the specific heat capacity of water times the change in temperature of the water. So we know that the mass of the water can be calculated by simply dividing the heat times the specific heat capacity and the temperature. So what are the specific heat capacity and the change in temperature? Well, the specific heat capacity of water is 4.184 joules per gram centigrade. And we also know that the change in temperature is a positive 1.5 degrees centigrade, because it goes from 23.4 initially, and after the aluminum is added and the system comes to an equilibrium, it's 24.9, so a additional 1.5 degrees centigrade. With those numbers, we then plug that into the final equation. And then the final answer that we get after all of this work is 98.56. So that is the total mass of water that was initially in the container, and that's the final answer. So this question asks us to calculate the amount of heat liberated in kilojoules when some mercury cools down. So in order to find the total amount of heat, we're going to use the equation that heat is equal to the mass times the specific heat capacity of that substance times the change in temperature. So we already know two of these things. We know that the mass, 366 grams of mercury, and we know that that change in temperature is going to be 12 minus 77 degrees centigrade. The last thing that we need is we need the specific heat capacity of mercury. And the specific heat capacity of mercury is equal to 0.139 joules per gram centigrade. Then all we need to do is multiply these three values together. And when you multiply all three of these values in your calculator, you will get that the amount of heat that is liberated in this chemical reaction is equal to negative 3.31 times 10 to the 3 joules. But because it asks for the answer to be in the amount of heat liberated, not in the delta H, and it asks for it to be kilojoules, the final answer is going to be in positive and in kilojoules, which is why it is going to be 3.31 kilojoules. And that is the final answer. So this question asks us to find the specific heat of silver given a piece of silver and its heat capacity. So for this piece of silver, we know that its mass is 362 grams and its heat capacity is 85.7 joules per degree centigrade. So the units for a specific heat capacity is joules per centigrade times gram. And this means how much energy is required to raise a gram of a substance by 1 degree centigrade. So given these values here, all we need to do is simply take the specific heat of that silver piece and then divide it by its mass. And then when we do this calculation, we get that the specific heat capacity of silver is 0.237 joules over gram centigrade. And that is the final answer. So this question asks us some fundamental things about calorimetry and calorimeters. So first, to define calorimetry, calorimetry is just the study of heat changes and how they relate to a system, surroundings, how heat is absorbed or released, etc. And so two different types of calorimeters that are commonly used. First, a bomb calorimeter. So what's special about how this calorimeter is used is that it is constant volume, which means that whenever it's measuring heat change of a system, it maintains its volume. And the second is constant pressure calorimeter. And as its name suggests, the way it works is that when the calorimeter detects and measures heat changes, it maintains the pressure. And the last part asks us why it's important we know the heat capacity of the calorimeter. And the reason why is because whenever you're doing an experiment and you're using the calorimeter itself will absorb heat. And what this means is that that will be a source of error, and some heat will be lost in your experiments because it's absorbed by the calorimeter. And unless you take that into account, there will always be some unaccounted loss of heat within your experiments. So it's very important to know the heat capacity and to measure how much heat is lost.
So here we have a fun little chemical reaction taking place where we have hydrogen gas and chlorine as a chloride in its gas form are reacting to form hydrochloric acid in its gas form. And we see their equations balanced, which is great. We have two hydrogens, two chlorides. This 2 coefficient applies to the hydrogens and chlorides, meaning that the equation is perfectly balanced. We have 2 hydrogens, 2 chlorides on both sides of the reaction. And we're told a few different things about this reaction. So first of all, the enthalpy, which we can think of as being the heat released, that's a good thing to think about, is negative 184.6 kilojoules per mole. And if it's negative, that normally implies that heat is being released. Okay, so we're also told some of the other units of different measurements that are going on. The pressure is 1 atmosphere, and the temperature is 25 degrees Celsius. We're also told that in this reaction we have 3 moles of hydrogen reacting with 3 moles of chloride. So how do we progress from here? Because the first thing it asks us to do is calculate the work done in joules. So how do we actually calculate work? Well, in a physics context, we understand work as being some force with some displacement. And we can apply this with chemistry as well, because when we think about the movement, this is going to be the volume. Because if something is changing in the size it occupies, there's going to be a change in the distance that something is covering. And then pressure is going to be our force here. So that would mean the force that is being exerted against like the outside of a container. For example, if we have a bike tire, there's going to be a certain pressure in the tire due to the gas that is pushing against the actual tire that is in the rubber part that's on the outside. So this is how we define work and actually solve for it. So how do we progress from here? Well, we're given the pressure at 1 atmosphere. We're given the temperature, which is not really relevant for this part of the question. So we have the pressure. That's something good to think about. And then we can think about the volume. That's the only other thing we really need to solve this problem. So one of the best ways to go about solving for volume is using an ideal gas law, where we have PV equals nRT. And just for a really quick review, P is equal to pressure, V is equal to volume, N moles, R is a constant, and T is temperature. So let's rearrange the equation to solve for V. So V equals nRT divided by P. So how do we progress from here? Well, we know the moles of the reactants. We have 3 moles of H2 and 3 moles of Cl2. So let's just write the volume of the reactants. So we're trying to find the change in volume, remember? And change is always, it's a comparative term. So the change in volume here is just going to equal Vf minus Vi, because we're looking at the change, the difference. So the volume of the reactants, which let's just use R. Let's make it a little more easy on us, lowercase r. So the volume of the reactants is equal to N, which is 6 moles in total, right? 3 plus 3. Let's just write it as 3 plus 3 for moles, just so we're not just skipping things mentally and we don't get confused down the line. We can keep R as it is. I would recommend doing so because it's a constant, right? Temperature, we're told it's 25 as well. Okay? And then the pressure is going to be 1. So that's how we'd find the volume of the reactants. But before we solve this, let me just point something very interesting out to you. Now, if you look at the final, we have to look at what the variables will be. So we're setting it up the same. It's the same equation. We have N for the moles. So we're told that we have 3 moles of H2 and 3 moles of Cl2. But if we look at the reaction, if this is 3 and this is 3, then to balance this 2 here, we have to change this to be a 6, because we have to have the same amount of elements on one side as the other. So it really turns out we'll have 6 moles of HCl. So just before we even solve for this, just see what is going on here. And I'd like you to try and predict where this is actually going to go. Now we can just cross off R from this equation because it's the same in both. It's a constant. We could even cancel out the rest of this as well if you wanted to, because it's the same for both equations. So if we were to set them equal to one another, these would cancel out. So if we were to apply things, so delta V is equal to Vf, which is 6. Of course it's not 6, but this is just, I'm just trying to prove something to you very quickly. Minus 6. Now it could be 100 minus 100, it could be 10,000 minus 10,000. The point I'm trying to get across is it doesn't matter, because even if we plugged in R as its official value, we plugged in the 25, and then we divided by 1, which of course divided by 1 doesn't do anything, meaning if we actually didn't cross these off and just solved for the equation by plugging everything in manually and you get a more accurate, relevant numbers, it would still equal 0 for change in volume. It's still 0. Now, if we know anything about arithmetic, we know that anything multiplied by 0 is 0. So the pressure is 1 times 0. is 0. So what is the work done in kilojoules? 0 kilojoules is the amount of work done here, because we don't have any change in volume. So there can be no work done. It doesn't matter how hard that pressure is pushing against the container it's in. If there's no change in volume, there's no work done. So that is the first part of the problem. The work is 0 kilojoules. Okay, so that was a little bit of a conceptual test. So it makes us think we're going to do a big calculation. But if we understand the terms and the concepts applied here, we can just understand that work is going to be 0. There's no actual calculation. It's more of a conceptual understanding. So now we need to calculate delta U. That's the next part. So delta U of the reaction is what? Now we have to know some other equations to proceed here. And in case you're wondering, there's some textbooks which refer to delta U as delta E. They're both just referring to the energy in a system, internally in a system, before it's being acted on by whatever else. So, and this is the change, right? Delta, the triangle, means change. So what are some equations that would be very useful? Well, we know that delta U or delta E, let's just use delta U because that's what the problem asks for. Same term though. It'd be like spelling gray with an E or an A. It's the same thing. An equation would be Q plus W. Now here's where things get a little bit fun. Here's where we have some fun. This is a fun thing because we don't actually have to do very much arithmetic. And without any more hints, I'm going to give you another equation where we have the enthalpy is delta H, but there's another equation that we know. So delta H is equal to delta E, or let's use delta U. It doesn't really matter again, but let's just try and make things a little less confusing. So it's equal to delta U, that's a U, plus pressure multiplied by the change in volume. Now this is where we get to do a little bit of substituting. This is where we can see that pressure multiplied by the change in volume is just W. So this is just equal to delta U plus work. All right, we're just substituting work in for this variable here. That's all we're doing. Just a little bit of substitution because we see that things equal. And we already know the work is 0. So we know that delta H is equal to the work done in the system, which makes perfect sense. So delta U is equal to the same as our enthalpy given to us at the very beginning of the problem, negative 148.6 kilojoules per mole. It's that simple for this problem. It makes it seem like it's more hard and there's more than it's cracked out to be, but there's no actual change in pressure or temperature given to us at the beginning of the problem. And because it's set up the way it is, everything has to stay the same as far as the volume is concerned. So this is going to be our second answer, or we can just know that enthalpy will be the same thing as the internal energy or the internal energy of the system, which is delta U.
So for this question, we're given three chemical equations and given their delta H's, and we're trying to find the delta H of a specified chemical reaction. So for this first equation, we know that the delta H is negative 393.5 kilojoules per mole. The second equation is this, and the delta H is negative 285.8 kilojoules per mole. And the final reaction is this. And then the delta H is negative 3,119.6 kilojoules per mole. And the desired reaction, or the desired equation, is 2 moles of carbon graphite, 3 moles of hydrogen gas, and then on the right side, 1 mole of C2H6. So when you're solving these types of problems, it's very important to write down each equation so you can clearly see the relationships in terms of the mole ratios and what's on the left side versus what's on the right side. So let's look at the desired equation and go step by step. The first thing we want is 2 moles of carbon graphite on the left side. And when we look at the first three equations, the only equation that has any moles of carbon graphite is the first one, right here. It's on the left side, just as we want it to, but instead of being 2 moles like we want in the desired equation, there's only 1 mole. So we're going to multiply this entire equation, including the delta H, by 2. And that will give us the 2 moles of carbon graphite that we want on the left side. Now, the next thing that we want is 3 moles of hydrogen gas. Now, once again, the only equation that contains any moles of hydrogen gas is the second one. And instead of being 3 moles, it's only 1 mole. But because it's also on the left side, which is the correct side, the only thing that we need to do is multiply this entire equation by 3. And that will give us the 3 moles of hydrogen gas that we want. The last thing that we want to do is we want to get C2H6. Only the third equation contains C2H6. But there's 2 problems here. The first is that it's on the left side of the equation instead of the right side. So we need to fix that. But more importantly, there's 2 moles of C2H6 in the third reaction, while we only want 1 mole. So to correct for both of these things, we're going to multiply this by a negative 1/2, where the negative flips the side and the 1/2 decreases it to only 1 mole. So then the last thing that we need to do is we simply need to take into account for all of the delta H's that we multiplied to get the final delta H for the desired reaction. So we can express this as the following: 2 times negative 393.5 plus 3 times negative 285.8, and then minus 1/2 of negative 3,119.6. And then finally, when you put all of that into your calculator, you will get that the delta H for the desired reaction here is negative 84.6 kilojoules per mole. And that is the final answer. So this question asks us to calculate the amount of heat given off when 1.26 times 10 to the 4 grams of NO2 are produced, given that specific chemical equation. In that chemical equation, we know that delta H is negative 114.6 kilojoules per mole. And for that specific equation, 2 moles of NO2 are produced. So this is going to be the conversion factor that's going to be critical to the dimensional analysis we're doing. The problem with this conversion is that it's in moles of NO2 and not grams, which is our initial value. So we can just divide by the molar mass of NO2, which happens to be 46.01 grams. And since we have now converted to grams, we can then multiply by the initial quantity, which is 1.26 times 10 to the 4 grams of NO2. When you multiply that equation through, you're going to get negative 1.57 times 10 to the negative 4 kilojoules. But the final answer is not negative. The reason why is because this negative sign means that it's an exothermic reaction, and that means that 1.57 times 10 to the 4 kilojoules of heat were released. But given that the question asks for the amount of heat given off, and not simply for the delta H, we can get rid of this negative sign. And so the final answer is simply a positive 1.57 times 10 to the 4 kilojoules. So this question gives us a chemical reaction as well as the delta H of that chemical reaction, and gives us a certain series of conditions to explain how that delta H would change. So the delta H of the initial equation is negative 1,452.8 kilojoules per mole. So Part A says that the equation is multiplied throughout by 2, which means that there's double the amount of reactants and double the amount of products. In this case, whenever you multiply an equation, a chemical equation, by a certain factor, the delta H of that same equation is also multiplied by that same factor. So here, the delta H would just be twice of the initial equation, and that yields us our answer of negative 2,905.6 kilojoules per mole. The second part asks us to explain what would happen if the direction of the reaction is reversed, so that the products become the reactants and vice versa. In this case, the delta H would simply flip signs, because now every single operation that you are doing when you're trying to find the heat of formation of the products and the heat of formation of the reactants is flipped. So in this case, delta H would be a positive 1,452.8 kilojoules per mole. Now Part C explains what would happen if water vapor instead of liquid water is formed as the product. So in this case, what we need to do is we need to subtract out the heat of formation of liquid water and instead add in the heat of formation of water vapor. So what would you do is we would simply take the initial delta H, which is negative 1,452.8. We take this initial value, and then we would have to subtract out the heat of formation of liquid water, which happens to be negative 285.8 kilojoules per mole. And then on top of that, we would need to add in the heat of formation of liquid water vapor. So then we add 4 moles times negative 242 kilojoules per mole, which is the heat of formation of water vapor per mole. When we take all of this together, we get that the final answer is negative 1,277.6 kilojoules per mole. And so those are our 3 final answers.
Simplest question of the day. We are asked to evaluate this thermochemical equation and explain what this means. So for a thermochemical equation, we will recognize because it's going to have a heat term. And this is a negative heat term, which means that heat is, my delta H is negative 904 kilojoules per mole. And because it's negative, we know that this is an exothermic reaction. And when this reaction occurs as written, it would yield negative 904 kilojoules per mole. That's what this would, and we would interpret that in terms of our coefficients. Okay. And that's as easy as this one is.
So this question asks us to explain why, when writing thermochemical equation, it's important to indicate the physical state of each substance. So the reason is when you're trying to calculate the enthalpy or the change in heat of every reaction, the heat of formation for each substance, which is required to calculate the enthalpy or change in heat of reaction, is different based on whether or not it is a gas, liquid, or solid. So in other words, the heat of formation is not the same for different physical states of matter. So let's look at a classic example. This first equation is, of course, of ice melting. And the second equation is of water freezing. So, if we didn't know the physical states of matter, we wouldn't know whether or not this reaction is endothermic or exothermic. But because we know that it goes from a solid to liquid in the first reaction, or in other words, ice is melting, that this is an endothermic reaction, while when water is freezing, that is an exothermic reaction. So that is why it's so important to know the physical state of all substances on both sides of a thermochemical equation to find the enthalpy of each reaction.
All right, so for this question, we're talking about enthalpy and the enthalpy of a reaction. Enthalpy, which is denoted by a capital H, is equal to the internal energy plus pressure times volume of a system. The enthalpy of a reaction is the change in enthalpy, which can be shown as the enthalpy of the products minus the enthalpy of the reactants. Or it can be shown as the change in internal energy plus the change in pressure times volume. So using this, we're also asked to find a situation where the heat of a system is equal to the change in enthalpy of a system. And the answer is, at constant pressure, the change in enthalpy of a system is equal to the heat of the system. And we can prove this. We have to start with, change of enthalpy is equal to the change in internal energy plus the change in pressure times volume. Now remember, At constant pressure, the pressure doesn't change, it's constant. So we can move this delta in because the pressure is going to be the same. So it's going to be the pressure times the change in volume. We also know that the change in internal energy is equal to work plus heat. So now we can write change in enthalpy is equal to work plus heat plus P delta V. Now, we're also given that we know that work is equal to negative P delta V. So we can write that the change in enthalpy is equal to negative P delta V plus the heat of a system at constant pressure plus P delta V. These, of course, cancel out, and we are left with the change in enthalpy is equal to the heat of a system at constant pressure.
So this question asks us to calculate the work when a mole of water vaporizes. So in order to find the work done, we're going to use the equation work equals negative pressure times change in volume. So obviously, when we have a mole of water that is a liquid, its volume is 0, but when it becomes a gas, there is some definite volume that it has, and so that will represent the change in volume. So the first step that we have to do is we need to find that volume. And in order to find that volume, we're going to use the ideal gas law, which says that PV equals nRT. And we can rewrite that so that it solves volume for us, which is nRT over P. And we can plug in the numbers that we know into this equation. So we know that we're dealing with 1 mole of water, as given to us in the problem. We know that R is a constant that is equal to 0.0821 liters times ATM over mole K. We know that the temperature, as given to us in the problem, is 100 degrees Celsius. We need to convert that to Kelvin, so we just add 273 to convert it to Kelvin. And then finally we divide by the pressure, which is given to us as 1 atmosphere. And when you plug that all in to the equation, we get that the volume of the gas is 31 liters. So now we can use this volume and plug that into our initial equation, which is that work equals negative pressure times change in volume. Well, we know that the pressure is 1 atm. We know that the final pressure is 31 liters, like we just calculated. And we know that the initial volume had to be 0 liters because it was not a gas at that point. So then, we know that the work is equal to negative 31 liters ATM. However, this isn't the conventional unit for work, and so we need to change this. We need to change this into joules, and in order to do that, we'll use a conversion factor that in 1 liter ATM, there's 101.3 joules. And when we multiply this out and take advantage of this conversion factor, we will get that our final answer is negative 3.1 times 10 to the 3 joules. And that is the final answer.
In this problem, we're asked to find work. And we are asked to find work when we are given 50.0 grams of tin. And our temperature is given as 25 degrees Celsius. And our pressure is given at 1.00 atmospheres. Let's make a note that this is 298 K. And we are going to want to convert this to moles pretty quickly. So what we're going to do is we're going to use PV equals nRT to solve for V. We're going to solve for V. And then we're going to use W equals negative P times delta V to solve for work. Okay, so when we're doing, let's call this step 1 and this step 2. When we're doing step 1 to get N, we're going to have to convert, let me switch colors, 50.0 grams of tin using the molar mass, which I wrote down here, 118.7 grams per mole. This gives me 0.421 moles of tin. So that's the number that we're going to go right here. So for step 1, V is going to equal moles, which is 0.421 moles, times R, which is 0.0821 LATM per kmol, and then temperature, which we said was 298 Kelvin, and divided by 1, and I think it was probably 1.00, keep our sig figs good, 00 atmospheres. Get done here, and we have 10.3 liters. Okay, and then for step 2, W is equal to negative, our pressure was, let me switch colors here. Erase this and I'll put this down again in a different color. Make it a little easier to look. So for step 2, W equals negative P, which is 1.00 atmospheres, times our delta T, which is 10.3 liters, equals negative 10.3. And that'll be liter atmospheres. Now, our last step is we're going to convert our negative 10.3 liter atmospheres to joules using the 101.3 joules per liter atmosphere. And if I do my math on this, I got a 1.04, I think it was times 10 to the third joules, which is the answer. Oh, and it's negative. I forgot to bring my negative over. So negative. In fact, let me make that a little bit clearer. This is something I do a lot when I'm doing these problems, is forget to keep track of my sign. So it's a negative 1.04 times 10 to the third joules.
So this question asks us to change the energy of a gas given some work is done to compress it and given some heat is given off. So the important equation here is that the change in energy of a system, or in this case the gas, is equal to the heat energy plus the work done onto it. So in this case, Q, or the heat energy, is negative 26 joules. And the reason why it is negative and not positive is because it's given off to the surroundings, which means that that's 26 joules of heat that the system loses. And in this case, the work is positive 74 joules. And the reason is because if the gas compresses, it means that positive work must have been done in order to shrink the volume of the gas. And from there, it's pretty straightforward. When you plug the two values in to your equation, your final answer will be positive 48 joules.
So for this problem, we're focusing on a gas expansion. For this problem, we're told that gas does 325 joules of work on the surroundings. So if the system is expending energy to do work on the surroundings, it's losing energy. So that's why this number is negative. We're also told that the system gains heat from the surroundings. If you're gaining heat, that's positive. You're adding energy to the system. So now we're also told we need to find the change in internal energy of our gas. And in this case, our gas is our system. So of course, if you follow the usual formula, the change in internal energy is equal to the work plus the heat. we know that the change in internal energy of our system is equal to negative 325 joules plus 127 joules, which we know will be equal to negative 198 joules. So because of this, we know that our system is overall losing energy because this number is negative. That means it's expending energy.
For this problem, we're going to be looking at combining two chemical equations in order to get an enthalpy change for a related transformation. So we are given two chemical equations. I'm going to write them both down. So for the first, we have S. Second is also S, but these are two different forms. These are allotropic forms, rhombic and monoclinic. Again, two different allotropic forms of sulfur. Both of these are reacting with, whoops, wrote my G in the wrong spot, reacting with oxygen to produce sulfur dioxide, and these are both gas. Now my delta H for each reaction, they're very close, but they're not exactly the same. This is negative 296.06, and this is negative 296.36. I'm going to have to, I can't quite get those fitting on there. I'm going to set these up just a smidge differently. I'm going to give you my delta H for the reaction right here. Negative 296.06 kilojoules per mole and negative 296.36 kilojoules per mole. And we are asked to combine these equations and find the change in enthalpy, the delta H, for transforming the rhombic to the monoclinic. Okay, in order to do that, we're going to call this equation 1 and equation 2. We're going to look at these two equations and arrange them so that we can get this as a result. So for equation number 1 contains the rhombic, so we're going to leave this equation exactly as written. I didn't leave room for my O's there. That's okay. And I have my SO2G and my delta H is negative 296.06 kilojoules per mole. Okay. Make a nice big negative there. Now my second reaction, let me switch colors here. My second reaction, I'm going to have to, if you will, flip this, which means my products will become reactants, and that means I have to change my sign. So SO2 is now my product, or excuse me, my reactant, and my products will be S, and I'm just going to write mono and O2. And my delta H for this will now be positive 296.36, and that's kilojoules per mole. And then I need to add this whole equation. So when I'm adding this equation, I need to cross out my O's that are on each side of my arrow, cross out my SO2's, and I get the rhombic, the monoclinic, and when I have negative 296.06 plus positive 296.36, just a little low on space here. I'm going to write that down underneath here, and then we can make it a funny little color. So if to get my heat, I'm going to take a negative 296.06 plus my positive 296.36, and my answer is 0.30 kilojoules. So I'm going to write my answer up here again, 0.30 kilojoules. Ooh, one page.
So this question asks us to calculate the work done in joules given a certain gas expands under different pressures. So before we get into any individual parts, the important formula in these situations is that work is equal to negative pressure times change in volume. And so before we enter some parts, there are some key, we already know what the change in volume is, because the volume goes from 26.7 milliliters to 89.3 milliliters, which means that the change in volume, you can put this in your calculator, is going to be 62.6 milliliters. And it's positive because it gains volume. So part A asks us for the work when the gas expands against a volume. So in this case, work is 0. The reason is because in a vacuum, the pressure is 0. Second one asks us against a constant pressure of 1.5 atm. So in this case, we can just plug that into our equation. And you multiply that by the change in volume. And when you plug that in your calculator, you're going to get negative 0.0939 liters times atm. In this case, I just automatically converted the milliliters to liters because that's going to be more useful for a conversion. But this isn't our final answer because it asks for joules to be our final unit. So then we have to convert this to joules using this conversion factor, which is at 101.3 joules is equal to 1 liter times atm. And when you multiply that together, you get negative 9.5 joules. We can do a similar thing for part C, and once again we use the formula that work is equal to the negative change in volume times pressure. And in this case, the pressure is a constant 2.8 atm. And once again, the change in volume is 62.2 milliliters. And when you multiply those figures together, you'll get that the answer is negative 0.17528. When you use sig figs, that'll get rounded down to 1.7 or 1.8, but we'll ignore that for now. Once again, we have to use our conversion factor. And when we do that, plug that in the calculator, you'll get that the final answer is negative 17.7 joules. But when you use proper sig figs, you'll get negative 18 joules. So this question gives us a series of chemical reactions and asks us to determine whether the work is done on the system or by the system. So the first reaction is this. And in this reaction, the work is done by the system. And when I refer to the system, I'm referring to the particles that are within the reaction. And in this case, work is done by the system because the system is expanding, which means that it is doing work. So because it is expanding, it is done by the system. Now, the second reaction is this. And in this case, the important thing to note here is that while both sides of the reaction contain only gases, on this side of the reaction, we have 3 moles, and on this side, we only have 2 moles. And for that reason, it is compressing, which means that work is being done by the surroundings in order to compress the system. Or in other words, the system is doing a negative work. Part C is a much longer chemical reaction. And it is this. In this case, once again, what we notice here is that there is a gas on the right-hand side of the equation, meaning that the system is once again expanding. And just as same as part A, if the system is expanding, it means that it is doing work on the surroundings in order to gain volume, which means it is done by the system. The final chemical reaction is this. And in this case, there's actually no work that's being done in the system, because both on the right and the left hand side of the chemical equation we have only gases, and on the left hand side we have 2 moles, and on the right hand side we also have 2 moles. So because there is neither compression nor expansion, there is no work done either by the system or the surroundings.
This problem is a quick discussion of the first law of thermodynamics. So we are given the following information. The internal energy of an ideal gas depends only on its temperature. So the internal energy, I'm going to abbreviate energy as NRG, depends only on temperature. That's given in the problem. We're going to do a first law analysis of the following process. We have an ideal gas, and it's allowed to expand at constant temperature. That'll be important, constant temp, in a cylinder against atmospheric pressure. Okay. And then we're asked to respond to 3 different questions. So I'll probably just do each one separately and then erase it and come back. Our first question is, does the gas do work? Does the gas do work on the surroundings? And that's actually a pretty easy question. Does the gas do work on the surroundings? And again, that's, in my opinion, that's a pretty easy one. Yes, because there's a change, we do have a delta V. So there's a change in volume. And if you'll remember, W equals minus P times delta V. So the first part is yes. I'm going to erase that. And then we'll look at our second question. Make sure I'm still recording here. And we are. For part B, the question is, for part B, let me find where I am here. Is there heat exchange? Is there heat exchange between the systems, between the system and surroundings? And if so, what direction is the heat exchange in? Okay, so this whole process takes place at constant temperature. Recall that we were at constant temperature, and the atmospheric pressure is constant. So the change in internal energy, our delta U, our delta U is equal to 0. And we know that delta U is also equal to our Q, either plus or minus W. Q plus or minus W. So in order for our work to be 0, Q and W have to be the same but opposite in sign. We said we do have work, and our work is negative. Work is negative. So our Q has to be positive, which means it's endothermic. Okay. So yes, there is heat exchange, and we did say the directions. Let me erase this, and we'll do our last one. This says, where is this? First C, what is delta U? Oh, I already told you that. Sorry, my bad. The delta U, because the temperature is constant, equals 0. So that one was pretty easy.
So this question asks about the definition of a state function. So state function means that it is path independent. What this means, that as long as you end at the same starting point and the same ending point, the value of a state function will always remain the same. So here are two examples of state functions. The first is potential energy. Potential energy as a state function is because it's only dependent upon the first or initial position and the later or second or final position. For example, if I have a suitcase that's on the ground, and then I move it up 10 meters, the difference in potential energy is derived solely based on the difference in height between the initial positions. Even if I bring it much higher and then lower it back down to 10 meters, the potential energy will always remain the same because it is only dependent upon the difference between the initial and final positions. Another classic example of a state function is displacement. Displacement is inherently based upon only the initial and final positions. For example, if we look at a beaker, and it has some markings, regardless of whatever goes in or out of this beaker, the displacement can be measured by the initial marking versus the final marking. And that's the only two measurements that matter. So let's say that that's the initial marking. And that's the final marking. Regardless of whatever I put in this beaker, if those are the initial and final, that will always be the displacement, which is the difference between those two positions. Now let's look at two examples that are not state functions. The first is distance. So let's say I have point A and I have point B. The distance between point A and point B is not a state function because it depends on the path you take. For example, this path is a much shorter distance than this path, which is why distance is not a state function. In a similar vein, work is not a state function because it is also dependent upon the distance that you move. Imagine trying to lug a piano from point A to point B. That's going to be much easier on this route compared to this route, because in this route you have to go much farther, which is why more work has to be done and why work is not a state function. So this question asks us to explain why decomposition reactions are endothermic and why combination reactions are exothermic. So let's first look at an example of a decomposition reaction where A goes to B and C. So endothermic means that you require energy in order for the reaction to occur. And in this case, it makes sense why energy is required for this reaction. It's because to go from A to B and C, you need to break the bonds within A to split them into two different compounds or elements, which is why the energy will be on the left side of the reaction, and is to why this reaction is endothermic. In contrast, when we look at composition reactions, where A plus B go to C, the reason as to why this is exothermic, or as to why heat is released from the system, is because the formation of new bonds within A and B that allow it to go into C release energy via heat, which is why the heat is on the right side of the reaction, and why this is an exothermic reaction as a whole.
All right, so for this question, we're asked to discuss exothermic processes and endothermic processes and give two examples of each. So to start, what's an exothermic process? An exothermic process is one where energy is a product. A reaction generates energy. In this case, the products have less energy than the reactants. So when you subtract the amount of energy of the reactants from the products, you'll get a negative number. So what's an example of an exothermic process? Well, burning a match, and melting an ice cube. So with burning a match, the excess energy created by this reaction is obvious in the form of heat and light. Melting an ice cube, you can see the excess energy in that the atoms of the ice cube, which were closely packed together, gained energy and are now able to move around more as water. All right, so for an endothermic process. An endothermic process is a process where energy is a reactant. Energy is required for the reaction to take place. In this case, the energy of the products is greater than the energy of the reactants. And when you subtract the energy of the reactants from the products, you get a positive number. So what's an example of an endothermic reaction? Well, freezing water into an ice cube and also condensation. Water vapor turning into liquid water. Now, in both of these cases, the molecules had more energy and then slowly lose energy. So for condensation, the water vapor molecules, had a lot of energy, and then when you reduced that energy, they got closer together and were able to form water. When you freeze water, the bonds, the molecules in the water were able to move pretty freely. They were still close enough together that they formed water, but they weren't frozen. And of course, when you freeze that water, they're basically stuck where they are. They don't have as much movement. They've lost energy. And actually, endothermic processes are associated with a cooling down, and which you can tell when things become frozen. They get colder, of course.
So this question asks us about which law thermochemistry is based upon, and thermochemistry is based upon the first law of thermodynamics, which essentially states that all energy is conserved within a system. So it is about the conservation of energy. A very classic example of a chemical reaction that highlights this is the combustion of wood. And so when we have the combustion of wood, the initial form of energy is the potential energy that comes from the bonds within the wood. And when we burn the wood or we combust it and we engage in a combustion reaction, that is then transferred into thermal energy and then subsequently heat that is emitted from fire. So even though the forms of energy change from potential energy to heat, the total amount of energy within the system is still the same. So for this problem, we're supposed to find the enthalpy change in kilojoules of a specific decomposition reaction, given that 66.8 grams of CO2 are produced. So the first step in solving this problem is to write the decomposition reaction. So we know that this specific reaction is that calcium carbonate decomposes into CaO plus carbon dioxide. So this equation is balanced. So now, in order to find the delta H of this specific reaction, we need to subtract the heat of formations of the reactants from the heat of formations from the products. So we can express that as the following. So the only thing that we have to do now, considering that each of the reactants and products is only 1 mole, is to find the heat of reactions for each of the following. And when we do that, we get the following. Negative 635 kilojoules per mole plus negative 393.5 kilojoules per mole. And finally, since we have to subtract a negative number, we change that to a positive sign, we add 1,207 kilojoules per mole. And when we add all of those together, we get that the entire heat of reaction is 178.5 kilojoules per mole. Now, we know that in this case, there was only 1 mole of CO2 that was produced. So we know that 178.5 kilojoules of heat per the reaction corresponds to 1 mole of CO2. However, we want to find it in terms of grams of CO2. So in this case, we need to multiply by the molar mass of CO2, which is 44.0 grams. We need to divide by the molar mass. So 1 mole of CO2 corresponds to 44.0 grams. And then the last thing we need to do is we need to multiply by the quantity of CO2 that we want to find. In this case, from the very beginning, we knew that that was 66.8 grams of CO2. And when you multiply all of that together, you get 271 kilojoules. And that is the final answer. And the first situation is we throw a softball up. So if you imagine a ball, and we throw it up, and this is its initial position, I, and this is its final position, F. So at I, it has kinetic energy. And the reason why it has kinetic energy is because it is moving. It has some kind of velocity, and the kinetic energy comes from that. Meanwhile, at the final position, or F, there is no kinetic energy because at the very top the velocity is 0, but it has potential energy. And that potential energy comes from gravity and its height. So the interconversion is from kinetic to potential. Part B, we have a flashlight and we turn it on. So at the beginning, we have potential energy. And this potential energy comes from the battery and the chemicals that are in it. And then when we turn it on, we have light, and light is a form of energy that combines both heat energy and kinetic energy. So the conversion here is from potential to light energy. Part C. We ride a ski lift to the top of a hill and then ski down. So let's first draw this hill. So if I take a ski lift up along this ski lift right here, the interconversion of energy here is that I'm gaining potential energy, and the reason why I'm gaining potential energy is because my height is increasing and I'm moving upward. And that, of course, is supplied by the work of the ski lift. So that comes from the ski lift. And then the second thing that happens is that when I get to the top of the hill, and I'm right here, and I ski down, I use all the potential energy that was given to me by the ski lift, and I transfer that into kinetic energy. Because when I go down, I have speed. So the interplay here is, once again, just like, or very similar to part A. It's from potential to kinetic. Finally, part D. I strike a match and let it burn down. Well, similar to part B, when I have a match before I light it, the potential energy comes from the chemicals and the materials within the match and the lighter. So that's what we have first. We have potential energy. And then when I light it, I have a fire, and that is a form of light energy plus heat. And then obviously when I let it burn down, even though there's no more potential energy in the match and I can't use it anymore, and there is no light energy because nothing is visible and the fire has gone out, what I have is heat. Because the fire emits heat, and that is the kind of energy that is produced. So the interplay is from potential energy to heat energy. So this question asks us about a truck that is moving and suddenly comes to a stop, and whether or not this violates the conservation or the law of conservation of energy. So let's draw what's happening right now. So we have a truck. Just assume this is a truck that's moving at 60 kilometers per hour. And then suddenly it comes to a full stop where it goes from 60 to 0 kilometers an hour. So evidently, there is a loss of energy from the point of view from the truck, because it has kinetic energy when it is going at 60 miles per hour, and when it comes to a full stop at 0, it has 0 kinetic energy. But this does not violate the law of conservation of energy, because this kinetic energy is instead transferred as heat. So when the truck comes to a full stop, it uses friction to go from 60 kilometers an hour to 0 kilometers an hour. And as a result, all that kinetic energy goes to heat, which is lost from friction as the tires slow the truck down. So no, energy is conserved within the total system. It just changes forms from kinetic energy to heat. So this question asks us about the fundamental principles between heat and thermal energy. So to start, heat is energy that can be gained or lost in a system. And heat can be transferred in between systems when certain conditions are met. Now this is different from thermal energy, which is derived from the movement of particles. What this means is that in a system, if particles are moving really quickly, there's high thermal energy, and when particles are moving very slowly, there's low thermal energy. And finally, the last question asks us about the conditions under which heat is transferred from one system to another. And heat is transferred when there is a difference or a change in temperature between two systems. As a result, heat will go from a system that is warmer to a system that is colder.
Given information we have we have a balloon with a diameter of 20 feet. We need to find how much weight could this balloon lift. Remember that a helium balloon can lift a mass equal to the different of the mass equal to the difference of the mass of air displaced and the mass of helium contained in the balloon. Calculations. Use the ideal gas equation and express the number of moles as the ratio of mass and molar mass. Then solve for mass. By using ideal gas equation, PV is equal to nRT. PV is equal to mass out of molar mass into RT. So M is equal to PVM divided by RT. We know that the balloon can lift the difference in in mass of air and mass of helium. So mass of air minus mass of helium is equal to PV, molar mass of air, divided by RT minus PV m helium divided by RT is equal to PV out of RT into molar mass of air minus molar mass of helium. So on so so once fully inflated we will assume that the balloon would become spherical with diameter of 20 feet. We can then find its volume. So we have delta M is equal to mass of air minus mass of helium is equal to PV out of RT into molar mass of air minus molar mass of helium. So by putting values we have here del M is equal to 1 atm divided by 1 atm into 118596 liter into 28.8 gram per mole minus 4.00 gram per mole into 1 kg divided by 1000 gram. Zero point 0821 liter pressure per mole per Kelvin into 25 plus 273 Kelvin. So delta M is equal to 120 kg. A 6-year-old boy weight less than 120 kg, so it is capable to lift a boy.
So the problem with this, you're going to see numbers, you're going to want to jump to math, right? You see a pressure, you see a temperature, it's asking you for volume, but there's a lot of information not given to you, so you have to kind of infer some things here. So inside the tire, we'll start with outside, right? So the outside is 1 atmosphere of pressure, and it's 22 degrees Celsius. It needs you to fill a tire so the gauge reads 5 atmospheres at that temperature. So the only thing you're doing is taking the gas and you're compressing it into a smaller volume. So that's what's going to be our key here. The issue, though, is that the gauge is going to read the difference in pressure, the difference between outside and inside. So what you technically need is 6 atmospheres of gas at that same temperature. So what you're doing here is essentially a Boyle's law problem, P1 V1 equals P2 V2. But without the numbers, we can't really figure it out. But what it's asking you to do is estimate the volume. So if you have a 1 liter sized tire, which you can estimate it as, you need 6 times its volume. So that's the estimate that you're going to be able to provide here. You're going to want to provide 6 times the volume of the tire. Because every time you put one of those pumps in, you're going to be compressing the gas, and it's going to be able to produce some pressure inside. So that's the estimate you're going to be able to provide, that it's 6 times the volume. Now the next one gets a little bit more tricky. It says the tire is pumped, and you're trying to fill it with it's 1 atmosphere at a time, but the problem is that the pump is 33% of the tire's volume, so you're only going to be able to provide it with 1/3 of that pressure at once. So after 3 full pumps, so that's 3 pumps, at 1/3 volume, you're only getting 1 volume. So you're only going to be able to fill it once over. Now remember, the gauge reads the difference between the inside and the outside. So if you're only provided 1 atmosphere, the gauge is going to read 0. Because at that point, after 3 pumps, inside and outside are equal, so the pressure inside will represent nothing.
Part A, the vapor pressure. The vapor pressure of mercury in fluorescent light bulbs is 1 multiply 10 raised to the power minus 5 standard atmospheric pressure ATM. We can estimate the diameter of the thin of the thin tube is 3.175 millimeter and 1/8 inches, and the typical length of office fluorescent tubes is 2 meters. The pressure inside fluorescent lamps is known to be known to be 0.003 standard atmospheric pressure and 25 degrees Celsius. Calculations. First, we need to find the volume of the cylindrical tube containing the mercury gas. So V is equal to pi r square, H is equal to pi 3.175 multiply 10 raised to the power minus 3 meter whole square into 2 meter is equal to 6.3 multiply 10 raised to the power minus 5 cubic meter is equal to 0.063 liter. Now find the number of moles of gas that could fit in the tube. So N is equal to PV divided by RT is equal to, we have values P1 standard atmospheric pressure into 0.063 liter is volume, and divided by R 0.0, R is general gas constant, R ideal gas constant 821 liter standard atmospheric pressure per mole per Kelvin into 25 plus 273 Kelvin is equal to 2.6 multiply 10 raised to the power minus 3 mole. Since partial pressure exerted by a gas is directly proportional to the number of moles, we can apply ratio and proportions to find the numbers of moles of mercury, Hg. So N number of moles of mercury, Hg, divided by total number of moles is equal to pressure of mercury divided by total pressure. Number of moles of mercury divided by 2.0 multiply 10 raised to minus 6 mole is equal to 1 multiply 10 raised to the power minus 5 standard atmospheric pressure divided by 0.0003 standard atmospheric pressure. So N number of mole of mercury is equal to 6.7 multiply 10 raised to the power minus 9 mole. Then the mass of the mercury vapor is 1.3 mg microgram or microgram, and note that some mercury remains as liquid. So the answer is 1 microgram.
Hello everyone. So what is given in this question? In this question, the term hyperbaric chamber is given. Hyperbaric chamber is given, and we have to find the trends in the relative solubility of the gases, and how the elevated pressure in the hyperbaric chamber used to decompression sickness. Let's see the exact concept to know the answer. So in this context, what is happening in this question? So hyperbaric chamber, this is basically mean that this is a kind of the chamber which is used to speed up the healing of carbon, speed up the healing of carbon monoxide, poisoning, gangrene, and stubborn wounds, infection in the tissues, that is starved for the oxygen. Not only that, when we compare the pressure in the hyperbaric chamber, so in this condition the pressure is nearly about 250 to 280 kPa, and in this condition when we have to make the separate arrangement, so what we get from this, we get the CO2, that is the most soluble form, and then after the CO2, that is the O2, then N2, that is the nitrogen, and the least soluble is, we can say, that is CO, that is the carbon monoxide, that is the least soluble. And in this case, the increased pressure of air, we can say, when the pressure is increased of air, so what happen? So it will force nitrogen and carbon monoxide out of the body. So this is the final answer to this question. Thank you.
Action, we are going to be looking at a thermochemical equation, and we'll be doing some super easy stoichiometry. Let's begin. The equation we're given is one of my favorites. I think every chemistry teacher uses this repeatedly to demonstrate various concepts. It is the production of ammonia from nitrogen and hydrogen. And the delta H for this reaction is negative 92.6 kilojoules per mole. Okay, we are given the following information. We have 1.26 times 10 to the fourth, quite a few, grams of ammonia being produced. So the question is, how much heat is given off? How much heat is given off? This is a pretty simple problem to do. Let's go with the green here. So we are going to go from grams of ammonia to moles of ammonia using the molar mass. And then we are going to use our heat term right here to get our kilojoules per mole. Let's begin. Go to a little brighter color here. So we're going to start with our 1.26 times 10 to the fourth grams, and that's ammonia. Got a little extra dot right there. I don't know how that got there. Okay. And the molar mass of ammonia is 17.04 grams per mole. And now I'm going to use my heat term, and it's negative 92.6 kilojoules. And now this is going to be per 2 moles of ammonia. That's an important thing to remember. When you do your math on this, you're going to get a negative 34,240 kilojoules. Okay, so I can report my answer to 3 significant figures. So here's how I'm going to report it, because I was asked how much heat is given off. So I have 3.42 times 10 to the fourth kilojoules of heat are given off. And notice I didn't use my sign on that. I really don't need to because I was asked how much heat is given off. Thanks.
Here we have a flask with a volume of 14.5 liter containing 1.25 mole of helium gas. We need to find the average distance between the helium atoms. Calculations. In reality, helium atoms will move randomly, so the distance between each other varies. However, to find the average distance, we can assume that the helium atoms are fixed and uniformly distributed throughout the entire volume. Moreover, we will assume that each atom is confined in a small cubes occupied by one helium atom using Avogadro's number. Using Avogadro's Ross number. V divided by atom is equal to 14.5 liter into 1 cubic meter divided by 1000 liter into we have 1.25 mole into 6.022 multiply 10 raised to the power 23 atoms divided by 1 mole is equal to we have 1.93 multiply 10 raised to the power minus 6 26 meter cube atom. Now we can find the length of the small cube partitions assuming that the atoms are at the center of each cube. Then the distance between each atom is just equal to the length of the side of each cube. V is equal to S cube. S is equal to V 1/3 is equal to 1.93 multiply 10 raised to the power minus 26 meter cube whole 1/3 is equal to 22.68 multiply 10 raised to the power 9 minus 9 meter. So S is equal to 2.68 nanometer.
So the question has to do with whether a sample of air would have a greater mass if it didn't contain water vapor or if it did contain water vapor. And if you thought of the water vapor as something that was just an additional component of the mixture in the sense that you would still have the same amount of air, then you would think, well, the water adds to the mass, but the water also adds to the pressure. We're talking here about water vapor, and in the sense of the ideal gas law, for example, the water vapor would not be any different than the molecules of oxygen or the molecules of nitrogen. So what we're really talking about here is replacing some of the nitrogen and oxygen molecules in the air with water molecules. See, at the same pressure, volume, and temperature, you'd have the same total number of moles of gas molecules. And so that doesn't involve additional molecules of water. That involves molecules of gaseous water, water vapor, replacing oxygen and nitrogen? Well, each molecule of oxygen has a mass of 32 AMU, and each molecule of nitrogen 28, and each molecule of water 18. So you're adding in lighter molecules. It would have a lower mass with the water molecules than it would if it was dry at the same PV and T.
We have the volume of balloon is 8.5 multiplied 10 raised to the power 8 liter. Temperature of minus 67.8 degrees centigrade, and pressure of 0.027 millimeter of mercury. We need to find part A, the mass of helium, and in part B, the volume when pressure is equal to 1.0 standard atmospheric pressure and T is equal to 23 degrees Celsius. Calculation for A, use ideal gas equation to find the number of moles of helium, He, then multiply it with the molar mass of helium to obtain the mass. Mass is equal to N. Molar mass is equal to PV out of RT into M. Mass is equal to we have 0.027 millimeter of mercury into 1 standard atmospheric pressure divided by 760 millimeter of mercury into 8.5 multiplied 10 raised to the power 8 liter into 4.003 gram per mole into 1 kg divided by 1000 gram. So 0.0821 liter atm per mole per Kelvin into minus 67.7 plus 273 Kelvin. M is equal to mass is equal to 7.2 kg. Part B, to find the volume when the pressure and temperature is changed. Pressure and temperature is changed. We can use combined gas law. The combined gas law is P1 V1 divided by T1 is equal to P2 V2 divided by T2. So putting values in the above combined gas law, we have values here 0.027 millimeter of mercury into 1 standard atmospheric pressure divided by 760 millimeter of mercury into 8.5 multiplied 10 raised to the power 8 liter divided by minus 67.8 plus 273 Kelvin is equal to, we have 1.0 standard atmospheric pressure into V2 divided by 23 plus 273 Kelvin. Now solve for V2 is equal to, we have V2 is equal to 8.5 multiplied 10 raised to the power 8 liter into 0.027 millimeter Hg into 1 atm standard atmospheric pressure divided by 760 millimeter of mercury into, we have 23 plus 273 Kelvin divided by minus 67.8 plus 273 Kelvin. divided by 1.0 standard atmospheric pressure. V2 is equal to 4.4 multiply 10 raised to the power 4 liter.
So it's not absolutely clear what this mass spectrum gives us, but if we take the intensity to be proportional to number of molecules or moles, rather than, for example, mass recorded at that molecular mass, then I estimate 4 units for the CH4, 1.5 units for the C2H6, and 2.5. So a total of 8 units, of which 4 is CH4. So it should be half of the total pressure if it's half of the molecules. And so 2.25 ATMs for the CH4. And then basically 3/16. That is, if we multiply the total to 16, then that goes to 3. Let me try that. 3 times 4.5 divided by 16 is, yes, again, times the total. So if these represent the fraction of the molecules, that's basically mole fraction times total pressure. And so that would be 0.84 ATMs. And then this would be 5/16 of the total. Again, that would be its mole fraction. 5 times 4.5 divided by 16, 1.41 ATMs. And so that does add up to 4.5 ATMs. That should
Given information we have generally the standard atmosphere is expressed in 1 ATM. So here 1 standard atmosphere ATM is equal to 101,325 Pascal. This value comes from the pressure exerted by a column of mercury exactly 76 cm high of density 13.5951 gram square centimeter in a place where acceleration due to gravity is gravity is 9.80665 meter per square second. Calculations by using the density of mercury equal to 1.35951 multiply 10 raised to the power 4 kg per cubic meter. The standard atmospheric pressure is calculated by the equation. So here we have pressure is equal to length multiply density multiply acceleration is equal to hgd is equal to, we have values 2.76 millimeter of mercury into 1.35951 multiply 10 raised to the power 4 kg per cubic meter into 9.80665 meter per square seconds is equal to 101,325 kg meter square seconds is equal to 101,325 Pascal. Part B. Using the combined gas law, P1 V1 divided by T1 is equal to P2 V2 divided by T2. Calculate the initial pressure from which the air bubbles started to form using the given values. P1 is equal to P2 V2 T1 divided by T2 V1 is equal to 0.973 standard atmosphere pressure divided by 18.73 degrees centigrade into 6V1 into 5.25 degrees Celsius divided by V1 is equal to 1.6364 standard atmospheric pressure. Calculations. The density of the lake is 1.02 gram per cubic centimeter. We can use the equation in part A to obtain the depth of the lake. Depth of the lake in meters. So we have 1.6364 standard atmospheric pressure multiply 101.325 kg meter per square meter per square seconds divided by 1 standard atmospheric pressure is equal to 16,508.23 kg meter per meter square per second square. So here length is equal to density into acceleration divided by pressure. By putting values, we have 1.02 multiply 10 raised to the power 3 kg per cubic meter into 9.80665 meter per second square divided by 16,508.23 kg meter per meter square per second square is equal to, we have 0.060 meter.
Okay, so we have these 3 flasks, and we're assuming that the valves are closed. We're told, let's see, the pressure in A is 4 atmospheres. What are the pressures in B and C? Well, B is 2 liters and A is 4 liters, so it's half the volume. I count 9 spheres in A and B each, so same number of moles. And so the pressure would be twice as great in, I'm sorry, that would be in B as it is in A. And so 8 atmospheres in B. And then in C, it's the same volume as A, but I count 12 spheres there. And so the pressure would be 12 ninths. It's a 12 to 9 ratio, the number of moles of gas. And so in C, I would have 5.3 atmospheres. And then after the valves are opened, I'm counting 9, and 9 is 18 plus 12 is 30. And so I've got 30 molecules total in 10 liters, and my reference in A was 9 molecules in 4 liters. And so the number of molecules has increased by a factor of 3 1/3, and the volume has increased by a factor of 2.5. So the pressure, the molecules have increased more than the volume. The pressure is going to increase by a factor of 1 1/3. So the total pressure after the valves are open will be 5.33. And A and B, let's see, those are the types of spheres, the red and green. I count 15 each. And so each of those makes up half of the total. And so each of them has a partial pressure after opening and mixing of 2.67 atmospheres, each one half of the total after the valves are opened.
Calculations. Since it is reacting with an excess of oxygen, we can assume that all the hydrocarbon is consumed. So we can find the number of moles of carbon from carbon dioxide produced, and the number of moles of hydrogen H from the H2O produced. This would give us the complete empirical formula. So here molar masses masses one mole of carbon dioxide is equal to 12.011 plus 2 15.999 is equal to 44.009 gram. And next we have 1 mole of H2O is equal to 1.008 into 15.999 is equal to 18.015 gram. So moles of carbon is equal to mole of carbon C is equal to 205.1 gram CO2 into 1 mole of CO2 divided by 44.009 gram CO2 into 1 mole of carbon divided by 1 mole of carbon dioxide is equal to 4.660 mole carbon. And next we have mole of hydrogen. Mole of hydrogen is equal to 168.0 gram H2O into 1 mole of H2O divided by 18.015 gram H2O into 2 mole of hydrogen divided by 1 mole of H2O. 1 mole of H2O is equal to 18.65 mole of hydrogen. So mole of hydrogen divided by mole of carbon is equal to 18.65. This is mole of hydrogen and 4.660, and this is mole of carbon is equal to 4. Thus the empirical formula empirical formula of the hydrocarbon. The hydrocarbon is CH4. CH4 to find the molecular formula we need to calculate the molecular mass using ideal gas equation. So ideal gas equation is here. PV is equal to nRT. PV is equal to mass out of molar mass RT. So molar mass is equal to mass RT divided by PV. So we need to find the mass of hydrocarbon. Mass of hydrocarbon initially present applying law of conservation of mass. This is just equal to the sum of masses of products minus that of oxygen that reacted. Mass of oxygen from CO2 is equal to 4.660 mole carbon into 2 mole of oxygen divided by 1 mole of carbon into 15.999 gram divided by 1 mole of oxygen is equal to 149.12 gram oxygen. So mass of oxygen from H2O is equal to 18.65 mole of hydrogen into 1 mole oxygen divided by 2 mole of hydrogen into 15.999 gram divided by 1 mole of oxygen. 1 mole of oxygen is equal to 149.19 gram of oxygen. Mass of hydrocarbon is equal to 205.1 plus 168.0 minus 149.12 plus 149.19 is equal to we have 74.79 gram oxygen. Now we can use the derived formula for molecular mass. Molecular mass is M is equal to MRT divided by PV is equal to 74.79 gram into 0.0821 liter ATM standard atmosphere per mole per Kelvin into 350 Kelvin divided by 6.63 standard atmosphere into 20.2 liter is equal to 16.05 gram per mole. Since the molecular mass is just equal to the empirical formula mass mass 12.011 plus 4 1.008 into the molecular formula is the sum of the empirical formula which is CH4. The hydrocarbon is known as methane.
Okay, this is question 159 from chapter 11. We have a constant pressure and a constant volume in this cylinder, and we're trying to find which one of these equations shows that the initial temperature is twice as much as the final temperature, so after the reaction. Okay, so usually what I think of things, what is be twice as much, I'm thinking of multiplication, I'm thinking of like the number 2, that stuff in general. So thinking of that helped me figure out which one of the answers was. So when I looked at these, I looked at the ones that were showing some sort of multiplication, and if the ones that weren't, that was not the answer for me. So A, I noticed it's A plus B reacts to make C. That is just showing me like a simple addition, I don't know, equation, I don't know, but I don't really see that it's showing it that's twice as much in the beginning, in the end. So I decided that A was not going to be one of the correct answers. Now for C, I can see the same thing. It's just A plus B reacts to make C plus D. And this really isn't going to show me that it's going to be twice as much in the initial for temperature than after. So I take out C2. Okay, now for D, we have A plus B reacts to make 2C plus D. Okay, so this 2C right here is showing like a 2. It's gonna and some multiplication. So you see that there could be the possibility of it being twice as much, but it wants it for twice as much in the initial, not the final temperature. And this is showing it to be final. So D is not going to be the answer, which leaves us with B being the answer. Okay, so we have A times B reacts to make C plus D. And this makes sense because it's showing the multiplication, and obviously when you're multiplying rather than just adding, you're going to have more of the temperature. So this is probably going to show that it's twice as much than the final temperature. So B is going to be your answer.
Part A, use the molar mass of nitrogen in kg per mole to the equations for root mean square and for most probable speed is shown below. So here most probable speed is equal to under root 2 RT divided by molar mass is equal to root mean square velocity root root mean square velocity or speed is equal to under root 3 RT divided by molar mass. Calculations here. The most probable speed is always slower than root mean speed, and it is evident to the calculated values at the same temperature same temperature 298 Kelvin. The most probable speed is equal to under root 2 8.314 joule per mole per Kelvin into 25 plus 273 Kelvin divided by 0.02802 kg per mole is equal to 421 meter per second. So here root mean square velocity or speed is equal to under root 2 8.314 joule per mole per Kelvin into 25 plus 273 Kelvin divided by 0.02802 kg per mole is equal to 5.5 meter per second. Part B, using the equation in Part A derive the formula to calculate the temperature T2. So here the most probable speed 1 divided by most probable speed 2 is equal to under root 2r T1 divided by molar mass divided by 2 RT2 divided by molar mass. Is equal to under root 2R T1 divided by molar mass 2R T2 divided by molar mass. And next we have most probable speed 1 divided by most probable speed 2 is equal to T1 divided by T2. T2 is equal to T1 divided by most probable speed 1 divided by most probable speed 2 whole square. Calculation substitute the T1 is equal to 300 Kelvin and the values of the most probable speed is speed in part B. So T2 is equal to 300 Kelvin divided by 500 meter per second divided by 1000 meter per second is equal to 200 Kelvin.
Okay, this is question 157 from chapter 11, and we have a root mean squared speed of a gaseous oxide is at 493 meters per second at 20 degrees Celsius. So what is the molecular formula of this compound? So the equation for root mean squared speed is RMS is equal to the square root of 3 times the gas constant times temperature over the molar mass, which is in kilograms. But since we don't have that, if we don't have the molar mass, we actually have to rewrite this to where it's the molar mass is equal to 3 RT over the U, RMS. Okay, so we can rewrite that, plug in the numbers for this. So I'm going to have 3 times the gas constant, which is 8.314, multiplied by the temperature, which they give us 20, to add 273 per Kelvin, that's 293 Kelvin, over the root mean squared speed, which is, they gave us 493 meters per second. And when you solve for this, it is going to come out to be 0.03007 kilograms per mole. And when we put this in grams to mole, it's going to be 30 grams per mole. So the compound has a molar weight of 30 grams per mole. And this is an oxide, so oxygen is included. So an oxygen is 16. You just take out 30 minus 16, you're left with 14. And which element on the periodic table roughly has a molar mass of 14? Nitrogen. So this compound is going to be NO. Because nitrogen is 14, oxygen is 16, and that gives you a total of 30 grams per mole.
So for this problem, we're supposed to find the kilojoules of heat released per gram of the compound, per gram of compound reacted with oxygen. The given reaction is the following. So the first step in solving this problem is finding the delta H of this entire reaction, and from there we can find the final answer. So delta H of this entire reaction can be expressed as the 9 times the heat of formation of H2O plus 5 times the heat of formation of B2O3 minus the heat of formation of the reactants. But for oxygen, we know that that's 0 because it's an element. So the only thing we need to subtract is 2 times the heat of formation of B5H9. And so when we look up the heats of formation for each of those things, we can then plug those values into this equation. So for the heat of formation of water is negative 285.8 kilojoules per mole. The heat of formation of B2O3 is negative 1,263.5 kilojoules per mole. And finally, the heat of formation of B5H9 is 73.2 kilojoules per mole as given in the problem. When we put all of that into the calculator, you will see that this yields negative 9,036.1 kilojoules per mole. Now the problem here is that this isn't the final answer because it isn't in terms of the grams of oxygen that is reacted. And so we need to express it in terms of grams. So we know that negative 9,036 kilojoules are released per every 2 moles of B5H9. We simply then divide by the molar mass of B5H9 to get it in terms of grams. And the molar mass of B5H9 happens to be 63 grams. And when we plug that in, you get that the final answer is negative 71.7 kilojoules per gram of B5H9. And that is the final answer.
Okay, this is question 156 from chapter 11, and we'll be using the ideal gas equation and the van der Waals equation to find the percent error to find the pressure. So first, let's start with the ideal gas law, which is equal to PV equals nR. Okay, so we're going to solve for that first, and you have to solve for pressure. So I'm going to rewrite it as P is equal to nRT over volume. Okay, and when we plug it in, we have 5.00 moles times the gas constant, which is 0.0806 liters times atmosphere per mole times Kelvin, multiplied by the temperature, which is 300, all divided by the volume, which is 1.92 liters. And this is going to come out to be 64.1 atmospheric pressure. Okay, so this is it for the ideal. Now I want to do the van der Waals equation. Okay, so the van der Waals equation is equal to pressure is equal to nRT